The universe, a vast and enigmatic expanse, has captivated human imagination for millennia. From the twinkling stars above to the distant galaxies that stretch across the cosmos, every celestial body, whether a star, a planet, or an entire galaxy, holds within it crucial clues about the origins of everything we know. Our place in this grand and ever-expanding universe is something we continuously strive to understand. As we embark on a journey to unravel the secrets of the stars, explore the mysteries of starlight, and search for life beyond our world, the universe beckons us to explore its many layers of knowledge. These layers are waiting to be uncovered, offering endless revelations about the very nature of existence itself. One of the most compelling questions that has preoccupied humanity for centuries is, how did the universe come into being? Numerous theories have been proposed over time, but one stands out as the cornerstone of modern cosmology: the Big Bang Theory. According to this theory, the universe began around 13.8 billion years ago from an extraordinarily hot and dense state, though it wasn't an explosion in the traditional sense. Instead, it was the rapid expansion of space itself, a vast, sudden stretching that initiated the creation of all the matter and energy that make up the universe today. As the universe expanded, it began to cool, and this cooling process allowed for the formation of fundamental particles. These particles eventually coalesced to form the simplest atoms, mainly hydrogen and helium. Gravity played a crucial role in this cosmic dance, pulling together these atoms and sparking the birth of stars and galaxies. Over billions of years, these stars and galaxies evolved, leading to the intricate and complex structures we observe today. The remnants of the universe's earliest moments can still be detected in the faint, ubiquitous glow of cosmic microwave background radiation, a relic from the very beginning that now permeates the cosmos. But the Big Bang Theory, while widely accepted, isn't the only lens through which we can view the origin of the universe. So, some scientists delve into even more speculative realms, exploring the possibility of a multiverse, a collection of universes, each governed by its own set of physical laws and constants. In this scenario, our universe is merely one among many, each with its own unique properties. This would mean that the Big Bang was not a singular event, but part of an ongoing cycle, universes expanding and contracting in a never-ending cosmic rhythm. Such ideas challenge the conventional notion of beginnings and endings, opening up profound questions about the very fabric of reality and the true nature of existence. Regardless of which theory resonates most with any given individual, the quest to understand the origin of the universe remains one of humanity's most profound intellectual and philosophical journeys. Each of these theories compels us to question our place in the vast cosmic expanse and encourages us to contemplate the fundamental principles that govern the universe's workings. As we continue to explore, we are filled with an ever-deepening sense of wonder, driven by the desire to understand the very nature of reality itself. The universe is far more than a random collection of stars, planets, and galaxies. It is a dynamic, living tapestry woven from the delicate threads of time, space, and matter. The Big Bang Theory remains central to modern cosmology, reshaping how we understand the universe's origins. According to this model, the universe began as an infinitely small, dense point, one that suddenly expanded, marking the commencement of space and time itself. This pivotal event set the stage for everything that followed, from the birth of the first particles to the formation of the galaxies we now study. Before the widespread acceptance of the Big Bang Theory, other ideas about the universe's beginning were proposed. Some imagined a timeless and unchanging cosmos, while others speculated about a universe in which expansion and contraction occurred in cyclical patterns. However, observations of distant galaxies in the 1920s provided the first solid evidence against these static models. It was discovered that galaxies were moving away from us, indicating that the universe itself was expanding. Further discoveries, like the detection of cosmic background radiation, provided even stronger evidence for the Big Bang, making it the leading explanation for the universe's origins. What makes the Big Bang Theory so captivating is its implication that the universe once existed in a state of unimaginable energy. As space expanded and cooled, it created the conditions necessary for the formation of basic particles, protons and neutrons, that eventually gave rise to the atoms that make up the matter we observe today. This process set the stage for the formation of stars, galaxies, and the complex structures that now fill the cosmos. The cosmic background radiation that permeates the universe is a faint echo of that early energetic state, a snapshot of the universe in its infancy. The Big Bang Theory does more than just explain the universe's origins. It also provides profound insights into its future. As scientists continue to study the ongoing expansion of the universe, they are unlocking more mysteries, particularly in relation to dark matter and dark energy, two elusive phenomena that continue to perplex even the brightest minds in cosmology. This ongoing journey to understand the universe's past, present, and future has sparked a deeper curiosity about our place within it, making the Big Bang not just a story of how it all began, but also a dynamic narrative that unfolds before our eyes. An intriguing extension of the Big Bang Theory is the concept of cosmic inflation. This theory proposes that immediately following the Big Bang, the universe underwent an incredibly rapid expansion, far faster than anything we see today. This expansion, lasting only fractions of a second, helped explain certain puzzling features of the universe, including its large-scale uniformity and structure. Cosmic inflation adds another layer of complexity to our understanding of the universe, suggesting that the very fabric of space-time itself underwent dramatic changes in those early moments. As we continue to explore these theories and refine our understanding of the cosmos, one thing remains clear. The story of the universe is far from over. The search for answers, whether in the remnants of the Big Bang or the mysterious realms of dark energy, is an ongoing journey that will continue to shape our understanding of the universe for generations to come. One of the most compelling and robust pieces of evidence supporting the theory of cosmic inflation comes from the observations of the cosmic microwave background, CMB, radiation. This faint, lingering afterglow is a relic of the Big Bang, stretching across the entire universe. It serves as a faint echo of the universe's earliest moments. When scientists carefully examined this afterglow, they discovered that it contained tiny, intricate fluctuations, tiny variations in temperature, matching predictions made by models of inflationary theory. These fluctuations are not random. They reveal a precise pattern that strongly suggests the universe underwent an incredibly rapid expansion during its earliest moments. This discovery is significant because the fluctuations in the CMB are not just a random scattering of data points. They show a coherence, a fine-tuned structure that points directly to the dramatic expansion theorized by inflation. The smoothness or near-perfect uniformity of the temperature across vast stretches of the cosmos further supports the inflationary hypothesis. Without such a rapid expansion in the early moments of the universe, we would expect to see more pronounced temperature variations across different regions of space. Prior to inflation, distant parts of the universe would not have had enough time to exchange energy and equalize in temperature. Yet, the microwave background radiation shows a surprising and striking consistency. This uniformity is a key feature that perfectly aligns with the predictions made by inflationary models. Another critical aspect of this story lies in the large-scale structures of the universe, particularly the distribution of galaxies. When we observe how galaxies cluster together, we notice they form a vast interconnected web-like structure that spans the entire universe. This cosmic web can be traced back to the initial density fluctuations introduced during inflation. These minute early deviations in density grew over billions of years, amplified by the force of gravity, eventually leading to the formation of galaxies, galaxy clusters, and all the complex structures we observe today. This alignment between the theory and what we observe in the cosmos provides powerful validation of the inflationary model, further reinforcing its credibility. As technology and observational methods continue to advance, the case for inflation only becomes more robust. High-precision measurements from satellite missions like the Planck spacecraft have provided us with incredibly detailed maps of the CMB. These maps allow scientists to examine the fine features of the background radiation with unprecedented clarity. When compared to the predictions made by inflationary models, these observations reveal a stunning agreement, bolstering the theory's place in the history of the universe. The combination of these observations paints a clear and compelling picture of an early universe that expanded at an extraordinary rate, setting the stage for the formation of the cosmos we see today. In the grand scheme of the universe, dark matter and dark energy play critical roles, yet they remain some of the most elusive and mysterious components of the cosmos. Dark matter, which is believed to make up about 27% of the universe, acts like a cosmic glue. It is invisible, not emitting light or radiation, but its presence can be inferred by observing its gravitational effects on visible matter. Dark matter helps to hold galaxies together, preventing them from flying apart as they spin through space. Without dark matter, the universe's structure would be vastly different, likely chaotic and far less organized. On the other hand, dark energy, which constitutes about 73% of the universe, is the force driving the accelerated expansion of space itself. Unlike dark matter, which exerts a gravitational pull and brings things together, dark energy acts in the opposite direction, pushing galaxies away from each other. It is thought to be responsible for the accelerating expansion of the universe, a phenomenon that was first observed in the late 20th century. This discovery has profound implications for the future of the cosmos. Will the universe continue to expand forever, drifting apart into a cold, sparse void, or will the forces of gravity eventually slow the expansion and reverse it, leading to a cosmic collapse? During the formation of the universe, following the Big Bang, dark matter provided the scaffolding that allowed ordinary matter, such as the matter that makes up stars, planets, and life as we know it, to coalesce. As clouds of gas and dust fell into the gravitational wells created by dark matter, they collapsed to form galaxies, stars, and the intricate structures of the universe. Without dark matter, these structures would never have been able to form in the way we observe them today. It serves as the unseen framework upon which the visible universe was built and continues to evolve. In contrast, dark energy began to dominate the scene as the universe aged. Initially, the gravitational pull of dark matter was strong enough to slow the expansion of the universe. However, over time, as the universe grew older, the repulsive force of dark energy began to take over. This shift led to the accelerated expansion we see today. Thus, dark matter and dark energy are inextricably linked, each playing a crucial role in shaping the past, present, and future of the cosmos. Their interplay is a key factor in determining the ultimate fate of the universe. The cosmic microwave background radiation, CMB, holds a foundational place in our understanding of the universe. This faint, pervasive glow fills the entire cosmos and can be detected no matter where we look. The CMB is a remnant of the very early universe, originating from an event called recombination, which took place about 388,000 years after the Big Bang. During this event, the universe had cooled enough for electrons and protons to combine, forming neutral hydrogen atoms. For the first time, light could travel freely through space, and the universe became transparent to radiation. The CMB is the leftover light from this era, offering a direct glimpse into the infant universe. The significance of the CMB lies in the information it carries about the conditions of the universe at that time. By studying the subtle fluctuations in temperature within the CMB, scientists can glean insights into the density variations that existed in the early universe. These variations, often described as the seeds of cosmic structures, would eventually give rise to the galaxies, stars, and clusters that we see today. In essence, the CMB acts like a snapshot of the universe in its infancy, capturing details about conditions that have long since disappeared, but still shape the universe in which we live. The cosmic microwave background, CMB, radiation stands as one of the most significant pieces of evidence supporting the Big Bang theory, a discovery that has revolutionized our understanding of the universe. The precise measurements of its temperature and spectrum align with the predictions made by this theory, solidifying the framework that explains the universe's origins. These findings have deepened our understanding of cosmic evolution, offering a clearer picture of the universe's early moments. Scientists have meticulously examined this faint radiation, uncovering groundbreaking revelations about the universe's expansion and the enigmatic presence of dark energy. The study of the CMB has blossomed into a dynamic field of research, offering insights into the universe's birth and ongoing evolution. As technology progresses and new instruments are developed, the scope for understanding this radiation only expands, promising even greater discoveries about the universe's secrets. Each new step forward in research brings us closer to unlocking mysteries that have lingered since the very beginning of time. This small but profound slice of the universe's history draws us in, inspiring endless questions about the very nature of reality itself. At the heart of the universe lies a stunningly complex and intricate structure, woven together by galaxies. These colossal systems, composed of stars, gas, dust, and dark matter, are not scattered randomly throughout space. Instead, they are organized into groups and clusters, some of which contain hundreds or even thousands of galaxies, all bound together by the gravitational forces exerted by their combined mass. Stepping back further to examine the universe on an even grander scale, we encounter superclusters, vast collections of galaxies and galaxy clusters spread out across enormous distances. Take, for instance, the Lanaka supercluster, which includes our own Milky Way. It contains over 100,000 galaxies. The distances between superclusters are so vast that they often exceed several hundred million light years, highlighting not just the immense scale of the universe, but also the vast emptiness that lies between them. When we examine the distribution of these superclusters, a stunning and intricate framework emerges: the cosmic web. This structure consists of vast networks of filaments composed of galaxies and dark matter. These filaments stretch across the cosmos, connecting vast, nearly empty voids of space, regions with few, if any, galaxies. The arrangement of this cosmic web can be compared to soap bubbles, where the filaments represent the threads connecting the bubbles. The shape of the cosmic web is governed by gravity, which dictates how matter clumps together over cosmic time. Understanding the vast scale of these structures provides us with more than just a snapshot of the universe's current state. It reveals its history, the processes that have shaped its expansion, and the evolution of matter within it. The formation and arrangement of galaxies, clusters, and superclusters offer clues about the universe's past, from its infancy to its present-day structure. Every layer of this immense cosmic structure, whether it be the smallest galaxies or the largest superclusters, adds another chapter to the story of existence, both captivating our imaginations and deepening our understanding of the universe. Galaxies, those massive cosmic systems made up of stars, gas, dust, and dark matter, are products of a remarkable journey that began long ago, soon after the Big Bang. In the earliest stages of the universe, particles began to clump together due to the influence of gravity, leading to the formation of vast gas clouds. Over millions of years, these clouds collapsed under their own weight, triggering the process that would eventually lead to the birth of stars. As stars ignited, they began to interact and merge, forming larger structures that would eventually evolve into the galaxies we observe today. The characteristics that define a galaxy, its size, shape, and star content, depend largely on its structure. Galaxies are typically classified into three primary categories: spiral, elliptical, and irregular. Spiral galaxies, such as our Milky Way, are defined by their beautiful, sweeping arms that radiate out from a central bulge. These arms are rich in younger stars and are teeming with gas and dust, making them vibrant hubs of ongoing star formation. The arms of spiral galaxies are the sites of intense cosmic activity, where new stars are born from collapsing gas clouds in vast stellar nurseries. In contrast, elliptical galaxies are generally more spherical or oval in shape, often with a smoother, less defined structure. These galaxies tend to contain older stars with far less gas and dust compared to their spiral counterparts. As a result, they experience little to no star formation, which gives them a more subdued, aged appearance. The lack of new star creation leaves these galaxies with a more uniform, featureless look, reflecting the passage of time and the inevitable aging of the stars within them. Thus, from the formation of the universe's earliest structures to the vast and diverse array of galaxies we see today, every aspect of the cosmos reflects a history of cosmic evolution. Each galaxy, star, and cluster contributes to the ongoing saga of the universe, telling a story of growth, transformation, and endless discovery. And as we continue to explore the cosmos, we are bound to uncover even more about the forces that shape everything around us, pushing the boundaries of our understanding of existence. Irregular galaxies stand out in the cosmos because of their distinct lack of shape compared to their spiral and elliptical counterparts. Often appearing disordered and chaotic, these galaxies defy the regular patterns that typify the more familiar galactic forms. Their irregularity can arise from various cosmic events, particularly gravitational interactions with neighboring galaxies or the remnants of past mergers. This disorder doesn't make them any less significant. In fact, it adds a unique vitality to their structure. Irregular galaxies tend to be rich in both gas and dust, which fuels the birth of hot, young stars. These stars contribute to the dynamic energy of the galaxy, making irregular galaxies both lively and complex entities within the grand tapestry of the universe. The presence of these galaxies highlights one of the most fascinating features of the cosmos: its diversity. This diversity doesn't just reflect the varying stages of cosmic evolution, but also invites us to explore the deeper mysteries that lie within our astronomical backyard. Each galaxy, regardless of shape or size, tells a story of cosmic processes that have played out over billions of years, shaping the structure of the universe as we know it. The universe itself is structured like an intricate web, a cosmic lattice that interlinks galaxies in a grand yet somewhat chaotic fashion. Known as the cosmic web, this network is made up of superclusters, vast collections of galaxies bound together by gravity, and the immense voids between them. Superclusters are some of the largest known structures in the universe, often containing thousands of galaxies clustered together in dense formations. These superclusters can span hundreds of millions of light years, serving as the cosmic hubs of the universe. They are the dense nodes of the cosmic web, where galaxies are not only packed closely together, but interact in fascinating ways, sometimes colliding, merging, or simply influencing each other's evolution. In stark contrast to the superclusters are the voids. These vast expanses of space contain very few, if any, galaxies. Stretching across tens of millions of light years, voids make about 80% of the volume of the universe. Though they may seem empty, these regions are crucial to the overall structure of the cosmos. They act as the spaces between the superclusters, creating a delicate balance in the cosmic web. This interplay between the crowded regions of the superclusters and the emptiness of the voids provides us with critical insights into the underlying forces that shape the universe. The formation of these superclusters and voids is driven by the same fundamental force: gravity. Superclusters grow and evolve through gravitational attraction, where the massive amounts of matter in these regions pull galaxies toward them. On the other hand, voids form as the gravitational pull of matter in surrounding regions attracts more matter, leaving vast empty areas in between. This cosmic dance of formation and emptiness reveals much about the history of the universe, showcasing how it has evolved over billions of years. Each supercluster and void plays an integral role in the dynamic structure of the universe, contributing to our understanding of phenomena such as dark matter, dark energy, and the very expansion of the universe itself. The universe in all its complexity is a living, breathing entity, constantly evolving, with every galaxy, cluster, and void telling a story etched into the very fabric of space and time. This intricate distribution of matter, shaped by gravity, has profound implications for the continued expansion and evolution of the universe. At the heart of this cosmic structure is the mysterious substance known as dark matter. Although invisible, dark matter constitutes a significant portion of the universe's total mass. Its influence is felt through its gravitational effects on galaxies, guiding their motion and shaping the visible structures that we observe today. Dark matter acts as a scaffolding, providing a framework that helps to shape galaxies, clusters, and superclusters. This interplay between dark matter and visible matter is a central theme in modern cosmology, driving much of the research and discovery in the field. Understanding the distribution of matter in the universe is key to piecing together the history of the cosmos. From the moment of the Big Bang, matter began to clump together, drawn by gravity into larger and more complex structures, such as galaxies, clusters, and superclusters. This clustering of matter not only influenced the formation of stars and galaxies, but also contributed to the expansion of the universe itself. As regions of higher density attracted more matter, they helped to determine the speed and direction of cosmic expansion. The formation of cosmic voids, those vast stretches of empty space, also plays a crucial role in our understanding of the universe's evolution. These voids, created by the gravitational influences of surrounding matter, provide valuable insights into how galaxies and larger structures have evolved over time. By studying the distribution of galaxies, astronomers are able to trace the history of the cosmos, revealing the patterns of cosmic evolution and the interaction of matter over billions of years. As scientists continue to study the intricate structure of the universe, they are also uncovering the mysteries of dark energy, the enigmatic force responsible for the accelerated expansion of the cosmos. Though still poorly understood, dark energy is thought to be one of the most significant drivers of the universe's expansion, shaping the very fate of galaxies and the cosmos itself. The study of these forces, gravity, dark matter, and dark energy, forms the backbone of modern cosmology, driving our understanding of the universe's past, present, and future. The ultimate fate of galaxies is one of the most captivating mysteries in cosmology. The universe is expanding, but the rate of that expansion is not uniform. This irregularity has led scientists to propose several possible scenarios for the future of galaxies. One such possibility is the Big Freeze, a scenario in which the universe continues to expand and galaxies drift farther apart over time. This would lead to a dark and empty night sky, with stars and galaxies fading into the cold expanse of space. Another potential outcome is the Big Crunch, where the expansion of the universe eventually halts and reverses, causing galaxies to collapse back into a dense singularity-like state. In this scenario, the gravitational forces of the universe would overpower the expansion, pulling everything back together into a cosmic implosion. However, current observations of the accelerating expansion, fueled by dark energy, suggest that the Big Freeze is a more likely outcome than the Big Crunch. Yet another possibility is the Big Rip, a theory in which dark energy grows increasingly powerful, eventually tearing apart galaxies, stars, and even atoms. Such an outcome would mark an abrupt and cataclysmic end to the universe, ripping apart all structures and leaving nothing behind. These possible fates, each one more mind-boggling than the last, raise profound questions about the future of cosmic structures and the fundamental forces that shape the universe. As researchers continue to investigate the fate of galaxies, they are using advanced telescopes and cosmic observations to unravel the behavior of galaxies over billions of years. These discoveries not only fuel scientific inquiry, but also spark deep philosophical questions about the future of the cosmos and the nature of existence itself. The fate of galaxies and the universe as a whole compels us to reflect on the nature of time and our place in this vast, ever-evolving cosmos. Time itself, in the context of the universe, is not as straightforward as it may seem. While humans tend to think of time as a steady, uniform progression from past to present to future, the flow of time in the cosmos is far more complex. According to Einstein's theory of relativity, time is not constant. It can stretch, warp, and even slow down depending on the influence of gravity. For example, near a massive object like a black hole, time moves more slowly compared to a distant observer. This phenomenon, known as time dilation, illustrates that time is a relative concept, one that is affected by both gravity and motion. If you were to orbit a black hole, time would appear to pass much slower for you than for someone far away from the black hole's gravitational pull. The closer you get to the black hole, the more pronounced the effect would become. This strange property of time adds a layer of mystery to our understanding of the universe and suggests that the passage of time, as we experience it on Earth, is but a small part of a much larger, more complex cosmic picture. Time in the universe is not only relative to the observer, but it is also deeply intertwined with the very forces that shape the cosmos, from the expansion of the universe to the behavior of galaxies, stars, and even black holes. Furthermore, when we explore the vast expanse of the universe, time itself takes on a more complex dimension. Since the dawn of the Big Bang, time has been intrinsically tied to the expansion of space itself. As galaxies continue to drift farther apart, the experience of time on a cosmic scale shifts dramatically. This phenomenon suggests that our perception of time is not a universal constant, but one deeply shaped by the unique conditions of our tiny corner of the cosmos. The contrast between our daily existence, bound by a rigid framework of time, and the boundless, ever-evolving nature of the universe offers a striking juxtaposition. It presents us with a reality that feels both foreign and awe-inspiring. In conclusion, while our daily lives are governed by a consistent ticking clock, the cosmos reveals a far more intricate and dynamic relationship with time. Time can bend and stretch, influenced by the powerful forces of gravity and the expansion of the universe itself. This not only underscores the extraordinary nature of our existence, but invites us to question the larger truths that govern the universe, sparking our curiosity and deepening our sense of wonder. Over a century ago, Albert Einstein's groundbreaking theory of relativity revolutionized our understanding of time and space. Traditionally, we have viewed time as a constant, unyielding force, and space as a fixed arrangement of distances and positions. However, Einstein's theory shattered these simple concepts, revealing a more interconnected and fluid reality. Time and space are no longer separate, but are intertwined, subject to the influences of factors such as velocity and gravity. This insight led to a series of unexpected and often counterintuitive revelations. One of the most captivating aspects of relativity is the concept of time dilation. This phenomenon shows us that time does not flow at a single constant rate. Instead, it moves at different speeds depending on how fast an object is moving relative to another. For example, if someone were to embark on a journey through space at speeds nearing that of light, they would experience time much more slowly compared to someone who remains on Earth. This means that upon their return, they could find themselves physically younger than their peers, despite having traveled far into the universe. This strange reality challenges everything we thought we knew about aging and the passage of time itself. Relativity also reshapes our understanding of space. According to Einstein, objects moving at high speeds appear to shrink in length along the direction of motion. This effect, known as length contraction, is negligible at everyday speeds, but becomes increasingly significant as one approaches the speed of light. This leads to a curious phenomenon where two observers, each moving relative to the other, might disagree on the lengths of objects and the distances between them, complicating our conventional views of space and spatial relationships. Moreover, gravity plays a crucial role in altering our perception of both time and space. General relativity tells us that the presence of mass warps the very fabric of space-time, influencing the flow of time. For instance, clocks located closer to massive objects, like planets, tick more slowly than those situated farther away. This means that time is not an absolute, unwavering force. Instead, it is pliable, shaped by the gravitational pull of objects in the universe. This realization leads us to reconsider the fundamental nature of reality, revealing a universe far more mysterious and wondrous than we had previously imagined. Time is not only a fascinating concept in the realm of physics, but also a profound element of various cultural philosophies. In many Western traditions, time is often conceived as linear, a continuous march from the past through the present and into the future. This viewpoint aligns with scientific perspectives, where time is considered a measurable, consistent progression, much like a river flowing steadily forward. The clocks and calendars we rely on today reflect this linear understanding, segmenting our lives into hours, days, and years. Yet other cultures offer a refreshing contrast. Many indigenous traditions view time as cyclical, emphasizing the recurring patterns of nature, seasons, and life events. In this view, time is not a one-way trajectory, but a series of repeated cycles, with history continuously shaping the present and future. The universe, in this context, becomes a place of renewal, where the rhythms of life and nature are eternally in flux, with the past informing the future in a never-ending loop. In Hinduism, time is conceptualized as vast cosmic cycles, known as the yugas. These cycles describe the endless dance of creation, preservation, and destruction, where entire epochs come and go. This cyclical understanding of time reflects a vision of the universe as a living, breathing entity, one that evolves over countless ages, offering a deep sense of continuity alongside profound transformation. Similarly, ancient Chinese philosophy weaves time into the very fabric of the natural world, where the passage of time is governed by the dynamic interplay of yin and yang. Here, balance and harmony dictate the rhythm of time, with the universe continuously shifting between opposing forces in an eternal cycle of change. When we consider these diverse cultural perspectives on time, we gain a deeper understanding of how humanity has grappled with its place in the cosmos. Whether viewed as a linear progression or a cyclical rhythm, these interpretations reflect our shared desire to make sense of the vast and expanding universe. Ultimately, our understanding of time shapes our connection to the stars and to the cycles of life itself, guiding us as we navigate the intricate web of existence. To grasp the relationship between black holes and the fabric of space-time, we must first understand how space-time is envisioned in physics. Imagine space as a flexible fabric that can stretch and bend, influenced by the mass of objects within it. When massive celestial bodies like stars exert a powerful gravitational pull, they warp this fabric, causing everything around them to move in response. Black holes represent the most extreme manifestation of this warping. A black hole forms when a massive star collapses under its own gravity, creating a point of infinite density known as a singularity. The gravitational pull of this singularity is so intense that it attracts nearby matter and energy, pulling everything toward it. The gravity within this region becomes so powerful that not even light can escape, marking the defining characteristic of a black hole. The boundary surrounding the black hole, known as the event horizon, represents the point of no return. Once something crosses this boundary, it is irrevocably drawn into the black hole's grasp, unable to escape. The interaction between black holes and space-time has profound implications for our understanding of the universe. Black holes reveal how gravity can warp the fabric of space-time to such an extreme degree that the conventional laws of physics break down. The motion of objects near a black hole is dramatically altered, with trajectories forced into spirals and curves. This relationship between black holes and space-time opens new avenues for scientific inquiry, offering insights into the nature of gravity and the fundamental forces that govern the cosmos. As we continue to explore these mysteries, we uncover the intricate ways in which black holes influence the universe's grand tapestry, highlighting the profound interconnectedness of all things. Wormholes, often a staple of science fiction, offer a fascinating theoretical possibility for traveling across the universe. Imagine a tunnel that connects two distant points in space-time, potentially allowing for instantaneous travel between them. This concept arises from Einstein's theory of general relativity, which suggests that the fabric of space-time can be warped in such a way that shortcuts, wormholes, could exist, linking far-flung regions of the cosmos. Though largely speculative at this point, the idea of wormholes challenges our traditional understanding of space and time, offering tantalizing possibilities for future exploration. Wormholes, those mysterious cosmic tunnels connecting distant points in space-time, offer both a tantalizing prospect for space travel and a fundamental challenge to our understanding of physics. The very nature of these theoretical constructs pushes the boundaries of what we know about the universe. However, not all wormholes are stable. Many could collapse before anything even had a chance to traverse them. Theorists speculate that exotic matter possessing negative energy density could be the key to keeping a wormhole open, offering a path for future explorers to journey across vast cosmic distances. Throughout history, numerous cosmic events have captivated humanity's imagination, inspiring myths, fueling scientific curiosity, and influencing cultures across the globe. From the earliest observations of the heavens to modern astronomical breakthroughs, some celestial occurrences stand out for their profound significance. One such event is the reappearance of Halley's Comet, a spectacle that has been recorded for over 2 millennia. Its next appearance in 176 appeared almost as a harbinger, stirring awe and fear alike. Halley's Comet, with its predictable return every 76 years, serves as a vivid reminder of the intricate mechanics of our solar system and the deep cycles that govern the movements of celestial bodies. Another historic event that left an indelible mark on our understanding of the universe was the supernova explosion observed in the year 1001. This stellar cataclysm, designated SN 1006, was so brilliantly luminous that it could be seen even during daylight hours, continuing to shine for weeks. The explosion was the death throes of a massive star, and its spectacular brightness provided astronomers a rare opportunity to study the life cycle of stars in real time. This supernova not only expanded our knowledge of stellar evolution, but also sparked philosophical debates about the nature of the universe itself. In the early 20th century, another cosmic milestone occurred, the total solar eclipse of 1919. This event, which took place on May 29th, allowed scientists, including the legendary physicist Albert Einstein, to observe the bending of light around the sun, a phenomenon predicted by his theory of general relativity. The successful observations during this eclipse served as a cornerstone for modern physics, confirming the existence of gravitational lensing and reshaping our understanding of gravity. Einstein's prediction that mass warps the very fabric of space-time was verified, propelling the study of cosmology into new realms of inquiry. Fast forward to 1990, and we witnessed the launch of the Hubble Space Telescope, a transformative moment in the exploration of our universe. The telescope has provided us with breathtaking images of faraway galaxies, nebulae, and black holes, each snapshot revealing the hidden wonders of space. More than just a tool for capturing stunning images, Hubble has significantly enhanced our understanding of the universe's age, its expansion, and the mysterious forces shaping its evolution. The data gathered by Hubble continues to be a vital resource for scientists, helping to piece together the vast, intricate puzzle of the cosmos. Among the most awe-inspiring events in the universe are supernovae, the explosive deaths of massive stars. When a star reaches the end of its life, it can no longer sustain the nuclear reactions at its core. This failure causes the star to collapse under its own gravity, triggering a violent explosion that ejects the star's outer layers into space. But these explosions are more than just the end of a star. They act as cosmic forges, creating a range of elements, especially those heavier than iron. In the intense heat and pressure of a supernova, nuclear reactions form elements like gold, silver, and uranium, which are then scattered into space. These newly formed elements enrich the interstellar medium, the gas and dust that fill the universe, becoming the building blocks of new stars and planets. The death of a star is thus not an end, but rather a vital stage in the cycle of creation, contributing to the formation of the next generation of celestial bodies. The very atoms that make up our bodies were forged in the cores of ancient stars, then scattered across space, only to be incorporated into new stars and planets. This cycle of birth, death, and rebirth is one of the most profound aspects of the universe, highlighting its interconnected nature. In the realm of neutron stars, pulsars offer a unique opportunity to explore the extreme conditions of the universe. These highly magnetized, rotating remnants of collapsed stars emit beams of electromagnetic radiation that sweep across space in regular pulses, much like a cosmic lighthouse. When these pulses are observed from Earth, they are incredibly consistent, allowing scientists to use them as natural clocks. By studying pulsars, we gain insights into the properties of neutron stars and the effects of extreme gravitational fields and intense pressures. Pulsars also serve as laboratories for testing theories of gravity and space-time, providing valuable data on how mass warps the fabric of the cosmos. Quasars, on the other hand, represent another fascinating class of cosmic objects. These incredibly luminous centers of distant galaxies are powered by supermassive black holes that consume surrounding gas and dust at an astonishing rate. As this material is devoured, it generates immense energy, making quasars the brightest objects in the universe, often outshining entire galaxies. Observing quasars provides astronomers with a glimpse into the early universe, as many of these objects formed when the cosmos was still young. By studying them, scientists gain crucial insights into the formation of galaxies, the conditions of the early universe, and the expansion of space-time itself. Together, pulsars and quasars provide invaluable tools for understanding some of the universe's most extreme phenomena. Pulsars help refine our understanding of gravity, while quasars challenge our theories about the evolution of galaxies and the role of black holes in shaping their environments. These objects, despite their vastly different nature, are interconnected by their ability to illuminate the mysteries of the cosmos, helping scientists explore both the distant past and the future of our universe. Gravitational waves, ripples in the very fabric of space-time, offer another exciting frontier in astrophysical research. Predicted by Albert Einstein over a century ago, these waves were first detected in 2015, confirming a key aspect of his theory of general relativity. Gravitational waves are generated by some of the most cataclysmic events in the universe, such as the collision of black holes or neutron stars. Unlike light, which can be blocked or altered by intervening matter, gravitational waves travel through space almost unaffected, offering a direct, unfiltered signal of cosmic events. The detection of gravitational waves has opened up a new way of observing the universe. Instruments like LIGO and Virgo have recorded countless events, providing insights into the size, spin, and interactions of black holes. These waves allow scientists to listen to the sounds of cosmic collisions, adding a new dimension to our understanding of the universe. Gravitational waves also play a crucial role in the synthesis of heavy elements like gold and platinum. When neutron stars collide, for example, they create not only gravitational waves, but also the conditions necessary for the formation of these precious elements, further linking the cosmos to the origins of life on Earth. As the technology for detecting gravitational waves advances, the potential for groundbreaking discoveries increases. Future observatories will be able to detect even smaller, more distant events, opening up new possibilities for studying the early universe. Each new observation brings us closer to unraveling some of the greatest mysteries of the cosmos, providing a fresh perspective on the immense forces at play in the universe. Gamma-ray bursts, GRBs, among the most powerful explosions in the universe, are another key phenomenon that helps us understand cosmic processes. These bursts release an enormous amount of energy, equivalent to the total output of the sun over its entire lifespan, all within a matter of seconds or minutes. GRBs are believed to be the result of massive stars collapsing to form black holes, providing a glimpse into the violent end of these stellar giants. Studying gamma-ray bursts gives us invaluable insights into stellar evolution and the dramatic processes that lead to the death of massive stars. Through the study of GRBs, we also gain a deeper understanding of the synthesis of heavy elements, such as those that will eventually form planets and life. These violent cosmic events allow scientists to observe the final stages of stellar evolution and the formation of black holes, deepening our knowledge of the universe's most extreme conditions. In all these phenomena, from wormholes to gamma-ray bursts, we see a common thread: the relentless curiosity of humanity to understand the vast and mysterious cosmos. Each discovery adds a new layer to our understanding, connecting us to the universe in ways both profound and humbling. The study of these cosmic events, from the birth of stars to their explosive deaths, continues to illuminate the mysteries of space and time, revealing the dynamic, ever-changing nature of the universe we call home. Gamma-ray bursts, GRBs, are among the most enigmatic and powerful events in the universe, offering scientists an unparalleled opportunity to explore the early cosmos. These bursts, which release an incredible amount of energy, can be observed from distances of billions of light years away, essentially serving as cosmic beacons. As they travel through the vast expanses of intergalactic space, GRBs illuminate the intergalactic medium, essentially the matter between galaxies, which in turn provides a window into the universe's formative years. By analyzing the light from these bursts, astronomers can gain invaluable insights into the conditions that existed during the infancy of the universe. This analysis is crucial for understanding the birth of galaxies and the processes that gave rise to the cosmic structures we observe today. Through this lens, GRBs become more than just violent events. They are essential tools for piecing together the history of our cosmos, allowing researchers to explore its evolution and the forces that shaped it over time. Furthermore, the study of GRBs pushes the boundaries of our technological capabilities. Harnessing the power of cutting-edge telescopes and detectors, scientists have been forced to develop new methods and techniques to observe these fleeting cosmic phenomena. The advancements made in gamma-ray astronomy often ripple out, leading to breakthroughs in other areas of science and technology. These innovations, while originating in the field of cosmology, often have far-reaching implications, resulting in advancements that can impact everyday life. In this way, The investigation of GRBs not only unveils stunning cosmic truths, but also serves as a catalyst for innovation in fields as varied as medicine, communications, and engineering. Similarly, when scientists set their sights on finding potentially habitable exoplanets, they are guided by a set of crucial criteria. One of the first and most fundamental factors is the planet's location in relation to its star. This Goldilocks zone, as it is often called, is the region where conditions might be just right for liquid water to exist, neither too hot nor too cold. If a planet is too close to its star, any water on its surface would likely evaporate, while a planet too far away would see its water freeze. Only in the Goldilocks zone can a planet maintain the stable environment needed for life, as we know it, to possibly thrive. The planet's size and composition also play a pivotal role in determining its habitability. To support life, a planet should ideally be rocky, much like Earth, as opposed to being a gas giant like Jupiter. A planet within the right size range has the potential to hold onto an atmosphere, which is essential for regulating temperature and shielding any potential life forms from harmful radiation. A planet that is too small may lack the gravitational pull needed to retain an atmosphere, while one that is too large may turn into a gas giant, with extreme conditions that are hostile to life as we understand it. Atmospheric conditions are another vital consideration. Researchers examine a planet's atmosphere for signs that it exists and for clues about its composition. An atmosphere that contains essential gases like oxygen and carbon dioxide, and that can sustain pressures conducive to the persistence of liquid water, is crucial for life. The presence of certain gases could even point to biological processes, suggesting that life, in some form, might already be present. This search for habitable exoplanets isn't merely about locating Earth-like planets. It's about finding environments that could nurture life in ways that might surprise us. Finally, the stability of a planet's environment is critical. Scientists look at factors such as orbital stability and potential cosmic events that could disrupt the planet's environment. Habitable planets benefit from a climate that remains relatively consistent over long periods, offering life the time it needs to evolve. By evaluating these criteria, scientists continue to expand their catalog of potential habitable worlds, each one representing a unique opportunity to answer one of humanity's most profound questions. Are we alone in the universe? One of the most intriguing tools scientists use to estimate the potential for life beyond Earth is the Drake equation. First formulated by astrophysicist Frank Drake in the early 1960s, this equation aims to provide a systematic framework for considering the various factors that would contribute to the existence of intelligent civilizations in our galaxy. At its core, the Drake equation is a mathematical model, but its true power lies in the way it encourages us to think critically about what we know and don't know about the universe. It compels scientists to explore the possibilities and limitations of our knowledge, all while inspiring new lines of inquiry. The equation incorporates several key variables, each representing a different aspect of the cosmic conditions necessary for intelligent life to emerge. These factors include the rate of star formation in our galaxy, the fraction of stars that have planetary systems, and the number of planets that could potentially support life. Each variable is an invitation for deeper investigation, underscoring that our understanding of life in the universe is still in its infancy. In this way, the Drake equation helps prioritize research in fields like astrobiology and planetary science, offering direction for future space exploration missions. However, the Drake equation also highlights the considerable uncertainty that remains in the search for extraterrestrial life. Many of the variables are still poorly understood, and this lack of clarity leaves room for speculation and debate. For example, while we know that there are numerous stars in the galaxy, we still have little idea how many of these stars host planets that could support life. This uncertainty fuels the scientific community's drive to gather more data through missions to other planets in our solar system, studies of exoplanets, and searches for extraterrestrial signals. Ultimately, the equation is not only a call to action, but also a reminder of the vastness of the unknown. It frames the search for alien civilizations not merely as a numbers game, but as an exploration of the fundamental conditions that allow life to emerge. The Drake equation continues to inspire the search for knowledge about our place in the cosmos and the possibility that we are not alone. Astrobiology is a rapidly growing field that examines the conditions necessary for life to exist beyond Earth. By using Earth as a reference point, scientists investigate what environments could harbor life, both within our solar system and beyond. One key area of research within astrobiology is the study of extremophiles, organisms that thrive in Earth's most extreme environments, such as deep-sea hydrothermal vents, acidic lakes, and the frozen expanse of Antarctica. These hardy life forms offer valuable insights into the potential for life in the harsh conditions of space. Extremophiles have proven that life can adapt to some of the most inhospitable environments on Earth. Certain bacteria, for example, can survive intense radiation, freezing temperatures, and extreme pressures. This resilience has sparked excitement in the scientific community. If life can survive and even thrive in such harsh conditions on our own planet, then why couldn't similar life forms exist elsewhere in the universe? This question has led scientists to consider worlds like Mars, Europa, and Enceladus, planets and moons in our solar system that may harbor similar extreme conditions capable of supporting life. The study of extremophiles has also shed light on the biochemical versatility of life. Many of these organisms possess unique metabolic pathways and structural adaptations that enable them to utilize resources in ways we are just beginning to understand. This knowledge is guiding astrobiologists in refining their search strategies. It helps scientists identify which types of environments are most likely to support life and what forms that life might take, potentially expanding the definition of what constitutes a habitable world. The fascinating world of extremophiles also influences the types of experiments scientists conduct in the search for life beyond Earth. By studying how these organisms adapt to extreme conditions, researchers can develop more effective methods for detecting life elsewhere. In this way, extremophiles play a critical role in shaping the direction of space exploration. As we look to the stars, we may be guided by the lessons learned from Earth's most resilient organisms, and it is through these discoveries that we may come closer to answering one of humanity's most profound questions. Are we alone? The discovery of water on other planets has been a game changer in our search for extraterrestrial life. For centuries, scientists have speculated about the possibility of life beyond Earth, imagining what kinds of organisms might exist on distant worlds. But when evidence surfaced that water, a crucial element for life, exists on bodies throughout our solar system, it opened up a new realm of possibilities. Water ice discovered on the Moon and Mars, for instance, revealed exciting opportunities for further exploration. On Mars, the detection of liquid water, albeit sporadic, suggests a dynamic climate that may have once supported life in the distant past. This discovery has reignited interest in the search for life beyond Earth, offering tantalizing evidence that perhaps we are not so unique after all. The discovery of subglacial lakes on Europa, one of Jupiter's moons, and the plumes of water vapor erupting from Enceladus, a moon of Saturn, has revolutionized our understanding of what might be possible in the search for life beyond Earth. These seemingly inhospitable icy worlds now offer tantalizing clues, suggesting they could harbor environments where life might not only exist, but thrive. This realization has shifted the scientific perspective on habitability. No longer are we bound by the need for Earth-like conditions to sustain life. Instead, we're expanding our criteria to consider even the most extreme, harsh environments that were once deemed unsuitable for life. The idea that life could flourish in conditions radically different from those on Earth is no longer confined to science fiction. In fact, extremophiles, organisms that thrive in extreme environments on our planet, are a prime example of the remarkable adaptability of life. These organisms, found in places like deep-sea hydrothermal vents, acidic hot springs, or even the frozen reaches of Antarctica, inspire theories about how life might exist on other planets under similar harsh conditions. The diverse forms of water, ranging from frozen ice to salty brines, suggest that life could adapt in ways we have yet to fully understand. This broadens our expectations and fuels the ongoing search for life beyond Earth, in environments we once thought too extreme to support it. As our knowledge of these celestial bodies grows, so too does our curiosity about whether life exists on other planets. This scientific drive has led to a new wave of missions designed to investigate the potential for life-supporting environments in our solar system and beyond. With each new discovery, whether it be the detection of water or the identification of organic molecules, the dream of finding extraterrestrial life inches closer to reality. What once seemed a distant, far-off dream is now transitioning into a tangible scientific endeavor. The pursuit of life beyond Earth is not only driven by our ever-expanding understanding of where water exists in the universe, but also by our deep-seated need to answer one of humanity's oldest and most profound questions. Are we alone? However, the search for life, especially intelligent life, raises numerous ethical dilemmas that touch on the very core of our values and responsibilities as a species. If we were to encounter intelligent extraterrestrial beings, how would we engage with them? Would we approach them as equals, or would we project our own sense of superiority upon them? The potential for miscommunication or misunderstanding could lead to consequences that we are ill-prepared to navigate. Therefore, experts advocate for a careful and respectful approach, emphasizing the need for open, transparent dialogue should we make contact with intelligent extraterrestrial life. Equally important are the ethical dilemmas surrounding our responsibilities toward these beings. Should we choose to share knowledge and resources with them? Should we discover they are technologically advanced? Or conversely, do we have an ethical obligation to assist and protect them if their civilization is less developed than our own? This dilemma mirrors past events on Earth, where more advanced civilizations have interacted with less technologically developed cultures, often with disastrous consequences. The lessons from these interactions remind us of the need to consider the long-term effects of our actions and our responsibilities toward other forms of intelligent life. Moreover, the search for extraterrestrial life also forces us to reevaluate our very definition of life itself. As we explore the cosmos, we are confronted with the idea that life could manifest in forms far different from what we know on Earth. This broadens not only our understanding of what constitutes sentient life, but also calls for an ethical reevaluation of how we regard and treat all forms of existence. Are we prepared to embrace a more inclusive ethical framework that accounts for these potentially vastly different forms of life? The answers to these questions will not only shape our approach to extraterrestrial life, but also challenge the fundamental values upon which our own society is built. In addition, the question of how we prioritize resources in the search for extraterrestrial life raises significant concerns. As we pour vast amounts of time, effort, and money into exploring the universe, one might ask, are we justified in pursuing this search when there are still so many pressing issues on Earth that remain unresolved? This question challenges us to balance our thirst for discovery with our responsibilities to address urgent concerns such as poverty, climate change, and social inequality. The delicate balance between exploring the cosmos and caring for our own planet is a complex ethical tightrope that we must navigate with care. The way we manage this balance will shape our identity as stewards of Earth, as well as our future role in the larger universe. Throughout human history, our relationship with the cosmos has been deeply intertwined with our cultures, beliefs, and everyday lives. Ancient civilizations, from the Egyptians to the Mayans, the Sumerians to the Greeks, looked to the skies and interpreted celestial phenomena in ways that influenced everything from agricultural practices to religious rituals. In ancient Egypt, for example, the alignment of the pyramids with specific stars was no mere coincidence. It was part of a complex system of celestial observation that helped predict the annual flooding of the Nile, an event crucial to the region's agriculture. Similarly, the Mayans developed an intricate calendar system built on their profound understanding of celestial cycles that governed everything from planting seasons to significant religious ceremonies. In Mesopotamia, the Sumerians were among the first to practice astrology, believing that the positions of celestial bodies could influence earthly events. These ancient societies viewed the heavens as a realm imbued with divine significance, and interpreting celestial events was a key part of daily life. Even philosophers in ancient Greece, such as Pythagoras, played a pivotal role in synthesizing knowledge about the stars and planets, laying the groundwork for modern astronomy. These early astronomical endeavors were more than just scientific inquiries. They were deeply spiritual and practical, reflecting humanity's desire to understand its place in the vastness of the cosmos. The ancient belief that the stars held divine messages has evolved over time, but the impulse to understand the universe remains unchanged. Our modern search for extraterrestrial life, grounded in science and technology, is the latest chapter in an ancient quest to comprehend the heavens, a quest that continues to shape our identity and our place in the universe. This journey, which began with mythological interpretations of the skies, has led to the emergence of a new understanding of the universe. Early astronomers laid the foundation for the discoveries we now take for granted, such as the movement of planets, the existence of distant galaxies, and the possibility of extraterrestrial life. What was once seen as the realm of the gods is now understood through the lens of science. But the wonder and awe that these celestial bodies inspire remain ever present, linking us to the stars in ways that transcend the purely scientific. The search for life beyond Earth, whether intelligent or microbial, represents not just a quest for knowledge, but a continuation of humanity's age-old fascination with the cosmos, and its deep yearning to understand the mysteries that lie beyond. However, astronomers like Copernicus and Galileo were pivotal in shifting the prevailing paradigm of the cosmos. They led humanity toward a more systematic, empirical approach to studying the stars and planets. Copernicus's influence, for example, shaped Western thought for centuries. His geocentric model, which placed the Earth at the center of the universe, provided an organizational framework that, despite its inaccuracies, was essential in shaping early astronomical inquiry. While this model was eventually displaced, it sparked a new interest in celestial observations. The meticulous records of planetary movements he inspired laid the groundwork for future astronomers to develop more precise models of the universe. The shift initiated by Copernicus was nothing short of revolutionary. He proposed the heliocentric model, positioning the sun at the center of our solar system, an idea that flew in the face of long-held beliefs. This bold proposition ignited a chain reaction, encouraging researchers to adopt more observational strategies. With the advent of tools like the telescope, astronomers such as Galileo began to gather concrete evidence that contradicted traditional views of the universe. Galileo's observations of planets and moons revealed a far more dynamic cosmos than anyone had previously imagined. The intricate dance of celestial bodies was far more complex than what the ancient models had suggested. This surge in inquiry reached a pivotal moment with Isaac Newton. Newton unified the principles of motion and gravity, laying down laws that explained how celestial bodies interacted. His work allowed astronomers to predict planetary orbits and other cosmic behaviors with unprecedented accuracy. Together, these early astronomers sparked a scientific movement that has only continued to evolve, shaping our understanding of the universe. From mere speculation to data-driven exploration, they inspired generations of scientists to peel back the layers of the cosmos, seeking to uncover its many mysteries. Yet, astronomy's roots extend far beyond Europe. Ancient cultures from across the globe have played an essential role in the development of astronomical knowledge, each offering unique observations and interpretations of the night sky. Civilizations like the Babylonians in Mesopotamia and the Maya in Central America meticulously recorded celestial events, laying down the early framework of what we now understand about the cosmos. For these cultures, astronomy was often intertwined with agricultural cycles, religious practices, and navigation, highlighting the profound connection between the study of the stars and daily life. The Babylonians, in particular, made early and significant contributions. They developed one of the first known star catalogs, keeping detailed records of astronomical phenomena. Their observations led to the creation of a lunar calendar, which was vital for agricultural planning. This early work also helped bridge knowledge across cultures, influencing the astronomical models of later civilizations, such as the Greeks. Meanwhile, on the other side of the world, Indigenous Australians mapped the stars with remarkable precision. Their constellations were not just a way of charting the sky. They were embedded in their stories and beliefs, with the stars representing ancestors and spirits. Their navigation methods, guided by the stars, demonstrated an advanced understanding of celestial navigation, refined over millennia. These diverse cultures' contributions have left an indelible mark on modern astronomy. The legacy of their astronomical knowledge continues to shape our understanding of the universe, demonstrating that the study of the cosmos is not just a scientific pursuit, but a deeply human endeavor, intertwined with culture, religion, and daily life. These early astronomers, philosophers, and navigators remind us that the night sky has long been a source of wonder, inspiration, and inquiry across all societies. In ancient times, astronomers relied primarily on direct observation of the night sky with the naked eye. They studied the positions and movements of stars, planets, and the moon, recording these patterns over time. This method of observation formed the foundation for much of what we know today about celestial movements. Simple tools, such as sticks planted in the ground to mark positions, or stones arranged to create early star maps, were used to track the shifting positions of stars and the cycles of the moon. As centuries passed, astronomers developed more sophisticated instruments to refine their observations. Devices like the astrolabe and armillary sphere were created to help solve complex problems related to time and the position of stars. The astrolabe, for instance, allowed astronomers to measure the altitude of celestial bodies above the horizon using a rotating arm attached to a disk. This tool enabled more precise calculations regarding the location of stars and planets. The armillary sphere, a model of the celestial sphere, provided a way to visualize the intricate movement of celestial bodies in relation to Earth. The invention of the telescope in the 17th century marked a revolutionary leap in astronomy. Crafted by pioneers like Galileo, the telescope enabled astronomers to observe distant stars and planets in greater detail than ever before. Galileo's groundbreaking observations, such as the discovery of Jupiter's moons and the phases of Venus, provided irrefutable evidence that the universe was far more dynamic and complex than previously imagined. These observations challenged conventional wisdom and opened the door for new ways of thinking about the cosmos. In addition to telescopes, early astronomers also relied heavily on mathematics to predict celestial events. They developed complex models to explain the movements of the heavens, looking for patterns that could predict phenomena like eclipses or planetary alignments. Through these methods, early astronomers laid the groundwork for modern astronomy, continually expanding our understanding of the universe. The mythology of the cosmos presents a fascinating tapestry that reflects humanity's age-old desire to understand the universe. Across cultures and eras, celestial bodies have often been ascribed divine attributes, giving rise to a diverse array of myths that sought to explain their movements and their influence on life on Earth. In Egyptian mythology, for instance, the sun god Ra was believed to battle against darkness each night, symbolizing the eternal cycle of day and night. Meanwhile, the ancient Greeks imbued celestial objects with personalities, turning stars, planets, and constellations into gods and heroes. As civilizations evolved, so too did their cosmologies, with new myths emerging to explain the nature of the universe and humanity's place within it. In Eastern traditions such as Hinduism and Buddhism, the cosmos is often seen as an endless cycle of rebirth, reflecting a universe that is infinite and ever-changing. In these traditions, time does not move linearly, but instead follows cyclical patterns, mirroring the natural cycles of life, death, and rebirth. These different views of the cosmos reveal how cultures perceive their relationship to the universe, offering profound insights into how humanity has always sought to understand its place in the grand design. In stark contrast, the scientific revolution brought about a more empirical approach to understanding the heavens. With this shift, mythological narratives began to give way to observations and theories grounded in evidence. The heliocentric model, proposed by Copernicus, was one of the key milestones in this transition. It directly challenged the long-held geocentric view and forever altered humanity's position in the cosmic order. From the laws of motion formulated by Isaac Newton to Einstein's theories of relativity, each new discovery has added depth to our understanding of the universe, blending the poetic myths of ancient times with the rigorous inquiry of modern science. Today, the exploration of the cosmos continues, with new technologies and discoveries offering even more insight into the mysteries of the universe. As our understanding of the cosmos continues to evolve, the conversation between ancient mythologies and modern theoretical physics deepens, painting a picture of an ever-expanding universe. With the rapid advancement of technology, we now explore the vastness of space with tools and instruments that extend the limits of our perception. Yet we find ourselves confronting the same timeless question that humanity has pondered for millennia. What is our place in this infinite universe? This ongoing dialogue between myth and science is not only a reflection of human curiosity, but also a testament to our inherent desire to connect with the cosmos in ways that are both meaningful and profound. In fact, this convergence ensures that the mythology surrounding the universe remains vibrant, evolving, and relevant to each new generation. One of the most thought-provoking ideas that has emerged from this fusion of science and philosophy is the anthropic principle. This concept invites us to ponder not only our existence, but also the very nature of the universe itself. At its core, the anthropic principle posits that the universe's physical properties are finely tuned to allow for the emergence of conscious observers, such as ourselves. In simpler terms, the structure of the cosmos seems to be shaped in a way that supports the existence of life, and in particular, intelligent life. This raises profound questions that transcend the mechanics of the universe, pushing us to consider what it truly means for us to be here at all. There are two primary interpretations of the anthropic principle: the weak anthropic principle and the strong anthropic principle. The weak version of this theory highlights the idea that the observed values of the universe's physical constants, such as the force of gravity or the strength of electromagnetism, are set in such a way that life could emerge. For instance, if the force of gravity were slightly different, stars might not form, and life as we know it would be impossible. This version of the principle simply suggests that the universe, as we observe it, is one of many possible configurations that happen to be conducive to the development of life. The strong anthropic principle takes this a step further, suggesting that the universe must be able to develop intelligent life, capable of asking questions about the nature of existence itself. In other words, the very fact that we are capable of contemplating the question, why does the universe exist, may point to something more profound, that the universe has been designed, or at least appears to be designed, to support conscious beings like us. This interpretation challenges us to reflect not just on the physical properties of the cosmos, but also on the deeper implications of our existence within it. The anthropic principle forces us to consider whether we are mere anomalies in a vast, indifferent cosmos, or if there is a deeper, more meaningful connection between all conscious beings and the universe they inhabit. Are we simply one of countless forms of life, or do we share a cosmic bond that transcends the boundaries of space and time? These questions encourage both scientists and philosophers to seek answers that blend empirical evidence with existential inquiry, inviting us to explore the nature of life and the universe from a more holistic perspective. By delving into these questions, the anthropic principle enriches our understanding of cosmology and invites us to remain curious about the universe's vastness and complexity. It pushes us to not only appreciate the delicate balance of forces that make life possible, but also to recognize that our own existence is part of a much larger interconnected web. Through this principle, we embark on a journey not just to understand the mechanics behind the stars, but to explore the very essence of what it means to be human in a universe that, against all odds, seems designed for consciousness to emerge. Throughout history, philosophy has provided different lenses through which humanity has sought to interpret and understand the cosmos. Ancient philosophical traditions, such as those espoused by the Greeks, set the stage for our modern conception of reality. Thinkers like Pythagoras and Plato viewed the universe as a harmonious, ordered system, suggesting that mathematics and philosophy were deeply intertwined in explaining the cosmos. This belief in an underlying order inspired centuries of scientific exploration, leading to the discovery of the universe as a grand interconnected tapestry. Their vision of the cosmos as an elegant structure laid the foundation for much of the scientific inquiry that followed. In contrast, The materialist perspective that emerged during the Enlightenment era offered a different approach to understanding the universe. Materialism emphasizes a universe governed by physical laws and observable phenomena, arguing that the only true knowledge is that which can be measured and tested. According to this view, the study of the physical properties of stars, planets, and galaxies is paramount, and the metaphysical questions about meaning and purpose are less important. This materialist perspective pushed scientific inquiry toward more rigorous observation and experimentation, eventually leading to breakthroughs in cosmology and physics. On the other side of the spectrum, existentialist and spiritual philosophies take a more introspective approach to the cosmos. These perspectives encourage us to delve into the deeper questions of meaning, existence, and our place within the universe. For example, existentialists who question the nature of reality and human freedom explore the idea that the universe may be indifferent to human existence. In contrast, spiritual philosophies often view the cosmos as a grand, purposeful tapestry, woven together by forces that transcend human understanding. These different worldviews can inspire us to reflect on our connections to the universe and to each other, deepening our sense of wonder and appreciation for the mysteries that surround us. These diverse philosophical orientations not only shape how we interpret the universe, but also influence the questions we ask and the pursuits we undertake in both science and the humanities. The interplay between science and philosophy offers a richer, more nuanced understanding of existence, pushing us to explore not only the mechanics of the universe, but also the meanings that arise from our quest for knowledge. It's through this dialogue that we are prompted to contemplate timeless questions about life, existence, and our role in the grand cosmic drama. Existentialism, as a philosophical movement, plays a significant role in this ongoing quest to understand the cosmos. Focused on the nature of existence, freedom, and individuality, existentialism challenges us to confront the fundamental uncertainties of life and the universe. By emphasizing our personal search for meaning, existentialism encourages us to reflect on our place in an often incomprehensible and chaotic cosmos. As we gaze at the stars or contemplate the vastness of space, existentialist thought pushes us to recognize the inherent uncertainty of existence, urging us to find meaning not in absolute answers, but in the subjective experiences that shape our understanding of the universe. This perspective can deepen our appreciation for the mysterious, sometimes chaotic nature of existence, allowing us to find meaning even in the midst of uncertainty. It encourages us to embrace the complexities and ambiguities of life, knowing that the answers we seek may never be fully realized. Instead, it is through the journey itself, the exploration of both the cosmos and our inner lives, that we come to understand what it means to exist within this vast, mysterious universe. Moreover, existentialism emphasizes the importance of individual responsibility, urging each person to navigate a vast, indifferent universe. As humanity stretches out into the cosmos in search of meaning and answers, we are continually reminded that the significance of our lives doesn't come from external sources, but from the choices we make, the actions we take, and how we interpret our existence. It is in embracing this notion that we not only strive to understand the universe, but also engage in the complex journey of self-discovery. This process shapes our paths in life, this guiding us through personal growth and leading us to explore our own identities against the backdrop of the stars. Ultimately, existentialism enriches our exploration of the cosmos by intertwining the scientific pursuit of knowledge with the deeply personal search for meaning. It challenges us to embrace the uncertainty of the questions we face, rather than focusing solely on the answers. This shift in perspective allows us to develop a deeper connection, not just to the universe around us, but to our own selves. As we journey through the profound mysteries that lie beyond the confines of our world, existentialism pushes us to understand that our search for meaning and purpose is as vast as the universe itself. The question of whether the universe can exist independently of human observation or thought is a profound inquiry that delves deep into the realms of both science and philosophy. The universe, with its unimaginable vastness, countless galaxies, and the intricate laws that govern it, existed long before humanity appeared on Earth. composed of matter, energy, and the fundamental forces of nature, the universe operates on principles that do not require human awareness or perception to persist. However, the question becomes more complex when we turn our attention to quantum physics, a realm where the interplay between observation and reality is particularly striking. In quantum mechanics, the act of observing particles can influence their behavior in ways that are not observed at larger scales. This phenomenon has sparked debates on the nature of reality itself, with some interpretations of quantum theory suggesting that observation plays a critical role in determining the state of a particle. These discussions challenge the objective nature of the universe, leading to fascinating questions about whether our consciousness shapes the very fabric of reality. Despite these thought-provoking theories, most scientists maintain that the universe does not rely on human observation to exist. The stars will continue to shine, and galaxies will continue to swirl, regardless of whether anyone is there to witness them. Our understanding of the cosmos may be shaped by the perspectives we hold and the advancements we make in science, but these discoveries ultimately reflect a reality that has always been there, evolving independently of our awareness. As we delve deeper into these questions, we encounter a unique intersection of science, philosophy, and the very experience of existence. The cosmos, in its grandeur, holds mysteries that far exceed our current understanding, inviting us not only to ponder who we are, but also to reflect on our place within the vast tapestry of the universe. The universe calls us to explore, revealing its wonders and truths, irrespective of how or whether we interpret them. The concept of infinity has fascinated philosophers, scientists, and mathematicians throughout history, shaping our comprehension of the universe in profound ways. When we speak of something as being infinite, we are often referring to an entity that has no boundaries or limits. In cosmology, this idea sparks compelling discussions about the nature of the universe itself. If the universe is infinite, it would stretch endlessly in every direction, housing an uncountable number of galaxies beyond our ability to observe. Infinity also plays a crucial role in theoretical physics, particularly when we consider the origins of the universe. The notion of an infinitely dense point, what we refer to as the Big Bang, challenges our conventional understanding of space and time, pushing the boundaries of what we can truly comprehend. The Big Bang theory, which proposes that the universe began from this singularity, raises questions that stretch the limits of human imagination. What existed before the Big Bang? How can we fully grasp the concept of a universe originating from an infinitely dense point? These inquiries not only invite us to explore the depths of our knowledge, but also provoke awe as we confront ideas that defy conventional reasoning. Moreover, infinity forces us to consider the vastness of space. The observable universe, immense as it is, represents just a tiny fraction of what might lie beyond our reach. Some scientists hypothesize that multiple universes could exist, each potentially infinite in its own right, leading to the intriguing idea of a multiverse. This tantalizing possibility suggests that there could be countless other realities, each with its own version of events unfolding. The idea reinforces the limitless nature of existence, emphasizing the complexity and wonder of what is around us. Finally, the concept of infinity has deep implications in the field of mathematics, particularly in relation to physical phenomena. Scientific models often rely on the idea of infinitely small points in space and time, helping us make sense of complex issues like the behavior of subatomic particles or the enigmatic nature of black holes. While these concepts may seem abstract, they fuel our sense of wonder about the universe, reminding us that while we have made extraordinary advances in understanding, the cosmos remains a vast, enigmatic realm that beckons us to explore further. In recent decades, advancements in technology have dramatically transformed our ability to explore space. A pivotal development in this transformation has been the evolution of rocket technology. Early space missions relied on basic rocket designs with limited payload capacities, restricting the scope of exploration. However, today's rockets, built with advanced materials and cutting-edge engineering, are capable of carrying larger and more sophisticated spacecraft into orbit and beyond. This evolution has enabled us to send more complex scientific instruments into space, expanding our ability to study distant planets, moons, and other celestial bodies. Another significant advancement has been in communication technology. Initially, our ability to send signals into space was limited by significant delays and interference. The advent of improvements in radio frequency technology and satellite communications has revolutionized space exploration. Today, we can transmit data from distant spacecraft back to Earth with unprecedented clarity and speed. This breakthrough has not only enhanced our ability to gather valuable scientific data, but it has also enabled real-time communication with missions, allowing scientists to make swift decisions based on the information coming in from far-off space probes. Through these technological advancements, our understanding of the universe has grown exponentially. Each step forward in rocket and communication technology brings us closer to unraveling the mysteries of space, opening new frontiers of exploration that once seemed beyond our reach. With each new discovery, we are reminded that while the universe remains an endless source of wonder and awe, it is our drive for knowledge and our pursuit of understanding that fuels our journey into the unknown. Our tools for observing the universe have undergone a revolutionary transformation. Once confined to the limitations of optical lenses, telescopes have evolved into sophisticated instruments utilizing cutting-edge digital sensors and adaptive optics. These advancements have unlocked the ability to peer deeper into space than ever before. Telescopes like the Hubble Space Telescope and the more recent James Webb Space Telescope have expanded our observational capabilities, allowing us to study the cosmos through a variety of wavelengths. This provides us with a multidimensional understanding of the universe, from the birth and death of stars to the intricate composition of distant exoplanets. These technological marvels are unveiling secrets about the universe that were once out of reach, offering us unprecedented insights into the very fabric of existence. In the early days of space exploration, telescopes relied primarily on optical lenses that captured visible light. However, this limitation constrained our understanding of the cosmos. With the advent of advanced digital sensors, these instruments are now capable of capturing a wider range of electromagnetic radiation, such as infrared and ultraviolet light, which provides a more comprehensive view of the universe. The Hubble Space Telescope, launched in 1990, was one of the first instruments to revolutionize our understanding of space. Its optical and ultraviolet capabilities allowed it to capture stunning images and collect crucial data that helped reveal the vastness and complexity of the cosmos. It provided new insights into the formation of galaxies, the life cycle of stars, and the accelerating expansion of the universe. However, the true game changer came with the launch of the James Webb Space Telescope, JWST, in December 2021. Designed to observe infrared light, JWST can peer through cosmic dust and gas, revealing distant objects that are either too cold or too faint for Hubble's optical sensors to detect. This breakthrough allows us to study the earliest galaxies formed after the Big Bang, providing vital information about the conditions and processes in the early universe. JWST's capabilities extend beyond simply observing galaxies. It plays an essential role in the study of exoplanets. Its ability to analyze the atmospheres of these distant worlds increases the likelihood of identifying potentially habitable planets, furthering our quest to answer the age-old question, are we alone in the universe? The data provided by JWST is enabling astronomers to refine their models of cosmic evolution, offering new insights into how the universe has developed over time. With its unparalleled precision, JWST is helping scientists better understand the formation of galaxies, stars, and planetary systems. This level of detailed observation is shifting our understanding of the cosmos in profound ways, pushing the boundaries of knowledge and challenging long-held perceptions about the nature of space and time. Moreover, these telescopes are not just tools for capturing breathtaking images. They are essential for advancing our understanding of fundamental cosmic processes. The implications of discoveries made by instruments like Hubble and JWST extend far beyond academic curiosity. Every breakthrough offers answers to deep philosophical questions about the origins of the universe, the nature of existence, and our place in the cosmos. Yet, with each new discovery, more questions arise, fueling our desire to explore further and unravel the mysteries of the universe. At the same time, the rise of robotic missions has transformed the way we explore distant planets and moons. These remarkable spacecraft, equipped with state-of-the-art instruments and technologies, venture into space to explore environments that are often inhospitable to human life. Robotic missions have become our eyes and ears on distant worlds, gathering invaluable data that helps us piece together the mysteries of our solar system and beyond. Whether it's imaging the surfaces of distant moons, analyzing the atmospheres of exoplanets, or studying the geology of Mars, robotic spacecraft are offering insights that no telescope could provide. One of the standout features of robotic missions is their ability to operate in extreme environments. For instance, the rovers on Mars have provided crucial information about the Martian surface, analyzing soil and rock samples for evidence of past water and determining whether conditions were ever suitable for life. Similarly, the Cassini spacecraft, which explored Saturn and its moons, uncovered extraordinary details about their atmospheres, rings, and potential habitability. These discoveries have dramatically expanded our understanding of these celestial bodies, revealing intricate details about their geological processes, atmospheric conditions, and potential for life. What makes robotic missions even more remarkable is their longevity. Spacecraft like Voyager, which were launched decades ago, continue to send back valuable information from the outer reaches of our solar system. This long-term data collection allows scientists to track changes over extended periods, providing a more dynamic understanding of planetary evolution and the broader workings of our solar system. The continued success of these missions highlights the power of autonomous exploration, pushing the boundaries of what we can learn about distant planets, moons, and even the farthest corners of space. These robotic missions do more than just expand our knowledge of distant worlds. They ignite our curiosity about the universe. Each new discovery serves as a catalyst for further exploration, raising new questions about life beyond Earth, the formation of our solar system, and the potential for future human exploration. As we continue to explore space with robotic pioneers, we move closer to understanding our place in the cosmos and the broader implications of our existence. Looking toward the future, several groundbreaking technologies are poised to revolutionize space exploration even further. A significant development is the creation of much more powerful rockets, such as NASA's Space Launch System, SLS, which represents a giant leap in space exploration capabilities. The SLS will be capable of sending heavier payloads into deep space, paving the way for missions that could take astronauts to Mars and beyond. These rockets will play a crucial role in expanding humanity's reach into the cosmos, allowing us to explore new frontiers and make unprecedented discoveries. Another area of innovation lies in the realm of robotics. While robotic spacecraft have already provided us with invaluable knowledge, advancements in artificial intelligence are set to take missions to new heights. Imagine rovers that can autonomously navigate rugged terrains on distant planets, or drones capable of exploring the atmospheres of gas giants. These advanced robots will work tirelessly in environments that are too hostile for humans, collecting data from places like Titan, Saturn's moon, or the gas giants of our solar system. Their autonomy and durability will unlock secrets that were once beyond our reach, enabling us to explore and understand these alien worlds in ways that were previously unimaginable. In essence, the combination of advanced telescopes, robotic missions, and powerful rockets is ushering in a new era of space exploration. These technologies are expanding the horizons of human knowledge, unlocking mysteries that were once beyond comprehension. As we continue to push the boundaries of space exploration, the possibilities for discovery are limitless. The universe, once a distant and enigmatic realm, is now becoming increasingly accessible, sparking the curiosity of future generations and driving humanity to explore the cosmos like never before. With each technological breakthrough, we move closer to unraveling the deepest secrets of the universe and our place within it. Humanity is standing at the cusp of an exciting era in space exploration, where technological advancements promise to dramatically alter our approach to traversing the cosmos. Among the most groundbreaking developments on the horizon are solar sails and ion propulsion systems, innovations poised to significantly cut travel times across vast distances in space. Solar sails function by harnessing the energy of sunlight, utilizing radiation pressure to propel spacecraft forward. When combined with electric propulsion systems, these sails can potentially reach extraordinary speeds, far beyond the capabilities of traditional rocket engines. This technology holds immense promise, particularly for interstellar missions. Imagine for a moment the possibility of reaching the closest star systems within a human lifetime. Something that once seemed impossible now appears within the realm of possibility. With solar sails, space travel may become as efficient as it is visionary. At the same time, we're witnessing rapid progress in communication technology, a vital component of successful deep space exploration. Current methods of data transmission are limited by the sheer distances involved in space travel, causing significant delays in communication with spacecraft on distant missions. However, recent breakthroughs, possibly inspired by advances in optical technology, could usher in new methods that allow for faster and more reliable data exchange. Such innovations could bring the vast expanse of space closer to our fingertips, enabling scientists on Earth to receive data from far-off planets, moons, and other celestial bodies nearly in real time. This will be transformative not just for exploration, but for the speed at which we acquire knowledge about the universe. But perhaps the most exciting developments lie in the realm of artificial intelligence, which has already begun to revolutionize cosmology. The universe is a treasure trove of complex data, from the subtle fluctuations in cosmic microwave background radiation to the intricate patterns of galaxy formation. Traditional methods of analyzing such data often falter when faced with its sheer volume and complexity. This is where AI comes in, using sophisticated algorithms and machine learning techniques to identify patterns and correlations that would otherwise remain hidden. AI has already proven invaluable in the classification of astronomical objects. In the vast and ever-expanding surveys of the night sky, AI systems can rapidly and accurately differentiate between stars, galaxies, quasars, and other celestial bodies. Trained on massive data sets, these AI models are able to detect subtle differences in images that would be nearly impossible for human analysts to perceive. As a result, research speeds up and the quality of findings improves, like unlocking new insights into the universe's structure. But the potential of AI doesn't end with classification. It plays a crucial role in data simulation and prediction, allowing scientists to model cosmic phenomena like galaxy formation and the behavior of dark matter. These simulations, grounded in existing data and theories, provide a means of visualizing scenarios that are beyond our observational reach. For example, AI can predict how light from distant galaxies is influenced by gravity as it travels through space-time, a phenomenon known as gravitational lensing. These predictions are invaluable in testing theories of relativity and refining our understanding of fundamental astrophysical processes. As the collaboration between artificial intelligence and human researchers deepens, AI is not merely enhancing our analytical capabilities. It is enabling the discovery of entirely new phenomena. AI tools are increasingly adept at flagging unusual events and anomalies in the data, pointing researchers to areas that warrant further investigation. With the exponential growth of data from telescopes and space missions, the partnership between AI and human insight will only become more vital, driving forward an era of profound discoveries that may completely reshape our understanding of the cosmos. One of the most exciting aspects of AI's role in cosmology is how it opens up entirely new frontiers for exploration. By pushing the boundaries of what we know about the universe, AI doesn't just enhance our current capabilities, it leads us into the unknown, propelling us to ask deeper and more profound questions about the nature of reality itself. Astrophysics as a discipline is a vast and thrilling field, filled with mysteries that continue to captivate both scientists and enthusiasts alike. Among the most profound unanswered questions are those surrounding dark matter and dark energy. Dark matter is believed to constitute about 25% of the universe, but its true nature remains elusive. While we can detect its presence through its gravitational effects on visible matter, we have yet to directly observe it. What could this mysterious substance be? Several theories have been proposed, ranging from exotic particles to entirely unknown forms of matter, yet none have been conclusively proven. Similarly, dark energy, an enigmatic force thought to make up about 70% of the universe, remains one of the most perplexing mysteries in modern cosmology. This elusive force is responsible for the accelerated expansion of the universe, but its origin and properties are still not understood. What exactly is causing galaxies to move away from one another at an ever-increasing rate? Some scientists speculate that dark energy might be a fundamental property of space itself, while others suggest it could be indicative of new physics beyond our current understanding. In addition to dark matter and dark energy, the enigma of black holes presents one of the greatest challenges in modern astrophysics. While we have a solid grasp of their existence and the profound effects they have on nearby matter, much remains unknown about what happens beyond their event horizons. Are singularities points of infinite density real, or do they signal a breakdown in our current understanding of physics? Unraveling the true nature of black holes could lead to revolutionary breakthroughs in our comprehension of space, time, and the fundamental structure of the universe itself. As humanity continues to make progress in technology and understanding, the mysteries of the cosmos seem ever more tantalizing. With solar sails and ion propulsion paving the way for faster space travel, AI unlocking deeper insights into the fabric of the universe, and new technologies facilitating real-time communication with spacecraft on distant missions, we stand on the brink of a new era in space exploration. The questions we have yet to answer may soon become the discoveries that define the next great leap in our quest to understand the universe. The search for extraterrestrial life is a captivating endeavor, one that continuously challenges our understanding of the cosmos. But as we look out across the vast expanse of our galaxy, we must ask, have we truly found every potential habitat where life could exist, or are there countless worlds teeming with life that remain just beyond our reach? Even as we send missions to distant planets and moons like the fascinating subsurface oceans of Europa and Enceladus, the answer to this profound question remains tantalizingly out of reach. The quest to uncover whether we are alone in the universe is far from over. It drives the relentless exploration of distant worlds, sparking vigorous debate and pushing the boundaries of astrophysical research. With every new discovery, we inch closer to understanding whether life exists elsewhere. But the vastness of space still leaves us wondering just how many hidden realms lie beyond our current capabilities. At the same time, the mystery of dark matter looms large over the universe, compelling scientists to seek answers about the very nature of reality itself. Dark matter is one of the most elusive and intriguing phenomena in modern physics. Although it makes up around 27% of the universe's total mass, it remains entirely invisible to current technologies. Unlike ordinary matter, which we can observe with telescopes or detect through various means, dark matter cannot be directly seen or measured. Its existence is only inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters. The first clues to the existence of dark matter came in the early 20th century. Astronomers noticed that galaxies were rotating at speeds so high that they should have been torn apart by centrifugal force. Yet, they held together. The problem was simple. There wasn't enough visible matter, stars, gas, and dust in these galaxies to account for the necessary gravitational pull to prevent them from flying apart. This led scientists to propose the existence of some form of unseen mass, which we now call dark matter. It's as though there's an invisible scaffolding, quietly maintaining the structure of the universe, while remaining completely undetected by our eyes. Over the decades, scientists have proposed various candidates for what dark matter could be, with the most prominent theory focusing on a class of particles known as weakly interacting massive particles, or WIMPs. These particles would interact with regular matter extremely weakly, making them very difficult to detect. Despite this, experiments are ongoing, from deep underground laboratories to high-energy particle accelerators, all in search of a glimpse of these elusive particles. Yet, the true nature of dark matter remains a profound mystery. Understanding it is crucial not only for comprehending the composition of the universe, but also for understanding its evolution. Dark matter plays a pivotal role in the formation of galaxies and the overall architecture of the cosmic web. Though we can't see it, its presence is strongly felt, influencing the motion of galaxies and clusters across vast cosmic distances. Dark matter is the silent architect behind the universe's grand design, shaping its structure while remaining an ever-present enigma. It continues to captivate scientists and stargazers alike, sparking a never-ending quest for discovery. Time travel, another concept that has captured human imagination for centuries, presents similarly mind-bending possibilities. It has long been a staple of science fiction, but it also raises profound questions within the domain of physics. At its heart, time travel challenges our understanding of time itself. We tend to think of time as an unbroken, flowing river moving steadily forward. However, in physics, time is often treated as another dimension, much like space. This leads to fascinating theories that suggest it might be possible to move through time just as we move through space. One of the most influential theories regarding time travel comes from Albert Einstein's groundbreaking work on relativity. In his theory, time is not a constant, but can be affected by factors such as speed and gravity. For example, the faster an object moves, especially as it approaches the speed of light, the more time slows down for that object, compared to an observer who is at rest. This phenomenon, known as time dilation, suggests that traveling at extremely high speeds could, in theory, allow a person to experience time differently than those remaining stationary, thus enabling a form of time travel into the future. Additionally, the idea of closed time-like curves has been proposed, particularly in the context of black holes and wormholes. A closed time-like curve would allow an object to return to its own past, creating a loop in time. This brings us to one of the most famous thought experiments, the grandfather paradox. What happens if you travel back in time and accidentally prevent your grandfather from meeting your grandmother? Could such an act erase your own existence? Such paradoxes highlight the logical complexities and contradictions inherent in the concept of time travel. Despite these mind-bending possibilities, practical time travel remains firmly in the realm of theory. The immense energy required to manipulate time, coupled with the limitations imposed by our current understanding of physics, makes time travel seem more like a distant dream than a present-day reality. Nonetheless, the concept of time travel continues to fascinate and inspire. It challenges the very fabric of how we perceive the flow of time and pushes the boundaries of what we understand about the universe. The allure of time travel sparks curiosity, encouraging scientists to explore the nature of time more deeply and keeping the door open for the possibility that one day we may unlock the secrets that allow us to venture beyond the present. Black holes, some of the most enigmatic objects in the universe, present yet another profound mystery. These massive gravitational wells bend space and time to such extremes that nothing, not even light, can escape their grasp. The very nature of black holes challenges our understanding of physics, especially when it comes to the behavior of information. What happens to information that falls into a black hole? This question leads to one of the most famous paradoxes in theoretical physics, the information paradox. According to the principles of quantum mechanics, information cannot be destroyed. But if anything that falls into a black hole is lost forever, it seems to contradict this principle. The paradox remains unresolved, pushing scientists to reconsider our understanding of both gravity and quantum mechanics. Are black holes truly the final resting places of matter, or is there some deeper truth that we have yet to comprehend? These paradoxes remind us that in the vastness of space, our current knowledge is only the beginning. The mysteries of the universe continue to unfold, each discovery leading to more questions, and each answer providing a stepping stone toward a greater understanding of our place in the cosmos. However, when something material falls into a black hole, it seems as though all the information about that matter disappears, never to be recovered. Once the black hole evaporates or merges with another black hole, this information seems to be lost forever. This apparent contradiction has puzzled physicists for decades and raises fundamental questions about the very nature of the laws of physics. Some physicists propose that perhaps the information isn't truly lost, but rather is encoded or preserved in some obscure way. One popular theory suggests that this information might be stored on the event horizon, the boundary surrounding a black hole, while others speculate that it could be emitted back into the universe in the form of radiation, though how this could happen remains unclear. This paradox challenges the most basic principles of our understanding of the universe and pushes the boundaries of scientific knowledge. Another captivating paradox concerns the nature of time near a black hole. The immense gravitational forces near a black hole are so strong that they warp the very fabric of space-time, creating drastic differences in how time is experienced. For an observer falling into a black hole, time slows down dramatically compared to someone watching from a safe distance. This creates a surreal scenario where the person falling into the black hole could witness the universe evolve in a way that seems entirely disconnected from their own experience of time. From their perspective, time might appear to stand still while the outside universe continues its inexorable march forward. In a sense, the individual would exist in what might be described as a timeless bubble. This fascinating idea stretches our understanding of time and space, challenging our most basic assumptions about reality and the passage of time. The quest to understand these paradoxes has led to the development of numerous theories and hypotheses. Researchers have delved into ideas such as the holographic principle, which posits that all the information contained within a black hole might be encoded on its surface. According to this theory, the information about everything that has fallen into a black hole could potentially be reconstructed from the surface, as though the three-dimensional objects we see are actually projections of information encoded on a two-dimensional plane. Such theories underscore the vibrancy of modern scientific inquiry, where each new discovery seems to give rise to even more complex and profound questions. In fact, the more we learn, the more we realize how little we understand about the universe. The mysteries of black holes, the nature of time, and the limits of information processing represent just a fraction of the unknowns scientists are working to unravel. Each step forward uncovers a deeper layer of cosmic complexity, urging us to look even further into the vastness of space in search of answers. As we probe these mysteries, we begin to realize that the universe is far stranger and more intricate than we ever imagined. This ongoing pursuit of understanding has led scientists to contemplate even grander ideas, including the concept of the multiverse. The multiverse theory has intrigued physicists and cosmologists for decades, proposing that our universe might not be the only one in existence. Instead, it might be just one of many universes that coexist in a vast, interconnected multiverse. One prominent theory within this framework arises from quantum mechanics, specifically the idea of many worlds. According to this hypothesis, every time a quantum measurement is made, the universe splits into different branches, each representing a different possible outcome. Essentially, every possible event, no matter how improbable, occurs in some alternate universe, creating an infinite number of parallel realities. This idea suggests that there are countless versions of reality, each playing out a different scenario. Another theory supporting the multiverse comes from the concept of cosmic inflation, a rapid expansion of space that occurred just after the Big Bang. According to this theory, different regions of space might inflate at different rates. Some areas might stop inflating entirely, while others continue to expand, potentially forming separate bubble-like universes. These universes could each have distinct physical laws, making each one unique in its own way. In this multiverse, the constants and conditions that we observe in our own universe might just be one of many possible sets, among countless others. The implications of this idea are mind-boggling. It suggests that our universe might not be as special as we once thought, and that the reality we experience might be just one of infinite possibilities. The multiverse theory challenges our understanding of reality itself. If there are infinitely many universes, what does it mean for the idea of uniqueness? Can we still justify the belief that our universe is special when there might be an infinite number of others that are equally real? Moreover, The concept of the multiverse forces us to reconsider what we mean by reality. If there are so many universes, how can we ever truly understand the one we live in? These questions force us to confront the limits of human knowledge and imagination. Yet at the same time, they offer tantalizing glimpses into the boundless possibilities of existence. However, the multiverse theory also raises significant challenges for the practice of science. Traditional scientific inquiry is grounded in the collection of empirical evidence and observation, yet many aspects of the multiverse remain speculative and untestable. The inability to directly observe or measure other universes means that we may never be able to confirm their existence, leaving the multiverse as a fascinating but unverifiable idea. This discrepancy between speculation and empirical science has sparked intriguing philosophical debates about the nature of scientific inquiry itself. If we live in a multiverse, how can we ever prove the existence of other universes? These questions continue to captivate scientists, philosophers, and thinkers, driving them to explore the deepest mysteries of existence. In examining the concept of the multiverse, we find that we are not only grappling with the limits of our understanding, but also confronting the vast, unexplored frontiers of knowledge. As we continue to push the boundaries of science, we discover just how much we have yet to uncover about the nature of reality, existence, and the universe itself. Light plays an indispensable role in our understanding of the universe. It is both a tool and a medium through which we gather information about distant stars, galaxies, and other cosmic phenomena. When we observe celestial objects, we are actually looking at the light that has traveled enormous distances to reach us. This light carries essential information about the objects it has passed through, revealing details about their temperature, composition, and movement. By studying the different wavelengths of light, ranging from visible colors to infrared and ultraviolet, scientists can glean a wealth of information about the structure and evolution of the universe. Light is not just a passive tool for observation. It is fundamental to our understanding of the universe's most profound phenomena. For example, the concept of redshift helps us comprehend the expanding nature of the universe. As galaxies move away from us, their light shifts toward the red end of the spectrum. By measuring this redshift, astronomers can determine not only the speed at which a galaxy is receding, but also derive valuable insights into the history and future of the cosmos. This relationship between light and cosmic expansion is one of the cornerstones of the Big Bang Theory, revolutionizing our understanding of the universe's beginnings and evolution. Furthermore, light plays a critical role in understanding the enigmatic phenomena of dark matter and dark energy. While these forces cannot be seen directly, they influence visible matter through their gravitational pull. By studying how light from distant galaxies bends and distorts around unseen masses, scientists have been able to map the distribution of dark matter across the universe. This discovery has profound implications for our understanding of the cosmos, especially since dark matter is thought to make up a significant portion of the universe's total mass. Without light, these invisible entities would remain completely undetectable. Light is also indispensable in the field of astrophysics, bridging the gaps in our knowledge and enabling the observation of cosmic events that would otherwise remain hidden. Advanced telescopes that can detect different wavelengths of light allow us to observe phenomena such as supernovae, black hole formation, and the birth of stars. Every new discovery made possible by light brings us closer to unraveling the mysteries of the universe, whether they involve familiar objects like stars and planets, or more enigmatic phenomena like black holes and dark matter. Spectroscopy, a scientific technique that studies how light interacts with celestial objects, plays a crucial role in this process. By analyzing the spectrum of light from distant stars, planets, and galaxies, astronomers can identify the chemical composition of these objects. When light passes through a prism or spectrograph, it breaks into its constituent colors, creating a spectrum. Each element in the universe absorbs and emits light at specific wavelengths, allowing scientists to detect the presence of elements like hydrogen, helium, and heavier metals in faraway celestial bodies. These spectral patterns, which are unique to each element, serve as fingerprints that enable astronomers to identify the chemical makeup of objects billions of light years away. Through these observations, we continue to deepen our understanding of the cosmos, revealing new layers of information about the universe's origins, evolution, and composition. Light, in its various forms, is a key player in our quest to understand the universe. Its behavior holds clues to the workings of distant galaxies, stars, and cosmic phenomena that lie far beyond the reach of our immediate perception. The way light shifts, bends, and interacts with matter gives us a window into the mechanics of the cosmos, unraveling mysteries that have intrigued astronomers for centuries. When a celestial body moves towards us, the light it emits undergoes a fascinating transformation. The wavelengths of light are compressed, resulting in a shift towards the blue end of the spectrum. This shift, known as a blue shift, is an indication that the object is moving closer. On the other hand, when a celestial body moves away from us, its light stretches into longer wavelengths, causing a red shift. This is the signature of an object receding from us. These shifts in light, as described by the Doppler effect, offer valuable insights into the movement and velocity of galaxies and stars, helping us track the expansion of the universe. Spectroscopy, the technique used to analyze these shifts, acts as a cosmic fingerprint. It provides a unique view into the distant universe, allowing astronomers to study the elemental composition of stars, the dynamics of galaxies, and the vast networks of matter that fill the universe. Each spectrum, with its distinctive lines and patterns, helps us understand the origins, behaviors, and trajectories of the objects it represents. Through this method, scientists can also look into the history, present state, and potential future of the universe, fueling curiosity and shaping our ongoing search for knowledge. At its core, light is a fundamental form of electromagnetic radiation that transcends our need for sight. It carries critical information about the cosmos, from the stars and galaxies it encounters to the gases and dust it passes through on its journey. Light travels through space at an astounding speed of about 300,000 kilometers per second, 186,000 miles per second, making it possible for us to witness the distant past of the universe as if it were unfolding in real time. This speed allows us to view objects that are millions, even billions of light years away, seeing them as they were long before we were born. When light passes through a medium, such as a cloud of gas, it can interact with the elements within that medium, revealing vital information. Certain wavelengths of light are absorbed by atoms and molecules, leaving behind dark lines in the spectrum of light, a phenomenon known as absorption lines. These lines act as a fingerprint for the substances in the gas, enabling scientists to identify its composition, temperature, and motion. By studying these absorption lines, astronomers can gain a deeper understanding of celestial objects, revealing hidden aspects of the universe that would otherwise remain invisible. Moreover, light is not merely a passive observer of the cosmos, it is also influenced by the massive objects it encounters. One of the most intriguing effects is gravitational lensing, where light bends as it passes near a massive object, such as a galaxy or black hole. This bending occurs because gravity warps the fabric of space-time, altering the path of the light. Gravitational lensing allows astronomers to study distant objects that would otherwise be too faint or far away to observe directly. By analyzing the way light has been distorted, scientists can learn about the mass, structure, and even the elusive dark matter surrounding these objects. The diverse range of wavelengths of light, from radio waves to visible light and beyond, further expands our ability to study the universe. Each type of light carries its own story. For example, radio waves can reveal the presence of cosmic background radiation, the faint afterglow of the Big Bang. X-rays, with their high energy, can expose dramatic phenomena like black holes and supernovae. By studying the full spectrum of light, astronomers can gain a multifaceted understanding of cosmic events, offering clues not only about the past, but also about the future direction of the universe. The speed of light itself serves as a cosmic speed limit. At approximately 300,000 kilometers per second, or around 186,000 miles per second, this speed is fundamental not just for light, but for all forms of electromagnetic radiation. It impacts how we perceive the cosmos and affects our understanding of the vast distances between objects. Because light takes time to travel across space, when we look at distant stars and galaxies, we are essentially looking back in time. The light we see may have been emitted millions or even billions of years ago. For instance, if a star is located 10 million light years away, the light we see from it today left the star 10 million years ago. In this sense, every observation we make is a snapshot of the past, a moment frozen in time that has traveled across the cosmos to reach us. This finite speed of light also gives rise to the concept of a light year, a unit of distance that represents the distance light travels in 1 year. A light year is equivalent to about 9.46 trillion kilometers, or about 5.88 trillion miles. This unit helps astronomers grasp the immense scale of the universe, making it possible to measure the vast distances between stars, galaxies, and other celestial bodies in terms we can comprehend. The light year becomes an invaluable tool for mapping out the universe's grand structure, from individual stars to vast galaxy clusters, and even to the enormous cosmic web that connects them all. Thus, light, in all its forms, is not just a means for us to see, but a powerful tool that guides our understanding of the universe. Its speed, its interactions with matter, and its varied wavelengths provide a wealth of information that is crucial to unraveling the mysteries of space. Whether it's revealing the motion of galaxies, uncovering the hidden properties of stars, or offering a glimpse into the farthest reaches of the cosmos, light plays an indispensable role in helping us piece together the grand narrative of the universe's evolution, from its inception to its ever-changing future. The speed of light is not just a fundamental constant in the universe. It plays an essential role in shaping the very framework of our understanding of space and time. At the heart of Einstein's theory of relativity, the speed of light is central to our perception of reality. As objects approach the speed of light, they experience time differently from those at rest. This phenomenon, known as time dilation, reveals just how deeply time is intertwined with space, challenging our most basic assumptions about the nature of both. It is no longer accurate to think of space and time as fixed, unchanging entities. Instead, they are dynamic and malleable, stretching and bending in response to the movement of objects and the fabric of the universe itself. The speed of light, therefore, is not only how we observe the cosmos, but also a fundamental key to understanding the very nature of existence. In tandem with the theories of relativity, advancements in optics have transformed the field of astronomy, expanding our ability to peer deeper into the universe than ever before. The journey of discovery began in the early 17th century with the invention of the telescope, an instrument that forever changed our ability to observe the heavens. By bending light through lenses or mirrors, telescopes allowed astronomers to observe distant stars, planets, and galaxies with an unprecedented clarity. These early instruments opened up new vistas in our understanding of the universe, revealing faraway celestial objects that had been hidden from human eyes for millennia. The development of larger and more sophisticated telescopes has continued to push the boundaries of our vision. Reflective telescopes, which utilize mirrors instead of lenses, have eliminated some of the distortions that plagued earlier designs. This has allowed astronomers to capture light from fainter and more distant objects, such as galaxies that were previously invisible to early observers. These advancements have significantly expanded our understanding of cosmic structures, unveiling the vast complexity of the night sky. Yet, even as optical technology improved, the challenge of observing distant objects through Earth's turbulent atmosphere remained. That's where adaptive optics come in. This revolutionary technology compensates for the distortions caused by the atmosphere, providing astronomers with much sharper images. By adjusting the telescope's mirror in real time to correct for atmospheric interference, adaptive optics has enabled astronomers to study celestial objects with an unparalleled level of detail. With this technology, they can now investigate the surfaces of distant planets, uncover hidden features within nebulae, and study the subtle structures of galaxies, all with incredible precision. But optics is only part of the equation. The development of sensor technology has been equally transformative. The advent of charge-coupled devices, CCDs, which capture light more efficiently than traditional photographic plates, has drastically improved our ability to gather and analyze astronomical data. These sensors are much more sensitive, allowing astronomers to capture faint light from distant stars and galaxies. They have also made it possible to create detailed maps of the universe, study the composition of distant stars, and track the movements of exoplanets orbiting far-off suns. Collectively, these innovations in optics and sensor technology have propelled the field of astronomy into a new era, one where the universe is more accessible and more mysterious than ever before. Defining the age of the universe is an equally captivating pursuit. It requires the careful application of various scientific methods, blending advanced techniques with a touch of cosmic detective work. At the heart of these methods is our understanding of the expansion of the universe. One of the primary tools used to calculate the universe's age is Hubble's law, discovered by Edwin Hubble. This law states that galaxies are receding from us at speeds proportional to their distance. By measuring the distances and speeds of galaxies, scientists can determine the rate of expansion, known as the Hubble constant. This leads to the estimate that the universe is approximately 13.8 billion years old, dating back to the moment of the Big Bang, the cataclysmic event that gave birth to everything we know. Another critical piece of the cosmic puzzle comes from studying the cosmic microwave background, CMB radiation, a remnant from the Big Bang. This radiation, which fills the entire universe, offers a glimpse into the universe's infancy when it was only about 300,000 years old. By carefully analyzing fluctuations in the temperature of the CMB, scientists can infer the conditions that existed at that time, refining our estimates of the universe's age. Satellites such as the European Space Agency's Planck satellite have provided invaluable data, allowing scientists to map the cosmic background with remarkable precision. Astronomers also turn to the oldest stars in the galaxy for clues about the universe's age. These ancient stars, particularly those in globular clusters, have been around almost as long as the universe itself. By measuring the rate at which these stars burn their nuclear fuel, scientists can estimate their age and create a cosmic clock that aligns with the age derived from other methods. Together, these different techniques form a coherent picture, not only providing an estimate of the universe's age, but also offering insights into the processes that have shaped it over time. The concept of an expanding universe has far-reaching implications for our understanding of time itself. As galaxies move away from us, we are witnessing an ongoing expansion that began with the Big Bang. This expansion reveals a universe in constant flux, where time is not a fixed, unchanging measure, but a dynamic component that evolves alongside space. The farther we look into space, the deeper we peer into the past. Light from distant galaxies takes billions of years to reach us, so when we observe them, we are seeing them as they were when that light was first emitted. This temporal connection allows us to trace the universe's history, revealing its evolution over vast spans of time. Moreover, this expansion challenges the way we perceive the flow of time. Regions of space with stronger gravitational fields, such as those near black holes, experience time more slowly than regions with weaker gravity. This concept, which is rooted in Einstein's theory of general relativity, teaches us that time is not uniform across the universe. Instead, it is shaped by the gravitational forces at play, stretching and compressing in response to the underlying structure of spacetime. The expanding universe also forces us to rethink time itself. It is no longer just a backdrop against which events unfold. Instead, it becomes an integral, malleable part of the cosmic narrative. Every moment, every event in the universe is linked to the flow of time, which is forever intertwined with the very fabric of space. As we study the cosmos, we come to appreciate the interconnectedness of time and space, recognizing that our perception of time on Earth is just one small piece of a much larger, ever-evolving story. The vast timescales of the universe are almost incomprehensible when compared to the brevity of human life. The universe, at 13.88 billion years old, has undergone countless changes. Galaxies have formed, stars have lived and died, and planets have emerged. In contrast, the span of a human life is but a fleeting moment in the grand scheme of things. This disparity in time perception invites us to reflect on our place in the universe and the legacy we leave behind. Though we tend to measure time in smaller units, seconds, minutes, days, and years, the long timescales of the universe offer a unique perspective. Evolution, for example, occurs over millions of years, and major shifts in the natural world take place on similarly vast timescales. This understanding can instill a sense of patience, reminding us that meaningful change often requires time and persistence. It also encourages us to appreciate the gradual growth that unfolds in nature, as well as in our own lives. Moreover, our perception of cosmic time has a profound influence on the technologies that shape the very fabric of our daily existence. For example, satellites, those marvels of modern engineering, rely on precise timing systems to navigate and communicate effectively. The delicate dance of these machines in orbit is influenced by intricate calculations that consider the effects of time dilation, a phenomenon predicted by Albert Einstein's theory of relativity. According to this theory, time itself behaves differently depending on the strength of gravitational fields. Near massive objects like black holes or neutron stars, time passes more slowly compared to regions with weaker gravitational forces, such as Earth. This subtle yet profound scientific insight, grounded in our understanding of the cosmos, has become the cornerstone of technologies we rely on every day, even if we rarely acknowledge the cosmic roots of these innovations. When we connect these scientific revelations to the smaller moments in our lives, a sense of awe and wonder emerges. Events like birthdays and anniversaries, simple markers of the years we've lived, are transformed when we place them within the larger narrative of the universe. These milestones, rather than being mere ticks on the clock, become markers in a grand, ongoing story that stretches across time and space. By embracing this cosmic perspective, we can cultivate a deeper appreciation for our own lives, recognizing that even the smallest of moments is part of an ever-unfolding cosmic saga. Time, far from being a static measure, is instead an active force, intricately intertwined with the unfolding of the universe itself. One of the most captivating ways in which cosmic events shape our understanding of time is through the phenomenon of gravitational time dilation. Einstein's theory reveals that time itself bends and stretches depending on the strength of gravity in a given region. In areas of intense gravitational pull, like near a black hole, time literally slows down. So a clock positioned near such a massive object would tick at a different rate compared to one placed far from it, such as on Earth. This revelation shows that time is not a fixed backdrop to events, but is instead a malleable force, subject to the immense forces of the universe. This fundamental understanding reshapes how we think about our own lives and the passage of time. Another profound factor in our understanding of cosmic time is the expansion of the universe itself. As galaxies move farther away from each other, the very fabric of space-time stretches, altering our perception of distances and time. One of the key indicators of this cosmic stretching is the redshift, a shift in the light emitted by distant galaxies. As these galaxies move away from us, their light lengthens, shifting toward the red end of the spectrum. This not only reveals the ongoing evolution of the universe, but also offers a glimpse into its distant past. As we observe light that has traveled across billions of years to reach us, we are essentially looking back in time, uncovering insights into the universe's age and its dynamic evolution. Cosmic events also mark the great epochs that define the universe. From the formation of stars to the birth of galaxies, each moment in the universe's history creates ripples that extend throughout time, affecting everything in their path. These cataclysmic events can lead to the creation of new elements, shaping the physical structure of the cosmos, and even influencing the formation of solar systems, including our own. Understanding these milestones allows us to trace the timeline of the universe, from the fiery explosion of the Big Bang to the ongoing processes of star formation and galaxy evolution. Intriguingly, certain cosmic events hold the potential to redefine our perception and measurement of time. Events like solar eclipses or the regular cycles of pulsars, rapidly rotating neutron stars that emit beams of radiation, offer us incredibly precise clocks to measure the passage of time. These cosmic clocks allow astronomers to test the very fabric of space-time itself. By studying such phenomena, scientists are peeling back layers of complexity in our understanding of time, revealing that it is not just a human construct, but something that is intricately connected to the universe's grand narrative. Each cosmic event offers a new layer of depth, reinforcing the idea that the universe is not a passive backdrop, but an ever-active force unfolding across time. However, measuring cosmic time presents unique challenges, many of which are inherent to the vastness and complexity of the universe itself. The sheer scale of space is one such challenge. Distances between celestial objects are so vast that the light emitted by these objects can take billions of years to reach us. This creates a time delay in our observations, meaning that when we look at distant stars or galaxies, we are seeing them as they were in the distant past, not as they are in the present moment. This time lag complicates our understanding of cosmic events, as we must always account for the travel time of light when interpreting what we observe. Further complicating matters is the expansion of the universe. Since the Big Bang, the cosmos has been stretching, and this stretching affects not just the distances between objects, but also how we measure time. Objects that are receding from us due to this expansion appear to move more quickly, altering how we perceive time and space on a cosmic scale. The rate at which the universe expands is still a subject of intense study, and this uncertainty introduces a level of complexity when attempting to measure and establish a precise cosmic timeline. Additionally, the nature of many cosmic events adds another layer of complexity. Phenomena like supernovae or gamma-ray bursts release vast amounts of energy over varying timescales. From our perspective, these events might appear brief, but they can have a profound impact on our understanding of the universe. Pinpointing their exact age or determining how long ago they occurred requires incredibly precise measurements and an understanding of their inherent variability. Einstein's theory of general relativity adds yet another layer to the complexity of cosmic time. Gravity, it turns out, plays a fundamental role in how time behaves. The stronger the gravitational field, the more slowly time moves. This means that time is not a universal constant. It is a variable dependent on where you are in the universe and how much mass is around you. The interplay between gravity and time is yet another reminder that our understanding of time is far from simple. All these factors, vast distances, the expanding universe, gravitational effects, and the dynamic nature of cosmic events, combine to make the measurement of cosmic time a deeply intricate challenge. As we strive to understand the history of the universe, we are faced with a complex web of forces and phenomena that shape our perception of time itself. Humanity's relationship with the night sky has evolved dramatically over the centuries. In ancient times, our ancestors looked to the stars for guidance. The night sky was their map for navigation, their clock for agricultural practices, and their guide for the changing of seasons. Celestial bodies were not just distant lights in the sky. They were powerful symbols, often associated with deities and myths, weaving rich stories that connected humans to the cosmos. As civilizations advanced, so did our understanding of the universe. The ancient Greeks, for example, began to document the movements of stars and planets, establishing the foundation for the field of astronomy. They recognized patterns in the heavens and developed models to explain these celestial movements. This intellectual curiosity gave birth to a host of profound philosophical and scientific inquiries that have shaped the course of history. The invention of the telescope in the 17th century marked a monumental shift in how we perceive the universe. Astronomers like Galileo Galilei used this new tool to peer beyond the limits of the naked eye, revealing worlds previously unseen. Moons orbiting Jupiter, the phases of Venus, and the vastness of space itself challenged long-held beliefs about Earth's place in the cosmos. The night sky, once a realm of myth and mystery, became an object of scientific inquiry and exploration. In the modern age, technological advancements have propelled our exploration of the cosmos even further. Satellites, space probes, and advanced telescopes have allowed us to peer deeper into the universe, capturing stunning images of distant galaxies, and even detecting planets orbiting stars beyond our solar system. As we continue to unlock the mysteries of the cosmos, our connection to the night sky deepens, and our understanding of time, both cosmic and personal, expands with each discovery. The night sky has always been a source of profound inspiration, evoking feelings of wonder, humility, and an ever-deepening sense of curiosity about the universe we inhabit. With each passing day, as our understanding of the cosmos grows, we come to recognize not only the vastness of the universe, but also the fragile and significant role we play within it. This awareness fosters a collective responsibility, an obligation to safeguard the future of our planet and its place in the broader universe. Throughout history, the stars and the infinite expanse of space have sparked the imaginations of countless artists, musicians, and writers. From the ancient civilizations to the present day, the celestial sphere has served as both muse and metaphor, influencing a wide array of creative expression. The stars themselves, with their radiant glow, embody beauty and mystery, offering an endless wellspring of inspiration to those who look up at them. The night sky in all its grandeur has not only been a canvas for painters and poets, but also a source of light and wonder for musicians who strive to capture its essence in melody. In literature, celestial bodies often transcend their literal meanings to symbolize profound and deeply human themes. The stars, the moon, and distant galaxies represent hope, the unknown, and the search for deeper meaning. Romantic poets, for example, often turn to the night sky to voice their feelings of longing, existential reflection, and yearning. Their verses captured the timeless human desire to transcend earthly limitations and connect with something greater, something beyond the ordinary scope of our daily lives. The stars were not just distant points of light, but beacons that guided the soul, representing both a destination and a dream. Books that explore space exploration and imaginary worlds allow readers to break free from the constraints of their own experiences, offering a glimpse into worlds where anything is possible. Through these stories, we are encouraged to imagine a future where the boundaries of space and time are no longer limitations, but invitations to explore the vast unknown. Similarly, music draws upon the cosmic imagery of stars, galaxies, and the infinite reaches of space to craft symphonies and songs that speak to the grandeur and beauty of the universe. Composers have long been inspired by the vastness of the cosmos, creating soundscapes that evoke the awe and wonder associated with the mysteries of the night sky. These haunting melodies invite listeners to lose themselves in the music, creating a connection between the listener and the vast, uncharted territories beyond our planet. Popular songs that reference celestial themes often touch upon universal human experiences, love, loss, yearning for the unattainable, and find resonance in the hearts of listeners who identify with these emotions, transcending time and space. Visual artists, from painters to sculptors, have also been deeply influenced by the cosmos, using celestial imagery to capture the ethereal beauty of the night sky. One need only look at the works of Vincent van Gogh, whose swirling skies seem to come alive with energy and movement, to see how the night sky becomes more than just a backdrop. For artists like Van Gogh, stars are not mere representations, but meditations on the nature of reality itself. These works challenge us to see the universe not as a distant, cold void, but as a vibrant, living entity, a reflection of our own inner thoughts, emotions, and desires. In the intersection of art and the cosmos, we find a profound connection, a timeless link between our shared curiosity and the awe-inspiring mystery of the universe. The role of mythology and folklore in shaping humanity's understanding of the universe is equally significant. Across cultures and centuries, people have looked to the stars, the moon, and the sun as a source of inspiration, crafting stories that help explain the movements of celestial bodies and the mysteries of the natural world. These stories, passed down through generations, provided frameworks for understanding life's most profound questions. Questions about creation, existence, and our place in the grand scheme of things. In the ancient world, civilizations such as the Greeks and Egyptians created intricate myths to explain celestial phenomena, personifying natural forces as gods and goddesses. The Greek god Helios, for example, was said to drive the sun across the sky in his chariot, while the Egyptians revered Ra, the sun god, who battled the darkness each night. These myths were not simply attempts to explain the natural world, but also reflections of humanity's deep curiosity about the cosmos. Through storytelling, these ancient cultures transformed the night sky into a canvas for human imagination, allowing them to grapple with existential questions and to share collective truths. These stories reflected the values of their societies, often illustrating themes of balance, order, and harmony. Creation myths, for instance, frequently portrayed the emergence of the universe from chaos or darkness, mirroring the human longing for stability and understanding in a seemingly unpredictable world. More than just entertainment, these myths were vehicles for moral lessons, shaping worldviews and offering a sense of unity through the shared experience of exploring the unknown. In modern times, while our scientific understanding of the universe has expanded exponentially, the essence of these ancient narratives remains as powerful as ever. Many contemporary scientists and philosophers still draw upon the wisdom embedded in these myths to communicate complex ideas about the universe. They remind us that while we may seek knowledge through data and observation, the human experience of wonder and curiosity is universal. The myths of old are not simply relics of a bygone era. They are reflections of our ongoing quest to comprehend the vast, enigmatic cosmos in which we live. Contemplating the cosmos can have a profound psychological impact on individuals. For many, gazing at the stars or considering the enormity of the universe stirs a sense of awe and wonder, an emotion that transcends simple curiosity. This feeling often evolves into a deep appreciation for the beauty and intricacy of existence itself. In these moments of reflection, we are reminded that we are not isolated beings, but part of something far greater, a universe so vast that its mysteries are beyond our comprehension. Such realizations have the power to expand our sense of self, prompting us to reconsider our place in the world and our responsibility to one another and to the planet we call home. The night sky, with its endless sea of stars and celestial wonders, continues to captivate the human imagination, shaping our culture, our art, and our understanding of the universe in ways both ancient and modern. As we continue to explore the cosmos, we find that the more we learn, the deeper our curiosity grows, a reminder that the journey to understand the universe is one that will never truly end. Contemplating the vastness of the cosmos can evoke a profound sense of humility. When we pause to consider the unfathomable scale of the universe, with its billions of galaxies, each teeming with countless stars, our personal troubles can seem insignificant in comparison. This humbling realization offers us a perspective that stretches far beyond our individual experiences. It reveals the fleeting nature of our concerns in the context of the boundless expanse around us. In these moments, we often feel a heightened sense of connection with others, an understanding that we are not isolated but share this extraordinary world, and even this cosmic journey with countless others. Such realizations can foster compassion, not just for ourselves, but for one another and for the planet that sustains us. The cosmos, in its vastness, becomes a mirror reflecting our shared humanity. Moreover, the act of exploring cosmic phenomena often sparks deep existential reflection. Many are driven to ponder their place in the universe and the true significance of life itself. This search for meaning can lead to profound shifts in how we perceive the world and our daily existence. It encourages a renewed appreciation for the small, ordinary moments that make up our lives, reminding us of their inherent beauty and value. In some cases, these reflections may lead to existential discomfort or anxiety as individuals grapple with the unknowable questions of life and the universe. Yet, paradoxically, this process can also encourage personal growth. It pushes us to dive deeper into our beliefs, values, and the essence of our being. The quest for understanding, though challenging, often leads to greater self-awareness and a clearer sense of purpose. The psychological benefits of contemplating the cosmos are also significant. Engaging with the mysteries of the universe provides a comforting escape from the stresses and challenges of everyday life. For many, stargazing or studying astronomy offers a rare moment of peace, a respite from the frenetic pace of modern existence. In these quiet moments, the mind can wander, reflecting on the majesty of the universe, reminding us of life's complexity and beauty. In this sense, the cosmos becomes more than just a field of study. It transforms into a wellspring of inspiration, a source of tranquility that nurtures our emotional well-being. The exploration of space also possesses an unparalleled power to unite humanity. Throughout history, the pursuit of space exploration has brought together people from all corners of the globe. Individuals from various countries, cultures, and backgrounds, all focused on one common goal: understanding the universe. This shared mission has a profound ability to break down societal and cultural barriers, helping us realize that despite our differences, we all inhabit the same planet and face many of the same challenges. When we gaze up at the night sky, we are reminded not only of our place within the vastness of the cosmos, but also of our collective responsibility to care for our planet and one another. In the pursuit of space exploration, collaboration is key. Projects like the International Space Station ISS stand as monumental examples of global cooperation. Scientists, engineers, and astronauts from diverse nations have worked together to create and maintain this unique laboratory in space. Their combined expertise pushes the boundaries of what we know about space, fostering a sense of collective identity as citizens of Earth. The ISS is not just a symbol of technological achievement, but a testament to the power of collaboration and shared purpose. It reminds us that when we work together, we can accomplish extraordinary things. Beyond the collaboration required for space exploration itself, the discoveries made through these endeavors have far-reaching implications for our understanding of Earth. The study of other planets, for instance, provides valuable insights into the delicate balance of our own planet's climate and ecosystems. Research into celestial phenomena, such as solar flares or asteroid impacts, often leads to a greater awareness of how interconnected our world is with the broader universe. These discoveries prompt us to reflect on our own actions and their potential consequences for the planet. They encourage a sense of responsibility that extends beyond our immediate needs, urging us to think about the well-being of future generations as we confront challenges like climate change and resource depletion. Looking further into the cosmos, the possibilities seem endless. As we venture deeper into space, whether in the hope of discovering life on other planets or unraveling the mysteries of dark matter, we begin to foster a shared sense of wonder that transcends borders and cultural divides. These aspirations are not confined to any one nation or group. They unite people from all walks of life, inspiring a global sense of curiosity and hope. The desire to explore and understand the cosmos serves as a powerful reminder that, despite our differences, we are all united in this incredible journey through time and space, bound by the same curiosity and desire to uncover the secrets of the universe. Yet, as we venture further into space, astronomers are confronted with an array of formidable challenges. One of the most pressing obstacles is the sheer scale of the universe itself. Space is unfathomably vast, filled with billions of galaxies, each containing billions of stars. This immense expanse makes it difficult to study distant objects, even with the most advanced technology. Observing far-off celestial bodies can be likened to trying to spot a single grain of sand on an endless beach. The scale is so vast that it becomes a challenge to comprehend, let alone explore. Another significant hurdle lies in the nature of light itself. Light travels at a finite speed, meaning that the further away a celestial object is, the longer it takes for its light to reach us. This time delay creates a unique challenge for astronomers, as they are forced to study distant objects as they appeared in the past, not as they exist in the present moment. This time lag can distort our understanding of the current state of the universe, making it difficult to track the evolution of galaxies, stars, and other celestial phenomena. The study of distant objects, therefore, often involves interpreting light that is billions of years old, complicating our understanding of the cosmos's current state. In addition to these challenges, astronomical observations are also affected by the Earth's atmosphere. Light pollution and atmospheric turbulence can significantly distort the data collected from ground-based telescopes, making it harder to capture clear, accurate images. These factors can obscure our view of the cosmos, limiting our ability to study distant stars, galaxies, and other phenomena. In response, astronomers have turned to space-based telescopes, such as the Hubble Space Telescope and the more recent James Webb Space Telescope. These instruments, positioned beyond Earth's atmosphere, offer a clearer view of the universe. However, building and maintaining these sophisticated tools require immense resources and technological expertise, highlighting the challenges inherent in space exploration. Despite these obstacles, the pursuit of knowledge continues as humanity pushes the boundaries of what is possible, striving to understand the mysteries of the cosmos. The challenges are immense, but so are the rewards. both in terms of the discoveries we make and the unity we experience as we embark on this shared journey. The cosmos holds countless secrets that continue to challenge our understanding, pushing the limits of our knowledge and existing theories. Phenomena such as dark matter and dark energy remain largely mysterious. These two elusive forces are believed to make up the majority of the universe's content, yet they remain exceedingly difficult to detect and study. Despite advancements in technology and the refinement of our theories, the more we learn, the more questions arise. As the tools available to astronomers continue to evolve, so too do the challenges, constantly demanding that scientists adapt, innovate, and reconsider their methods. The pursuit of understanding our vast universe is an endeavor that shows no sign of slowing down. Rather, it intensifies with each new discovery. At the heart of this exploration, however, lies a fundamental issue: the availability of funding and resources. These factors significantly shape the direction and potential of astrophysics research. The resources available to research teams determine not only which projects they can pursue, but also the scope and scale of their investigations. With limited budgets, scientists are often forced to prioritize certain areas of research, gravitating toward inquiries that promise quick, tangible results or align with the specific interests of funding bodies. Public institutions and private organizations are the primary sources of financial support, and they often guide researchers toward areas that not only advance scientific knowledge but also capture public attention or address pressing societal issues. For instance, studies exploring the connections between climate change and cosmic phenomena tend to receive significant funding due to their direct relevance to contemporary concerns. On the other hand, investigations into the fundamental nature of dark matter, while central to our understanding of the universe, might struggle to secure resources. Despite the theoretical importance of such inquiries, their abstract nature makes them harder to justify from a financial standpoint. The cutting-edge technology required for groundbreaking discoveries, such as advanced telescopes or particle accelerators, also plays a crucial role in shaping the research landscape. A well-funded laboratory, for example, may have the resources to explore high-energy astrophysics, probing the mysteries of black holes or supernovae. Meanwhile, teams with fewer resources may focus on niche investigations, often with limited capacity to scale their work. This imbalance in funding can create uneven progress across the field of astrophysics. The relentless pursuit of knowledge is often constrained by financial limitations. In this intricate balance between ambition and available resources, the direction of research evolves, revealing just how inextricably linked economics and exploration truly are. As much as the search for answers is driven by scientific curiosity, it is equally shaped by the practicalities of securing funding. Political factors, too, play a significant role in determining the course of international space exploration. Space exploration has long been viewed as a reflection of a nation's technological prowess and global standing. National priorities influence which projects receive funding and the extent of international collaboration. This competition between countries can foster partnerships, but it can also create barriers, especially when space achievements are seen as integral to national prestige. For instance, countries with competitive national agendas may hesitate to share valuable resources or knowledge with others, fearing that it could compromise their edge in the space race. Moreover, political stability, or the lack thereof, can also impact space exploration partnerships. In times of national turmoil, governments might shift their focus to domestic issues, putting international collaborations on hold or scaling down projects. In contrast, nations with stable political systems are more likely to honor long-term commitments to international projects, fostering trust and cooperation over time. The International Space Station, ISS, serves as a prime example of how cooperation in space exploration can endure despite shifting political climates. This ongoing collaboration between multiple nations demonstrates the recognition of the mutual benefits that arise from shared exploration and resources. Beyond government entities, the rise of commercial space activities introduces a new dynamic to the political and scientific landscape. Private companies are now key players in space exploration, and their involvement complicates the traditional state-based structure of space missions. Governments must navigate their relationships with these private entities, ensuring that national interests are aligned with the commercial objectives of corporations. As commercial space initiatives become more prominent, they further intertwine the spheres of politics, economics, and exploration, altering the traditional boundaries of space research and development. In the realm of astrophysics, scientists often encounter paradoxes that provoke deep philosophical questions, challenging our very understanding of reality. One of the most famous of these is the Fermi paradox, which ponders the question: if the universe is so vast, with billions of stars and potentially habitable planets, why have we not yet encountered evidence of extraterrestrial life? This paradox presents an intriguing dilemma. On one hand, the sheer scale of the cosmos suggests that the existence of intelligent life should be highly probable. On the other hand, the absence of any definitive signs of such life raises questions about the rarity of intelligent civilizations or the limitations of our search methods. Another paradox that has long puzzled scientists is Olber's paradox, which questions why the night sky is dark if the universe is infinite, eternal, and filled with stars. According to the logic of the paradox, if the universe had existed forever, there would be an abundance of stars and the sky should be illuminated at all times. The resolution to this paradox lies in the understanding that the universe is finite and ever-expanding. As light from distant stars stretches over time, it redshifts beyond the visible spectrum, rendering it invisible to the naked eye. Perhaps the most captivating paradox of all is the information paradox related to black holes. When objects fall into a black hole, it seems as if all information about those objects is lost forever, a notion that contradicts the principles of quantum mechanics, which state that information cannot be destroyed. This contradiction raises profound questions about the nature of reality itself, suggesting that our current understanding of the laws of physics may need to be revisited or revised in light of new discoveries. Then there's the paradox of dark energy. The universe is expanding, and the rate of expansion is accelerating. Yet, we remain largely in the dark about the nature of the force driving this acceleration. Dark energy, which is believed to be responsible for this phenomenon, remains one of the most significant unknowns in cosmology. While scientists can measure its effects, they are still grappling with its origins and how it fits into the broader framework of cosmic forces. This paradox reflects the deep mysteries that continue to elude us, highlighting both the limitations and the boundless possibilities of our understanding of the universe. Each of these paradoxes, whether related to extraterrestrial life, the nature of light, black holes, or dark energy, serves as a reminder of the limits of our knowledge. Yet they also embody the relentless quest for understanding that defines the field of cosmology. The answers to these paradoxes may be far off, but the pursuit itself continues to drive scientific inquiry forward, opening up new avenues for exploration and discovery. The role of public perception in shaping the trajectory of scientific research cannot be overstated. When the public values and trusts scientific inquiry, it often leads to increased investment from both government and private sources. This financial support can propel research forward, enabling the scientific community to make significant advancements in technology, medicine, and our understanding of the universe. Conversely, skepticism or distrust in scientific findings can hinder progress by diminishing support and resources. Therefore, effective communication of scientific discoveries is essential for maintaining public trust and engagement. Scientists must find ways to communicate their findings in clear, accessible terms, bridging the gap between complex research and everyday life. When scientific concepts are explained in a manner that resonates with the public, it fosters greater understanding and interest. This, in turn, encourages people to support scientific endeavors and may inspire future generations to pursue careers in the sciences. As such, effective communication not only furthers our understanding of the cosmos, but also ensures the continued flow of talent and innovation, ensuring that the journey of discovery remains alive for years to come. The media plays a powerful role in shaping public perception, especially when it comes to scientific research. Whenever a new scientific breakthrough or study makes headlines, it has the potential to capture public attention, influence conversations, and even guide government policy. However, sensationalized reporting or the oversimplification of complex findings can often lead to confusion or misinformation. This means that scientists have a dual responsibility. Not only must they conduct thorough and rigorous research, but they must also be proactive in engaging with the public. By participating in discussions about their work and responding to public concerns, scientists can help ensure that their discoveries remain relevant, understood, and respected. This relationship between science and society is not one-sided, it's symbiotic. As the public engages with scientific topics, they influence research agendas, priorities, and funding. In turn, scientists benefit from a society that values knowledge, supports inquiry, and provides the resources necessary for scientific advancement. The exchange of ideas between researchers and the public will be key in addressing the global challenges we face today, such as climate change, health crises, and social inequality. Moreover, it will help propel us toward a future where our understanding of the universe deepens and our capacity to explore and thrive beyond Earth grows. As humanity reaches further into space, the desire to establish a lasting presence on other planets becomes increasingly urgent. The ambition to explore, understand, and eventually inhabit worlds beyond Earth reflects our innate curiosity and drive for discovery. This dream is shared by institutions like NASA, the European Space Agency, and private companies such as SpaceX, who are at the forefront of this spacefaring ambition. However, the goal is not simply to visit other celestial bodies. The long-term vision is to build sustainable, self-sufficient colonies on places like the Moon and Mars. This vision is increasingly becoming a reality through ambitious projects such as NASA's Artemis program, which aims to return humans to the Moon and establish a permanent lunar presence by the end of this decade. The Moon, often referred to as Earth's closest neighbor, serves as an ideal testing ground for these groundbreaking endeavors. By establishing a human presence there, we can develop and refine the technologies needed for longer, more distant missions, including those to Mars and beyond. One key concept driving lunar exploration is in situ resource utilization, the idea that we can use the Moon's native resources, such as water, ice, and minerals, to support human activities. This could include producing fuel, oxygen, and building materials directly from lunar resources, reducing the need to transport everything from Earth. This approach not only makes long-term lunar missions more viable, but also lays the groundwork for future exploration into the outer reaches of our solar system. Mars, often regarded as the next frontier in space exploration, holds even greater promise. While the Moon will serve as a testing ground, Mars offers the potential for humans to build permanent habitats, using the planet's resources to sustain life. Plans are already in the works for crewed missions to the Red Planet, with NASA targeting the 2030s for the first human landing. Scientists are optimistic that with the right technology, we could one day harvest Martian materials, such as water, ice, and regolith, to support human colonies on the surface. But the possibilities extend even further to a bold and exciting concept: terraforming. Terraforming, the idea of transforming Mars into a more Earth-like environment, has captivated imaginations for decades. The challenge is daunting. How can we change the Martian atmosphere, warm the planet, and introduce the necessary elements for human life to thrive? While these efforts are still in their infancy, they hold the potential to not only reshape our relationship with Mars, but also transform how we think about life itself. The possibility of terraforming Mars raises profound questions about humanity's role in the universe and the ethical considerations of altering another planet's environment. The broader vision behind these ambitious space colonization efforts is to ensure the survival of humanity in the face of potential global catastrophes. By establishing a human presence on other planets, we could mitigate the risks posed by natural or man-made disasters on Earth, such as climate change, pandemics, or nuclear conflict. In this way, becoming a multiplanetary species might be humanity's best hope for long-term survival. But beyond the survival aspect, the pursuit of space colonization reflects humanity's unyielding curiosity and desire to explore the unknown. It is a dream that transcends borders, inspiring not only scientists and explorers, but also the millions of people who gaze up at the stars, wondering what lies beyond our home planet. Establishing human settlements on other planets has the potential to fundamentally reshape our understanding of the universe. First, by expanding our presence beyond Earth, we open up new vantage points from which to observe celestial phenomena. Each new location in space provides fresh opportunities to study the cosmos. For example, a colony on Mars could offer a unique perspective on solar radiation and its interaction with the Martian atmosphere, an insight that could not be achieved with telescopes located on Earth. This new vantage point could revolutionize our understanding of the Sun, the solar system, and the universe at large. Moreover, space colonization offers the opportunity for long-term scientific experiments that would be impossible on Earth. In the microgravity environments of space or the Moon, scientists can explore how living organisms adapt to conditions vastly different from those on Earth. Over generations, these experiments could reveal how life might evolve and adapt in extraterrestrial environments. The insights gained could have profound implications for human physiology, especially for the future of long-duration space travel. For example, understanding how the human body responds to the effects of reduced gravity could inform how we prepare for missions to distant stars or even other galaxies. In addition to scientific advancements, space colonization has the potential to drive technological innovation. The challenges of developing life support systems, sustainable agriculture in alien soils, and advanced energy solutions will require new technologies. These innovations could have far-reaching benefits, not just for space exploration, but also for solving problems back on Earth. The technologies developed for space habitats could be adapted to address some of our most pressing global challenges, such as climate change, food scarcity, and energy sustainability. In this sense, the pursuit of space colonization might not only help us conquer the cosmos, but also improve life on Earth. Finally, the ethical implications of space colonization are profound and complex. As humanity ventures into space, we must confront difficult questions about our responsibility to other worlds. What right do we have to alter the landscapes of celestial bodies, or potentially disrupt unknown ecosystems? These questions challenge our notions of exploration and environmental stewardship, and they force us to consider the moral dimensions of our actions. Should we impose human values on other worlds, or should we respect their autonomy and preserve them in their natural state? The concept of ownership in space further complicates these issues. Just as land ownership on Earth has a history fraught with conflict, the same dilemma extends to space. Who has the right to claim territory on Mars or the Moon? Should nations, corporations, or all of humanity share ownership of these celestial bodies? While the 1967 Outer Space Treaty prohibits nations from claiming sovereignty over celestial bodies, the lack of a comprehensive legal framework for space exploration raises difficult questions about territorial rights and governance. As we expand into the cosmos, we must also consider the ethical implications of transplanting Earth's social, political, and economic systems to other worlds. Would colonies on Mars reflect the best of human society, or would they simply recreate the inequalities and struggles that we face here on Earth? There is a distinct responsibility to learn from past mistakes and build new societies that prioritize equity, sustainability, and cooperation rather than privilege and exploitation. The road to space colonization is fraught with challenges both technical and ethical, but the potential rewards are immense. By exploring, understanding, and inhabiting other planets, we can ensure the survival of our species, expand our scientific knowledge, and deepen our understanding of our place in the universe. In the end, space colonization is not just about reaching other worlds. It's about discovering what it means to be human in a universe that is vast, mysterious, and full of possibility. Colonization of space has become one of the most talked about frontiers of our time, sparking a broad range of questions that not only touch upon the practical aspects of space travel, but also delve deep into the ethical and philosophical dimensions of humanity's journey beyond Earth. As we consider the future of space exploration, we are forced to confront the fundamental question: why are we reaching out to the stars? Are we venturing into the cosmos to escape the challenges and problems we face here on Earth, or is there a more noble pursuit at play, a genuine desire to expand our understanding of life in the universe? As we grapple with these complex ethical dilemmas, one thing becomes abundantly clear. Any steps we take beyond our home planet must be approached with a profound sense of responsibility and respect. There is an urgency to act thoughtfully, with a keen awareness of the potential consequences, not just for humanity, but for any other worlds we may one day inhabit. Every decision, from the selection of planets to explore to the methods we use to travel, will shape the future trajectory of our species and define our role as caretakers in a universe that is vast and largely unknown. One of the most significant challenges standing in the way of human expansion into the stars is the limitation of current propulsion technology. Traditional chemical rockets, while effective for missions within our solar system, fall woefully short when it comes to the long-duration journeys required to reach other star systems. If we are to turn the dream of interstellar travel into reality, we must develop propulsion methods that can drastically reduce travel times, possibly by a factor of hundreds or even thousands. In the search for these breakthrough technologies, scientists and engineers are exploring a range of innovative solutions. Nuclear propulsion is one such avenue, and it holds the promise of revolutionizing space travel. There are two main types: nuclear thermal propulsion and nuclear electric propulsion. Nuclear thermal propulsion uses the heat generated by a nuclear reactor to propel a spacecraft, offering a far more efficient use of fuel than conventional chemical rockets. This technology could potentially enable missions to Mars within a matter of months, rather than the years it would take using traditional methods. It could also pave the way for even deeper exploration of the solar system and beyond. On the other hand, nuclear electric propulsion harnesses electricity from a nuclear reactor to power ion thrusters. These thrusters work by expelling ions at extremely high speeds, producing a small but continuous thrust that builds over time. While the thrust produced is lower compared to chemical rockets, this type of propulsion is ideal for long-duration missions, particularly those aimed at exploring the distant stars. It offers the possibility of near-constant acceleration, potentially allowing spacecraft to reach speeds that make interstellar travel feasible in the long run. Another exciting possibility is the concept of solar sails. These sails are pushed by the pressure of sunlight and, in theory, could accelerate a spacecraft to significant fractions of the speed of light. Over time, solar sails could enable spacecraft to travel to nearby stars within decades, an unimaginable feat with current propulsion systems. As advancements in materials science continue, the idea of creating durable, efficient solar sails becomes increasingly plausible. What was once pure science fiction is now edging closer to the realm of possibility. The potential of antimatter propulsion and fusion drives is also being explored. Antimatter, the most energy-dense substance known to humanity, could theoretically provide vast amounts of thrust, but there are immense technical challenges to overcome in order to harness its energy safely. Similarly, fusion drives, which aim to replicate the same processes that power the sun, could offer a sustainable and powerful energy source for spacecraft engines, though they remain firmly in the experimental phase. Still, each step forward in these areas brings us closer to a reality where interstellar travel is not just a dream, but an achievable goal. As the exploration of these revolutionary propulsion technologies progresses, one thing becomes clear. We are on the brink of a new era in space exploration. These advancements could ignite the imagination of generations to come, fueling a thirst for discovery and a deeper understanding of the universe. In the meantime, space tourism is bridging the gap between everyday life and the vast expanse of the cosmos. No longer is space travel confined to astronauts alone. Ordinary people with the financial means can now experience the thrill of venturing into space. This burgeoning industry is making space more accessible and more relatable, transforming it from an abstract concept into a tangible experience. As private companies continue to push the boundaries of what is possible, space tourism could become a common experience in the near future. When ordinary individuals go into space, they come back with stories, photos, and a newfound enthusiasm for the cosmos. Their experiences, whether it's floating in weightlessness or seeing Earth as a small blue marble from above, inspire a sense of wonder and curiosity that can be contagious. Through social media and personal narratives, These travelers are helping to demystify space and bring the awe of the cosmos into our daily lives. In doing so, they foster a broader public interest in space science and astronomy, particularly among younger generations who may one day look to the stars as their future. Moreover, space tourism has the potential to elevate educational initiatives around space exploration. As the general public becomes more engaged with the idea of space travel, there is a corresponding increase in interest in the science behind it. This could lead to greater funding and resources being allocated to educational programs, helping to foster a new generation of scientists, engineers, and astronauts. Schools, community groups, and institutions dedicated to space education may emerge, further deepening the public's understanding and appreciation of the universe. Space tourism at its heart isn't just about luxury trips to the stars. It is a cultural shift, a democratization of access to the cosmos. It allows ordinary people to experience something once thought reserved for only the elite or highly trained astronauts. This shift could reignite our collective imagination, sparking conversations about the future of humanity in space and expanding our perspective on the possibilities that await us beyond Earth's atmosphere. Beyond the immediate thrills of space travel, our efforts to explore the stars could have profound implications for how we view our own planet. The study of the cosmos provides us with valuable insights into the delicate balance that sustains life on Earth. As we examine other planets and celestial bodies, we gain a deeper understanding of how fragile our ecosystems truly are. The harsh climates of Venus and Mars, for example, offer cautionary tales about the dangers of unchecked pollution and greenhouse gas emissions. By studying how atmospheric conditions evolve on these planets, scientists can draw direct comparisons to Earth's own climate dynamics, shedding light on the possible consequences of our actions if we continue down our current path. In a sense, the universe is teaching us critical lessons about the fragility of life. We are reminded, time and time again, that Earth is a unique oasis in the vast expanse of space, and its resources are not infinite. This realization brings into sharp focus the urgent need to preserve and protect our planet for future generations. Space exploration does not only offer us a chance to understand the cosmos, it also reminds us that in the grand scheme of the universe, we are but a small part of a much larger and interconnected system. As we look outward to the stars, we must also look inward, taking responsibility for the stewardship of our home planet. Our actions today will determine not just the future of space exploration, but the future of life on Earth itself. The lessons of the universe are waiting to be learned, and it is up to us to heed the warning signs before it is too late. Advancements in technology, particularly those driven by the exploration of space, have often proven to be more than just tools for studying the cosmos. These innovations frequently find valuable applications right here on Earth, helping us tackle some of the most pressing environmental challenges we face today. Take satellite imagery, for example. This technology has become indispensable for monitoring our planet's health. With it, we can track the devastating effects of deforestation, monitor the fluctuating conditions of our oceans, and observe the shifting landscapes of wildlife habitats. These real-time insights are crucial for addressing environmental issues, guiding efforts to combat climate change, manage resource depletion, and prevent further habitat destruction. As we look toward the stars, we are reminded of our place in the universe and the shared fate we have with all life on Earth. Just as celestial bodies orbit in harmony, there is a growing call for humanity to learn how to coexist with the environment and each other. Understanding the vast universe not only inspires awe and wonder, but it also serves as a clarion call to action, encouraging us to work together for a sustainable future, not just for ourselves, but for generations to come. While space exploration inspires curiosity, it also brings to light some of the more unsettling realities of our existence. Cosmic disasters such as asteroid impacts may seem like science fiction scenarios, but they are all too real. Throughout Earth's history, significant asteroid impacts have caused dramatic and often catastrophic changes. One of the most famous of these was the asteroid impact roughly 66 million years ago, widely believed to have contributed to the extinction of the dinosaurs, marking the end of the Cretaceous period. When a massive object collides with Earth, the energy released can be unfathomable. The explosion could be equivalent to millions of atomic bombs, generating searing heat and shock waves that devastate everything in their path. If the asteroid strikes an ocean, it can trigger colossal tsunamis. In the aftermath, debris is hurled into the atmosphere, blocking sunlight and triggering a phenomenon known as impact winter. This could lower temperatures worldwide and disrupt weather patterns, severely affecting global food supplies and potentially leading to famine and societal collapse. The lack of sunlight would also halt photosynthesis, decimating plant life and fundamentally altering ecosystems. But the environmental consequences are not the only threat. The psychological and societal impacts of such a cosmic disaster would also be profound. If an asteroid were found to be on a collision course with Earth, governments around the world would likely mobilize all available resources to devise strategies for mitigating the impact or evacuating populations. However, the uncertainty and fear surrounding such an event could lead to widespread panic, and failure to address the situation properly could lead to chaos even before the impact. Despite the daunting possibility of such a disaster, the scientific community is actively engaged in monitoring near-Earth objects. Dedicated missions aim to identify and track asteroids that could pose a risk to our planet. Some efforts are focused on devising potential deflection strategies, allowing humanity to better prepare for and potentially avoid the destruction that these cosmic events might bring. By deepening our understanding of these phenomena, we can help secure a safer future for all. In contemplating the vastness of space and the potential threats it holds, it is crucial to remember our responsibility to protect our own planet. Earth is the only known refuge for life in the infinite expanse of the universe. Its incredible diversity of ecosystems and species is unmatched by anything we've encountered beyond our atmosphere. Even the smallest organism plays an integral role in the intricate web of life. The loss of a single species could trigger far-reaching consequences throughout the environment. The human footprint on the Earth has far-reaching effects. From the emissions that fuel climate change to the pollution contaminating our oceans and the depletion of vital resources, every decision we make impacts the health of our planet. The ongoing shifts in Earth's climate are not isolated phenomena. They are interconnected, influencing weather patterns, sea levels, and biodiversity across the globe. As stewards of this unique world, we have an obligation to minimize our ecological footprint and champion sustainability. In the grand scheme of the cosmos, Earth is an anomaly, a rare jewel. While we have discovered thousands of exoplanets, none compare to the conditions that allow life to thrive here. Protecting our planet safeguards not just our immediate surroundings, but also our place in the universe. It ignites curiosity about the possibility of life elsewhere and drives us to consider our role as the guardians of this fragile oasis. By supporting conservation efforts, advocating for renewable energy, and promoting policies that prioritize ecological health, we take crucial steps toward preserving this planet for future generations. Ultimately, our responsibility extends beyond Earth. It is not merely about maintaining the health of our world today, but about preserving it for the explorers, scientists, and dreamers of tomorrow. These efforts serve as an inspiration, showing future generations a world still teeming with life and boundless possibility. As we look out into the stars, the study of other planets offers valuable lessons that inform our approach to environmental stewardship. Consider Mars, once a world that might have hosted liquid water and a thriving atmosphere. Today it is a barren, arid desert, its atmosphere lost to catastrophic climate changes. This serves as a stark reminder of how vulnerable planetary climates can be and urges us to carefully consider Earth's own delicate balance. Venus, on the other hand, presents an entirely different cautionary tale. The planet's thick clouds of sulfuric acid and surface temperatures high enough to melt lead highlight the extreme consequences of unchecked greenhouse gases. Venus's runaway greenhouse effect serves as a chilling preview of what could happen to Earth if we continue on our current trajectory of carbon emissions. Learning from Venus's fate reinforces the need for urgent action in combating climate change before it is too late. Meanwhile, the moons of Jupiter and Saturn, like Europa and Enceladus, offer a glimpse into the wonders that lie beyond Earth. These icy moons hide vast subsurface oceans beneath their frozen surfaces, possibly teeming with microbial life. The existence of such environments underscores the importance of preserving Earth's biodiversity and natural ecosystems, encouraging us to protect our planet not only for ourselves, but also for any future life that may one day be discovered elsewhere. These celestial examples serve as powerful reminders of the fragility of life on Earth. They inspire us to take action and become better stewards of our planet. As we gain a deeper understanding of the dynamics of other worlds, we can apply that knowledge to our efforts here on Earth, tackling climate challenges, protecting biodiversity, and ensuring that our planet remains a vibrant, thriving home for future generations. Cosmic events, such as supernova, gamma-ray bursts, and asteroid impacts, provide us with a humbling perspective on the vastness and unpredictability of the universe. These phenomena, often occurring millions or even billions of light years away, remind us of the immense forces at play beyond our planet. A supernova, for instance, occurs when a massive star exhausts its nuclear fuel and collapses under its own gravity, resulting in an explosion of unimaginable force. Should such an event occur near Earth, it could drastically alter our atmosphere and disrupt life as we know it. In many ways, these cosmic events serve as reminders of just how fragile life on Earth is. They underscore the delicate balance required for life to flourish and highlight the overwhelming power of the universe beyond our control. As we turn our gaze to the stars, we are reminded not only of the mysteries that lie ahead, but also of the profound responsibility we bear to safeguard the planet that sustains us all. The study of past cosmic events, such as the asteroid impact that led to the extinction of the dinosaurs, serves as a stark reminder of the fragile nature of life on Earth. This catastrophic event, which occurred approximately 66 million years ago, demonstrates how a single massive object striking the planet can cause widespread destruction, triggering an ecological collapse and mass extinctions. The sheer scale of such cosmic phenomena reminds us that although life on Earth has proven itself to be resilient, capable of remarkable adaptation in response to changing environments, it remains highly vulnerable to sudden and unpredictable disruptions from the universe. Reflecting on these cosmic occurrences helps us gain a deeper understanding of the precariousness of our planet's delicate balance. Our atmosphere, a protective shield that sustains life, is thin and fragile, and our ecosystems, finely tuned over millions of years, are vulnerable to disruptions far beyond our control. The asteroid that wiped out the dinosaurs serves as a poignant lesson in this regard. While life persists in countless forms, the universe is capable of unleashing events of unimaginable scale that could fundamentally alter or even wipe out the foundations of life as we know it. However, these events also highlight the importance of preserving and protecting our environment. By understanding our place in the cosmos and acknowledging the potential threats that loom from the vast expanse of space, we become more aware of the intricate and delicate connections that bind all life on Earth. This perspective encourages us to take responsibility for safeguarding our planet, not just for our generation, but for those that will follow. In our quest to understand the universe, we gain not only a deeper appreciation for the beauty and fragility of life on Earth, but also a sense of awe for the boundless mysteries that lie beyond our reach. As we look up at the night sky, we are reminded that our planet exists in a vast and ever-changing cosmos, one that is full of wonders, dangers, and unknowns. The study of the cosmos, which includes the discipline of cosmology, has led to some of the most profound discoveries in human history, reshaping our understanding of the universe itself and our place within it. Cosmology, the scientific study of the universe's origins, evolution, and ultimate fate, has provided us with groundbreaking insights that have radically transformed our understanding of reality. One of the most pivotal discoveries in this field was made in the early 20th century by astronomer Edwin Hubble. Hubble's observation that distant galaxies were moving away from us, an indication that the universe was expanding, changed the course of modern astronomy. This finding challenged the prevailing view of a static universe and suggested that space itself was stretching, carrying galaxies away from each other. This discovery led to the formulation of the Big Bang theory, which proposes that the universe began as an incredibly hot and dense point around 13.8 billion years ago, before rapidly expanding into the cosmos we observe today. Another transformative breakthrough came in the late 1960s when scientists Arno Penzias and Robert Wilson inadvertently discovered the cosmic microwave background radiation, a faint glow that permeates the entire universe. This radiation is a remnant of the early universe, a snapshot of the cosmos just a few 100,000 years after the Big Bang. The presence of this radiation provided strong evidence supporting the Big Bang theory and revealed that the universe began as an intensely hot and dense environment, dramatically altering our perspective on cosmic history. As we have continued to probe the universe's depths, we have encountered more mysterious phenomena that have reshaped our understanding of the cosmos. One such discovery is the existence of dark matter and dark energy, two enigmatic components that make up the vast majority of the universe's content. Dark matter, which cannot be directly observed, is inferred from its gravitational effects on visible matter, such as stars and galaxies. Despite its invisibility, dark matter is thought to account for about 27% of the universe's total mass energy content. Meanwhile, dark energy, a mysterious force that drives the accelerated expansion of the universe, is believed to comprise roughly 70% of the cosmos. Together, these two components raise fundamental questions about the nature of the universe and the forces that shape its future. The advent of modern observational technology has further expanded our ability to explore these cosmic mysteries. Telescopes, such as the Hubble Space Telescope and the more recent James Webb Space Telescope, have allowed scientists to peer deep into space, revealing distant galaxies and providing insights into their formation and evolution. These technological advancements have opened new frontiers in cosmology, offering us glimpses into the early universe and revealing the vast, interconnected structures that have developed over billions of years. Each new discovery adds another layer to our understanding of the cosmos, helping us to better comprehend the forces that govern the universe and the processes that shape its continued evolution. In addition to these advancements in cosmology, the emergence of quantum physics has led to a profound shift in our understanding of the universe. Before the advent of quantum theory, classical physics reigned as the dominant framework for understanding the physical world. In this classical view, particles were seen as solid, discrete objects moving through space in a predictable manner, much like tiny balls. However, quantum physics introduced a radically different perspective, revealing a universe that is far more complex and nuanced than we had ever imagined. At the heart of quantum mechanics is the concept of superposition, the idea that particles can exist in multiple states simultaneously. For example, an electron doesn't occupy one specific location, but instead exists as a cloud of probabilities spread across a range of possible positions. It is only when the particle is measured that its position becomes definite. This challenges traditional notions of determinism and suggests that at the most fundamental level, the universe operates according to principles of uncertainty and probability. These ideas force us to reconsider our understanding of reality itself, urging us to embrace a more fluid, dynamic view of the cosmos. Quantum entanglement, another mind-boggling concept in quantum mechanics, has further transformed our understanding of the universe. Entangled particles are so deeply linked that the state of one particle can instantaneously influence the state of another, even if they are separated by vast distances. This phenomenon defies the traditional laws of locality, which assume that objects can only influence each other through direct interaction. Entanglement raises profound questions about the interconnectedness of all things in the universe, prompting scientists to reconsider the very nature of space, time, and the relationships between objects. These developments in both cosmology and quantum physics have not only deepened our knowledge of the universe's mechanics, but have also sparked a sense of wonder and curiosity that continues to inspire both scientists and enthusiasts alike. As we uncover the mysteries of the cosmos, we are constantly reminded of the vastness of the unknown. The more we learn, the more questions arise. Questions that challenge our fundamental understanding of existence and our place in the universe. It is a journey that promises to keep us asking, seeking, and discovering for generations to come. The principles of quantum physics have laid the groundwork for revolutionary advancements in technology, many of which touch our lives in ways we often take for granted. From the development of semiconductors, which power the devices we use daily, to the cutting-edge innovations in quantum computing, these scientific breakthroughs are reshaping not only the way we understand the universe, but also how we interact with it. As we delve deeper into the quantum world, we continue to uncover new mysteries and gain insights that promise to further alter our perception of reality and expand our technological horizons. Moreover, the role of citizen scientists in the exploration of the cosmos has become increasingly vital. These passionate individuals, often without formal scientific training, have become indispensable players in our efforts to better understand the universe. Citizen scientists contribute to a vast array of projects, from analyzing data collected by powerful telescopes to tracking the movements of asteroids. Through the power of community collaboration, these everyday people are helping to unravel some of the greatest mysteries of the cosmos. Take, for example, the Galaxy Zoo project, a remarkable initiative where volunteers classify hundreds of thousands of galaxies based on their shapes. This project has not only provided invaluable data, but has also led to discoveries that might have eluded even the most seasoned professional astronomers. By enlisting the help of the public to perform tasks that require human intuition, like distinguishing between different types of galaxies, researchers have uncovered new patterns and anomalies in the data, which have deepened our understanding of galaxy formation and evolution. In another fascinating example, platforms like Planet Hunters engage citizen scientists to analyze light curves from distant stars in search of potential exoplanets. Volunteers comb through vast amounts of data, looking for tiny dips in brightness that indicate a planet might be passing in front of its host star. These efforts have already led to the discovery of numerous exoplanets, providing us with a broader view of the universe and its potentially habitable worlds. Engaging the public in scientific inquiry not only accelerates research, but also fosters a deeper appreciation for science among the participants. Each contribution, no matter how small, adds to our collective understanding of the universe, igniting curiosity and excitement about the mysteries of the cosmos. The increasing involvement of citizen scientists serves as a powerful reminder that scientific exploration knows no boundaries. Anyone, regardless of background, can play a role in the quest for knowledge and help unlock the secrets of our vast and mysterious universe. Collaboration across different disciplines, such as physics, astronomy, and philosophy, can enrich our understanding of the cosmos in profound ways. Each field offers a unique perspective and methodology, creating a more holistic approach to answering the deep questions of existence. Physics, with its laws governing matter and energy, provides the foundation for understanding the mechanics of the universe, while astronomy uses powerful telescopes to observe the grandeur of distant celestial bodies. Philosophy, on the other hand, steps in to examine the deeper implications of these findings, questioning the very nature of reality, existence, and our place in the cosmos. When scientists from different fields collaborate, they tackle questions that no single discipline could answer on its own. For example, astrophysicists might use complex theories to explain the existence of black holes, but it takes a philosophical framework to understand the implications of these phenomena on our concepts of time and space. Similarly, philosophers can frame questions about the universe that spark new theories in physics, guiding the development of experimental designs and techniques. This cross-disciplinary synergy has the potential to lead to groundbreaking discoveries, challenging conventional thinking, and expanding the boundaries of human knowledge. Furthermore, interdisciplinary collaboration encourages the development of new tools and technologies. Techniques from physics that are used in experiments can enhance astronomical observations, while philosophical inquiry can guide ethical considerations in scientific research. Together, these fields are uniquely positioned to explore some of the most profound questions about the universe, such as the origins of time, the possibility of parallel universes, or the very nature of consciousness itself. This collaborative spirit fosters a richer dialogue about existence and the universe, allowing us to probe deeper into the mysteries of the cosmos and challenge our understanding of the world around us. One of the most thrilling possibilities for humanity's future is the discovery of extraterrestrial technology. If we were to find evidence of advanced civilizations beyond Earth, it would completely transform our understanding of the universe and our place within it. The very idea that intelligent life exists elsewhere in the cosmos challenges everything we know about life, intelligence, and the nature of existence itself. It would raise profound questions about the nature of these civilizations. How did they evolve? What are their technological capabilities? What can we learn from them? Such a discovery would undoubtedly spark a new wave of scientific curiosity and research. Scientists would rush to study any technology that could be found, eager to understand its principles and apply them to our own world. This could lead to groundbreaking innovations in energy production, propulsion, communication, and even space travel, advances that far exceed our current technological capabilities. Entire fields of engineering and technology could be revolutionized overnight, opening up possibilities that we cannot yet even imagine. However, the discovery of extraterrestrial technology would also raise a host of philosophical, ethical, and political questions. What would it mean for humanity to share the universe with other intelligent beings? How would we communicate with them? What protocols should be in place to ensure peaceful engagement? Furthermore, the revelation of extraterrestrial intelligence could prompt a re-evaluation of international relations, as governments and organizations would need to navigate the complexities of this new cosmic reality. Ultimately, the discovery of extraterrestrial technology would force humanity to confront the very nature of existence and our responsibilities as stewards of our planet. We would need to reconsider what it means to be human in a universe that is no longer limited to our own world. This paradigm shift would prompt a collective effort to explore not only what lies beyond Earth, but also what this discovery means for our future and identity as a species. International collaboration is essential in the exploration of space and the universe. By bringing together scientists, engineers, and researchers from around the world, countries can share resources, knowledge, and expertise to tackle complex questions that no single nation could solve alone. This cooperative approach enables global efforts to pool their strengths, whether in funding, technology, or scientific knowledge. By working together, nations can push the boundaries of exploration and understanding, creating advancements that benefit all of humanity. The International Space Station, ISS, is a shining example of what can be achieved through international collaboration. This incredible achievement involves multiple countries working together to maintain and operate the space station, conducting experiments that explore the effects of microgravity on biological systems. These experiments are helping to advance our understanding of life itself and pave the way for new medical and technological breakthroughs. The insights gained from the ISS benefit not only the countries involved, but also all of humanity. Large astronomical projects such as the Large Hadron Collider in Switzerland or the upcoming James Webb Space Telescope further illustrate the power of global teamwork. These projects require the contributions of scientists and experts from across the globe to connect data, interpret findings, and push the boundaries of what is possible. Without the input of diverse perspectives and expertise, these projects would not be possible. International collaboration also fosters a culture of unity and shared purpose in scientific exploration. In a world where the cosmos can seem vast and isolated, the coming together of scientists from all corners of the Earth underscores the universality of our quest for knowledge. By sharing both triumphs and challenges, these collaborative efforts inspire future generations to wonder and explore, nurturing a spirit of curiosity that transcends borders and unites humanity in our pursuit of understanding. The scientific community plays a vital role in addressing misconceptions about space through educational outreach and public engagement. Through the production of educational materials, books, documentaries, podcasts, and interactive websites, scientists are working to clarify common misunderstandings about the cosmos. These resources aim to provide accurate, easily digestible information about complex astronomical phenomena such as black holes, the vacuum of space, and the true nature of stars. By educating the public and dispelling myths, the scientific community is helping to create a more informed and curious society that is better equipped to understand and appreciate the wonders of the universe. Moreover, scientists frequently participate in public lectures and community events where they actively engage with the public by sharing their expertise and answering questions. This direct face-to-face interaction creates an invaluable dialogue between scientists and the general public, enabling the opportunity to debunk myths, correct misconceptions, and provide a clearer understanding of complex scientific concepts. These events often spark curiosity and ignite a passion for science in attendees who may otherwise have held on to inaccurate views about the cosmos. Through these interactions, scientists illuminate the importance of critical thinking, encouraging audiences to ask questions, seek deeper insights, and explore the vastness of the universe in new and more meaningful ways. Social media platforms have become an essential tool in this public outreach effort. Many scientists and research institutions now use these digital channels to disseminate information rapidly and connect with a broader audience. These platforms allow scientists to address trending myths and popular misconceptions about space, astronomy, and other scientific fields, providing accurate, well-researched facts to counter misinformation. By using social media effectively, scientists amplify their voices and make their work more accessible, engaging, and relatable to the public. These interactions help to create an informed and scientifically literate society, one that is not only knowledgeable about the wonders of space, but also capable of thinking critically about the world around them. Collaboration plays a vital role in these outreach efforts. Scientists, educators, and communicators have forged powerful partnerships to ensure the continued expansion of these initiatives. School programs, science museum collaborations, and involvement in global campaigns all contribute to promoting accurate scientific literacy. By combining various approaches, the scientific community works toward creating a public that appreciates the wonders of space, equipped with accurate knowledge. This ongoing endeavor highlights the importance of effective science communication while showcasing the intrinsic beauty and mystery of the universe. Public engagement initiatives are pivotal in fostering interest in astrophysics by making complex and often abstract concepts more tangible and relatable. These initiatives come in many forms, such as interactive exhibitions, public lectures, stargazing events, and community-based science projects. By presenting astrophysics in a hands-on, interactive manner, audiences can experience the cosmos firsthand, which fuels their curiosity and deepens their understanding. One particularly effective approach is storytelling. Narratives that combine the latest discoveries with human experiences can captivate imaginations. For example, the story of a scientist who grew up in a small town and made a major contribution to a groundbreaking discovery can inspire young minds, showing them that anyone can pursue a career in science, no matter their background. Furthermore, scientists often share their personal motivations, challenges, and experiences, humanizing the field of science in a way that resonates on a personal level with the audience. This human connection can make scientific work feel more accessible and relatable. In addition, digital platforms and social media significantly enhance these outreach efforts. Online webinars, interactive social media campaigns, and educational videos enable scientists to reach a broader and more diverse audience, especially younger generations. By harnessing the power of digital media, astrophysics can be brought into living rooms and classrooms, inspiring curiosity in ways that traditional outreach methods may not always achieve. These outreach initiatives also help create communities around science where individuals can discuss, ask questions, and share ideas. Engaging local schools, community groups, and individuals in these efforts fosters collaboration, encouraging the growth of a new generation of science enthusiasts. When the public is actively involved in the exploration of astrophysics, it nurtures a culture of lifelong learning and a deeper appreciation for the universe, ensuring that the pursuit of knowledge and discovery will continue for generations to come. Over the history of space exploration, numerous missions have encountered setbacks, each leaving behind valuable lessons that shape future endeavors. One of the most significant lessons learned is the critical need for thorough testing and validation in early mission phases. Many spacecraft were launched with insufficient trials, which led to avoidable failures. For instance, the Mars Climate Orbiter disaster of 1999 was the result of a simple metric conversion error, underscoring the necessity for rigorous checks and cross-referencing at every stage of mission preparation. By reflecting on these past mistakes, engineers have learned the importance of establishing strict protocols, conducting extensive simulations, and ensuring that every detail is double-checked to prevent such errors in future missions. Additionally, the importance of communication and collaboration within teams has become increasingly clear. The failure of the Columbia Space Shuttle in 2003 illustrated how critical it is for engineers, scientists, and mission control to share information, concerns, and insights openly. Working in isolated silos can lead to critical information being missed or overlooked, and this tragedy emphasized the need for interdepartmental cooperation. Today, modern missions focus on fostering a culture of collaboration, where every team member's voice is heard and valued, leading to more informed decisions and better outcomes. Moreover, these setbacks have revealed the importance of building flexibility into mission designs. The journey to exploring and understanding space is inherently unpredictable, filled with unforeseen challenges and surprises. Take, for example, the Spirit and Opportunity rovers, initially designed for a 90-day mission on Mars. Their remarkable resilience allowed them to continue functioning for years beyond their expected lifespan, making groundbreaking discoveries along the way. This experience taught mission planners to build adaptability into their strategies, enabling them to adjust plans as needed and extend the life of their missions, ultimately enhancing the scope of their discoveries. Finally, there has been an increasing focus on transparency and public engagement, particularly following mission failures. When missions do not succeed, it is vital for the scientific community to openly communicate the lessons learned with the public. This approach not only fosters an informed society, but also nurtures a sense of shared adventure and collective learning in space exploration. By openly discussing setbacks, scientists build trust and encourage public involvement, which can ultimately drive further interest and passion for the field. The sharing of data across international borders is another key factor in accelerating scientific progress. When researchers collaborate on a global scale, they pool their resources, expertise, and findings, creating a more comprehensive and nuanced understanding of complex scientific problems. For example, consider the ongoing battle against diseases like COVID-19. The rapid exchange of genomic data among researchers from different countries allowed scientists to track the virus's mutations, develop vaccines, and establish effective public health strategies in record time. Without such collaboration, progress would have been far slower and critical resources would have been duplicated rather than built upon. Instant access to shared data not only speeds up research, but also improves its quality. This global cooperation ensures that discoveries are not limited by national boundaries, but are instead part of a collective effort to solve the world's most pressing challenges. Whether it's combating global pandemics, addressing climate change, or advancing our understanding of the cosmos, the sharing of knowledge and data across borders accelerates progress and paves the way for groundbreaking achievements in science. Moreover, sharing data fosters inclusivity in scientific endeavors, offering researchers from less affluent nations access to valuable information that enables them to contribute meaningfully to global scientific dialogues. This act of democratizing knowledge not only empowers underrepresented communities, but also fuels innovation. As ideas from diverse cultures and scientific traditions come together, they often lead to breakthroughs that might never have emerged in isolation. This collaborative spirit makes science not just a pursuit of the few, but a universal endeavor that benefits humanity as a whole. In essence, international data sharing nurtures a thriving collaborative environment that accelerates scientific progress. By allowing scientists to work together, regardless of their physical locations, we create a more robust and effective search for solutions to some of the world's most pressing challenges. The interconnectedness of modern science stands as a powerful testament to how collaboration can unlock discoveries that benefit everyone, fostering a deeper collective understanding of the world and beyond. Art plays an equally vital role as a bridge between complex scientific ideas and the general public, especially when it comes to making the vast and intricate universe we inhabit more accessible. While science often depends on data and equations to communicate findings, art transcends language barriers, invoking emotions that can make abstract concepts more tangible and engaging. Through creative expression, artists illuminate scientific principles, inviting viewers to connect with these ideas on a personal level. Visual art, for example, can transform abstract theories like the nature of black holes or the expansiveness of galaxies into vivid representations. These works turn what could be dry mathematical ideas into visually compelling narratives. When someone gazes at a painting of the cosmos, they not only appreciate the beauty, but also gain insights into the scale and complexity of the universe. This visual depiction serves as a tool for demystifying science, allowing the audience to understand these concepts without feeling overwhelmed by technical jargon. Furthermore, performance art and multimedia experiences offer additional layers of engagement. Imagine a theatrical performance that interprets the life cycle of stars, or a dance that visually narrates the movement of celestial bodies. These forms of expression create immersive, emotional experiences that resonate with audiences, making the underlying science more relatable. By transforming scientific ideas into stories or movements, art captivates the audience's attention, ensuring that the concepts presented leave a lasting impression. Collaborative projects between scientists and artists have the potential to yield even more remarkable results. Artists, in their exploration of scientific themes, often ask questions that may not occur to scientists, pushing both fields into new realms of possibility. In this symbiotic relationship, art does not merely communicate science, it fosters curiosity. Through such collaborations, art sparks the imagination and invites audiences to seek further understanding of the universe we all share. Ultimately, art becomes an indispensable tool, ensuring that the wonders of the cosmos are accessible to all, regardless of their scientific background. Film and literature are equally powerful mediums, acting as mirrors to our evolving understanding of the cosmos. These art forms have the unique ability to blend storytelling with scientific exploration, inviting audiences to consider the vastness of space, the nature of existence, and humanity's place within this immense expanse. For instance, Arthur C. Clarke's 2001 A Space Odyssey delves into profound philosophical questions surrounding evolution, intelligence, and the future of humanity, all set against the backdrop of space exploration. Likewise, films like Interstellar bring complex scientific concepts like time dilation, black holes, and the fabric of space-time to mainstream audiences, making high-level physics accessible through emotional storytelling. These works bridge the gap between scientific theory and human experience, allowing viewers to connect with otherwise abstract ideas on a personal level. By fusing science with emotional narratives, these films don't just encourage us to think about the cosmos, they compel us to feel something about it, its beauty, its danger, and its profound mystery. Literature has played an equally significant role in shaping our understanding of the universe. Works like Carl Sagan's Cosmos and Neil deGrasse Tyson's Astrophysics for People in a Hurry have made complex scientific concepts relatable and digestible for general audiences. These books explore themes of awe and curiosity, often drawing attention to the incredible interconnectedness of all things. By using vivid descriptions and imaginative language, authors spark curiosity in readers, inviting them to explore the universe beyond our blue planet. Both film and literature go beyond presenting scientific facts. They challenge us to think deeply about the cosmos, prompting us to reflect on what we know, and perhaps more importantly, what we do with that knowledge. The stories told through these mediums shape our understanding of the universe and our role within it, posing fundamental questions that resonate across time and space. These narratives serve as a reminder that humanity is part of a much larger story, unfolding within the vastness of the cosmos. Visual representations of the universe, too, have an extraordinary impact on how the public perceives space and our place within it. Images captured by powerful telescopes and space missions showcase the universe in all its breathtaking detail. These stunning visuals transform abstract concepts like distant galaxies or the vastness of space, into tangible, awe-inspiring representations. They invite curiosity and wonder, which are essential for deepening our understanding of the universe. Such images also serve as a bridge between scientific research and public engagement. Stunning photographs of cosmic phenomena, such as black holes or the expanding universe, make these complex ideas more relatable. They capture attention, sparking interest in scientific fields like astrophysics and cosmology. This curiosity might start with a mere admiration of a photograph and eventually lead someone to explore the sciences further, perhaps even inspiring a career in these fields. In the end, the fusion of science and art through data sharing with visual representations, literature, performance, and film creates a profound and lasting impact. By making complex ideas more accessible and emotionally resonant, we not only enhance public engagement with science, but also ensure that the pursuit of knowledge is a collaborative and inclusive journey, one that inspires curiosity, fosters understanding, and encourages the pursuit of greater truths about the universe we share. Visuals, while captivating, can sometimes distort the public's perception of reality. This is particularly true when it comes to space and the universe. Images, often designed to be awe-inspiring, can convey a sense of grandeur that overshadows the harsh truths about the cosmos, such as its inhospitable nature. These stunning representations, while beautiful, may lead us to believe that the universe is far more accessible or welcoming than it truly is. This romanticized view of space can create misconceptions, presenting a version of the universe that doesn't fully align with scientific reality. Therefore, it's essential to balance these imaginative visualizations with accurate scientific understanding to ensure we convey not only the wonder of the universe, but also its vast, uncharted challenges. The imagery we use to depict space plays a dual role. It captivates the imagination and fuels our curiosity about our origins and the mysteries of existence. At the same time, it pushes us toward a deeper appreciation of the scientific disciplines that strive to unravel these mysteries. Through breathtaking images of distant galaxies, nebulae, and cosmic landscapes, we are invited to reflect on our place in the universe, sparking a desire to understand the forces that shaped it. These visuals act as a gateway, expanding our minds and encouraging us to engage with the deeper questions of life. However, they also underscore the need for a grounded, scientific perspective to avoid oversimplifying the complexities of space. Creativity is often seen as the driving force behind scientific discovery and innovation. It's the spark that pushes scientists beyond conventional boundaries, urging them to challenge established norms and explore uncharted territories. Imagination allows researchers to ask new questions, propose novel hypotheses, and experiment with fresh approaches. The breakthroughs we've seen in various fields, from medicine to technology, are frequently the result of creative thinking that enables scientists to envision possibilities that others have not yet considered. The true power of creativity lies in its ability to connect seemingly unrelated ideas across different disciplines. For example, when a mechanical engineer finds inspiration in nature, this can lead to innovations such as biomimicry, where designs and technology mimic the complex systems found in living organisms. This interdisciplinary approach not only fosters creativity, but also accelerates technological progress by merging ideas from diverse fields. In a similar vein, creativity plays a crucial role in how scientific theories are developed and tested. When faced with uncertainty or unexpected results, creative thinking allows scientists to rethink their approaches, adjust their research questions, and refine their methods. Rather than viewing failure as a setback, creative minds understand it as a valuable part of the discovery process. The intersection of creativity and scientific inquiry is where true innovation thrives. By blending imagination with rigorous experimentation, scientists can inspire breakthroughs that expand our understanding of the universe. But this synergy is not limited to laboratories or theoretical frameworks. It also fosters a culture of curiosity, exploration, and the relentless pursuit of knowledge. This dynamic relationship between art and science opens up a space for deeper reflection on the nature of the cosmos and our place within it. Art plays a significant role in communicating complex scientific ideas, often offering insights that resonate on an emotional level. Through powerful visual representations, such as stunning images of galaxies, black holes, or nebulae, art helps make abstract scientific concepts more tangible. For example, by portraying the vastness of space or the intricacies of time, artists invite us to ponder questions that lie beyond our immediate understanding, such as the origins of the universe or the fundamental laws that govern existence. Art not only provides an aesthetic experience, but also enriches our intellectual engagement with science, making it more accessible and relatable. Consider how iconic photographers like Ansel Adams use the medium to capture the grandeur of Earth's landscapes, instilling a sense of awe and reverence for nature. Adams's work inspired people to appreciate the delicate balance of ecosystems and the importance of environmental conservation. Similarly, contemporary artists often draw on scientific concepts, such as quantum physics or genetics, to inform their work. By exploring the implications of these discoveries, they open up conversations about the future of humanity and our relationship with the universe. This symbiosis between science and art fosters public interest in scientific progress, while highlighting the creative process that underpins much of scientific exploration. Art transforms complex data into something more approachable, bridging the gap between expert knowledge and everyday experience. When artists translate scientific phenomena into visual form, they make these concepts not only comprehensible, but also deeply meaningful. Imagine an art installation that brings the life cycle of a star to life, or an exhibit that visualizes the intricacies of the human genome. These experiences not only inspire awe, but also ignite curiosity, encouraging people to engage with science in new ways. Through this fusion of creativity and knowledge, science and art work together to expand our cultural narrative, promoting a more holistic view of human understanding. It reminds us that the search for truth in the universe is not solely a rational endeavor, but also a deeply emotional and intuitive journey. The process of discovery is as much about asking profound questions as it is about exploring and embracing the mysteries that connect us all. Through art, we can experience the universe on a personal level, gaining a deeper understanding of our place in the cosmos and the stories that shape our collective human experience. The origins of the universe have long been a subject of fascination, spurring countless theories and ideas from scientists and philosophers alike. Of these theories, the Big Bang theory is the most widely accepted. It suggests that the universe began as an incredibly hot, dense point, roughly 13 billion years ago. In the blink of an eye, this point expanded rapidly, eventually leading to the universe we see today, filled with galaxies, stars, planets, and more. Supporting this theory are key pieces of evidence, such as the cosmic microwave background radiation, which is considered a remnant of the early fiery state of the universe. Additionally, the observed redshift of distant galaxies indicates that the universe is still expanding, providing further evidence of the Big Bang's occurrence. In contrast to the Big Bang theory, the steady-state theory offers a different explanation for the universe's origins. This theory proposes that the universe has no beginning or end, instead expanding eternally while maintaining a constant average density. As galaxies move apart, new matter is continuously created to fill the gaps. However, this theory has fallen out of favor over time. Observations, particularly the discovery of cosmic microwave background radiation, provided strong evidence for the Big Bang theory, leading to the steady-state theory's decline. Another fascinating idea is the theory of cosmic inflation. This concept builds upon the Big Bang model, proposing that the universe experienced an exponential expansion during the first moments after the Big Bang. This rapid inflation smoothed out irregularities and set the stage for the uniformity we observe in the cosmos today. Cosmic inflation helps explain the uniform temperature of the cosmic microwave background radiation and sheds light on the large-scale structure of the universe, including the distribution of galaxies. These theories offer different perspectives on the origins of the universe, each providing valuable insights into the nature of our cosmos. While the Big Bang remains the most widely accepted explanation, the evolving landscape of scientific discovery continues to challenge and refine our understanding of the universe's beginnings. As we explore these ideas further, we continue to uncover new layers of mystery. all of which contribute to a deeper understanding of the vast and awe-inspiring universe in which we live. The concept of the multiverse theory suggests an astonishing idea that our universe might not be unique. Instead, it could be just one of many parallel universes, each potentially governed by different physical laws and constants. This opens the possibility for a wide array of realities, some that may differ vastly from our own, perhaps with entirely different forms of life, matter, and energy. While the multiverse theory stretches the boundaries of our understanding and remains speculative, it also raises profound questions. What might exist beyond the observable limits of our universe? Could there be other realms, completely different from our own, existing alongside us? These are the kinds of tantalizing questions that challenge our perception of reality, inviting us to think beyond the confines of the known universe and explore what lies in the unexplored depths of existence. In stark contrast, the Big Bang Theory provides a more grounded explanation for the origins of our universe, arising from a series of groundbreaking discoveries made in the early 20th century. The first major clue came in the 1920s when astronomer Edwin Hubble made a stunning observation. Galaxies were moving away from us. This implied that the universe was not static as once believed, but expanding. Hubble's discovery contradicted the then popular notion of a fixed, unchanging cosmos and suggested instead a dynamic, evolving universe. His findings provided compelling evidence that something extraordinary had occurred to shape the cosmos into what we observe today. One of the most crucial pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation, CMB, which was discovered accidentally by scientists Arno Penzias and Robert Wilson in the 1960s. This faint, pervasive radiation is believed to be the afterglow of the universe's initial explosion, providing a snapshot of the universe when it was just a hot, dense ball of matter and energy. The presence of this radiation across the entire universe strongly supports the Big Bang model, suggesting that the universe began in an extremely hot and compact state. As the universe expanded, it cooled, and the CMB became the remnant of that early energetic phase. Additionally, the abundance of light elements such as hydrogen and helium found throughout the universe further bolsters the Big Bang Theory. According to the model, these elements were formed during the first few moments after the Big Bang in a process called nucleosynthesis. The relative amounts of these elements, as observed across the cosmos, closely match the predictions of the Big Bang model, strengthening its credibility. Over the decades, a wealth of observational evidence and theoretical advancements has led to widespread acceptance of the Big Bang Theory. The theory not only explains the current expansion of the universe, but also provides a cohesive narrative of how the universe evolved over billions of years. Though alternative theories have emerged, none have been able to match the Big Bang model's consistency and predictive power in explaining the universe's features. As such, the Big Bang Theory remains the cornerstone of modern cosmology, offering a framework for understanding the universe's past, present, and future. The universe's first moments immediately after the Big Bang were truly extraordinary. Imagine a place where energy and matter existed in a chaotic state, teeming with fundamental particles like quarks, electrons, and neutrinos, all moving at nearly the speed of light. Temperatures soared to levels unimaginable, exceeding trillions of degrees Celsius. These conditions were not just extreme, they were foundational to everything that would follow in the universe's evolution. The particles that raced through space in those first moments would go on to form the building blocks of everything we see around us today. Within mere moments after the Big Bang, the universe began to expand in a process known as inflation. This rapid expansion stretched the fabric of space itself, setting the stage for the universe's eventual growth into the vast cosmos we know. During these incredibly brief moments, the first building blocks of matter began to emerge. Quarks, fundamental particles that make up protons and neutrons, coalesce to form protons and neutrons. As the universe continued to cool, these particles began to combine, setting the stage for the formation of atomic nuclei. Within minutes of the Big Bang, the universe had cooled enough for protons and neutrons to unite and form light elements, primarily hydrogen and helium. This stage, known as Big Bang nucleosynthesis, lasted only a few minutes, but was crucial for shaping the universe's composition. Within about 20 minutes, most of the helium and a small amount of lithium had formed. The interesting thing about this early composition is that it has remained largely unchanged over the billions of years since, laying the foundation for the stars and galaxies that would later emerge. As the universe continued to expand and cool over several 100,000 years, it entered a phase known as recombination. During this period, electrons combined with protons to form neutral hydrogen atoms, which allowed photons, light particles, to travel freely for the first time. The release of these photons created the cosmic microwave background radiation, the faint glow that permeates the universe today. This radiation provides scientists with a glimpse of the universe when it was just 380,000 years old, offering an invaluable snapshot of its early conditions. The study of the early universe requires a combination of observational techniques, theoretical models, and experimental physics. One of the most important tools in this investigation is the cosmic microwave background. By studying the CMB, scientists can infer the universe's temperature, density, and the fluctuations that eventually led to the formation of galaxies. In addition to the CMB, astronomers use advanced telescopes to observe light from distant galaxies. This light, having traveled for billions of years, provides a window into the past, allowing scientists to study the formation and evolution of cosmic structures over time. Another critical area of research involves high-energy particle physics, which helps scientists understand the universe's early moments. Large particle colliders, such as the Large Hadron Collider, are used to recreate the extreme conditions that existed just after the Big Bang. By smashing particles together at unprecedented speeds, scientists can generate temperatures and energies similar to those found in the early universe. These experiments allow them to study the fundamental forces and particles that shaped the cosmos, offering further insight into how the universe evolved from its hot, dense beginnings into the expansive cosmos we observe today. Through these combined efforts, we are piecing together a more detailed and profound understanding of the universe's history, one that continues to inspire both awe and curiosity as we venture deeper into the unknown. Theoretical physics delves deep into the mysteries of the cosmos through complex mathematical modeling and cutting-edge simulations. By using intricate equations, scientists predict how the universe should behave under different circumstances from the earliest moments of existence to the present day. These models are constantly refined as they are tested against real-world observational data, creating a dynamic feedback loop that sharpens our understanding. The interaction between theory and observation has allowed scientists to piece together a much clearer picture of the universe's infancy, unveiling a vibrant, ever-evolving tapestry that captivates and inspires. The study of these cosmic phenomena is not limited to a single field of research. By blending insights from multiple disciplines, scientists have unlocked many of the universe's deepest mysteries, shedding light on how our cosmos came into being. This rich narrative of cosmic evolution has reshaped our view of the universe, from its fiery origins to its continued expansion and transformation. One of the most profound pieces of evidence that has emerged from this research is the cosmic microwave background, CMB radiation. The CMB, often described as a faint afterglow from the Big Bang, offers a direct connection to the universe's early moments. This omnipresent radiation, visible in all directions of the sky, provides an image of the universe at a pivotal time, when it was just 370,000 years old. At this stage, the universe had cooled sufficiently for light to travel freely, marking the end of a long period when the universe was a hot, dense soup of particles. As the universe continued to expand, this light was stretched into the microwave range, an effect caused by the ongoing expansion of space itself. The discovery of this radiation was one of the defining breakthroughs in cosmology, offering critical insights into the age, composition, and evolution of the universe. The CMB is not merely a uniform glow. It contains subtle fluctuations in temperature, which correspond to minute variations in density. These fluctuations are the seeds from which the universe's large-scale structures, including galaxies, would eventually form. Detailed measurements of these temperature variations, particularly from satellites like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck Observatory, have allowed scientists to calculate the rate of the universe's expansion and determine its overall geometry. These fluctuations also provided conclusive evidence for the Big Bang theory, including the ratio of hydrogen to helium in the early universe. This ratio, confirmed by CMB data, closely matches the predictions made by nuclear physics regarding the conditions just after the Big Bang. In addition to offering a clearer view of the universe's early state, the CMB has proven essential in the identification of dark matter and dark energy, two of the most mysterious and enigmatic components of the cosmos. By studying the way matter was distributed in the early universe, scientists realized that ordinary matter accounts for only a fraction of the universe's total energy density. The remainder is attributed to dark matter and dark energy, which continue to shape the universe's evolution and will likely dictate its ultimate fate. The insights gleaned from the CMB not only illuminate the universe's past, but also provide a framework for future explorations into the nature of these mysterious forces. The formation of galaxies is one of the most awe-inspiring processes in the universe. Galaxies emerge from the cosmic web, a vast, interconnected structure of dark matter and gas that permeates space. This web consists of long, filamentous strands of dark matter which act as gravitational scaffolding. Over time, small density fluctuations within this web cause gas and matter to clump together. As gravity strengthens these clumps, the formation of galaxies begins. This process stretches across billions of years, transforming the universe from a hot, uniform state into a dynamic and complex array of galaxies. The shape and structure of a galaxy are influenced by a variety of dynamic processes. As gas and stars collapse under the influence of gravity, they conserve angular momentum, causing them to spin faster and faster. This can lead to the creation of spiral galaxies, which are characterized by their iconic arms and flat disc-like shapes. In contrast, galaxies that experience significant mergers with other galaxies often take on more irregular or elliptical forms. These collisions can trigger intense bursts of star formation, radically altering the structure and appearance of both galaxies involved. Galaxy interactions are central to their evolution. When two galaxies collide, their gravitational forces distort each other's shapes, often leading to the formation of new features such as tidal tails, streams of gas and stars that are pulled away from the galaxies. Over time, these interactions can merge galaxies into larger, more massive structures. The result can be a galaxy with a smooth, rounded appearance, or one that displays a more chaotic and irregular shape. Environmental factors also play a key role in shaping galaxies. Galaxies located within dense clusters of other galaxies experience different gravitational influences than isolated galaxies. In crowded environments, the competition for space and resources can suppress star formation, leading to older, redder stars dominating the galaxy. Conversely, galaxies in less crowded regions can continue to form new stars, resulting in a vibrant, diverse population of young stars and nebulae. Understanding the formation of galaxies requires a deeper dive into the roles of dark matter and dark energy. Dark matter, which constitutes about 23% of the universe, is invisible and does not emit light. However, its gravitational effects are profound. As the universe expanded after the Big Bang, dark matter began to clump together under gravity, forming dense regions that acted as the scaffolding around which ordinary matter could accumulate. This gravitational attraction was crucial for the creation of the large-scale structures we observe in the universe today. Without dark matter's invisible influence, the formation of galaxies and the very structure of the universe as we know it would have been impossible. In the grand scheme of cosmic evolution, galaxies are not solitary islands, but part of a larger, interconnected web of forces and interactions. The universe continues to evolve, shaped by the interplay of gravity, dark matter, dark energy, and the physical laws that govern all matter. As our understanding of these forces deepens, we gain not only a clearer picture of the cosmos's past, but also a glimpse of its future, one that is still unfolding in ways we are only beginning to understand. Dark energy is one of the most intriguing and significant components of our universe, representing about 73% of its total mass energy content. Unlike the familiar matter and forces that we encounter in daily life, dark energy is an enigmatic force driving the accelerated expansion of the cosmos. While dark matter plays a critical role in pulling together matter to form galaxies and structures within the universe, dark energy works in the opposite direction, pushing galaxies apart. This contrasting dynamic of attraction and repulsion influences not only the movement of galaxies, but also the very shape and fate of the universe itself. If dark energy did not exist, dark matter's gravitational pull would dominate the universe's dynamics. Without the expansionary force of dark energy, the universe might have followed a much different path, with matter clustering together more densely, perhaps ultimately leading to a big crunch, where everything collapses back into a singularity. Together, dark matter and dark energy create the framework within which the universe evolves, driving the formation and ongoing transformation of galaxies. In the early universe, dark matter began to create dense regions of mass. These concentrations served as gravitational wells that drew in ordinary matter, such as gas and dust. Over time, these clumps of matter coalesced into the very first stars and galaxies, marking the beginning of cosmic structure formation. As galaxies formed, they underwent constant evolution, influenced by the underlying expansion of space itself, driven by dark energy and by interactions with other galaxies. This complex cosmic dance set the stage for the universe as we know it, with dark matter providing the scaffold for galaxy formation and dark energy shaping their long-term destiny. Galaxies, the majestic collections of stars, gas, dust, and dark matter, go through a fascinating and intricate journey over cosmic time. The process of galaxy formation begins soon after the Big Bang, with slight fluctuations in the density of matter in the primordial universe. These tiny deviations set off a chain reaction, leading to the gradual accumulation of matter and the formation of gas clouds. Under the force of gravity, these clouds collapsed, leading to the formation of the very first stars. Around these young stars, galaxies began to take shape, marking the onset of the protogalactic phase. During the protogalactic phase, galaxies are not static. They are dynamic entities, engaging in a variety of processes that alter their structure. One of the most significant processes is galactic mergers, where two or more galaxies collide. These collisions can trigger bursts of star formation and alter the galaxy's morphology, such as transforming a spiral galaxy into an elliptical one. As galaxies mature, their star formation slows down. This is particularly evident in older galaxies, where the gas required for new star formation becomes increasingly depleted. These galaxies gradually evolve into what we recognize as elliptical galaxies, which often have a smooth, rounded shape and fewer new stars being formed. Some galaxies, particularly those in densely packed clusters, undergo processes like strangulation, where they lose their gas supply, stifling further star formation. Over time, this can cause them to fade into more passive, less dynamic states. However, even as galaxies grow older and quieter, they continue to interact with their cosmic neighbors. These interactions can lead to further mergers or the transfer of material between galaxies, enriching the evolving narrative of each galaxy. The cosmic dance of galaxies is never truly over. It lasts billions of years, constantly shifting and evolving as galaxies change their appearance and occasionally their very essence. The study of distant galaxies allows astronomers to look back in time, offering a window into the origins and evolution of the universe. The light from these galaxies takes billions of years to reach Earth, meaning that when we observe these distant objects, we are seeing them as they were in the distant past. Many of the galaxies that we observe today are hundreds of millions or even billions of years old, allowing researchers to piece together the timeline of cosmic history. These observations provide invaluable clues about the processes that have shaped the universe, from the formation of galaxies to the evolution of stars and the distribution of matter. By studying the light emitted by distant galaxies, scientists can gain insights into the conditions that existed in the early universe. The light spectra emitted by these galaxies reveal a wealth of information about their composition, age, and structure. Early galaxies, formed when the universe was still young, hold key details about the distribution of matter and the formation of the first stars. As these stars ignited, They produced heavier elements, which were then scattered into the surrounding space, enriching the material available for the creation of new stars and planets. This chemical evolution is crucial for understanding how the universe transformed over time. The study of distant galaxies allows scientists to trace how these elements spread throughout space, offering clues about the history of stellar and planetary formation. Furthermore, these distant galaxies are not just time capsules. They also offer a unique perspective on the nature of dark matter and dark energy, two of the most mysterious and elusive components of the cosmos. By analyzing the distribution of galaxies across vast distances, astronomers can infer the effects of dark matter, which cannot be seen directly, but whose presence is inferred by its gravitational influence on visible matter. One of the most exciting aspects of galaxy evolution is the process of galactic mergers. When two galaxies collide, the gravitational forces between them lead to dramatic interactions, causing a reshuffling of stars, gas, and dark matter. This chaotic process can significantly alter the structure of both galaxies, often resulting in a new, more massive galaxy. A spiral galaxy, for example, can be transformed into an elliptical galaxy due to the gravitational disturbances caused by the merger. The merging of galaxies also has profound effects on star formation. As the two galaxies interact, clouds of gas and dust are compressed, often triggering bursts of new star formation. These periods of intense star birth are known as starburst phases, where stars are born at a much higher rate than normal. However, this phase is typically short-lived. After the merger, as the galaxies settle into their new structure, star formation slows down, and the galaxies enter a more stable, less active phase. The consequences of galactic mergers extend beyond star formation. They can also influence the supermassive black holes at the centers of galaxies. When galaxies merge, their black holes can come closer together, eventually merging into a single, larger black hole. This process can generate intense gravitational waves, ripples in space-time that travel across the universe, offering a glimpse into the mysterious nature of these cosmic powerhouses. The study of these galactic mergers and their aftermath provides critical insights into the evolution of galaxies, the role of dark matter, and the behavior of dark energy. Through this ongoing research, we continue to unravel the grand narrative of the universe's formation, evolution, and ultimate fate. In the vast expanse of the cosmos, the final destiny of merging galaxies is profoundly shaped by their initial conditions and the angle at which they collide. The fate of these galaxies can take several paths. Some may merge into a larger, stable galaxy, while others may evolve into new, distinct galactic structures. There are even instances where these mergers act as catalysts for further cosmic collisions, sparking a chain reaction of galactic transformations. Every time galaxies collide, they tell a story of cosmic evolution, revealing a universe that is in a constant state of change, an intricate and ever-expanding tapestry woven from threads of creation and destruction. One of the most enigmatic phenomena in the universe is the black hole, a region in space where gravity is so intense that nothing, not even light, can escape. This is why black holes appear as dark, inky voids against the backdrop of the stars and galaxies. Surrounding each black hole is a boundary known as the event horizon, which marks the point of no return. Once any object crosses this threshold, it is pulled inexorably inward, destined to be swallowed by the black hole's immense gravitational pull. The life cycle of a black hole typically begins with a massive star. Stars, which are born from clouds of gas and dust, rely on the process of nuclear fusion to fuel their existence. Throughout their lifetime, these stars burn through vast amounts of helium and other elements, eventually becoming supergiants. When these stars reach the end of their lives, they experience an explosive finale known as a supernova. When the nuclear fuel of a massive star is exhausted, the star can no longer support itself against the relentless force of gravity, causing it to collapse in on itself. The core of the star may then collapse even further into a black hole if it is sufficiently massive. While this is one of the most common ways black holes are formed, they can also arise through other means, such as the merger of two neutron stars or the collision of smaller black holes. When these massive objects collide, they can create an even more powerful black hole, intensifying the gravitational pull and further contributing to the overall population of black holes in the universe. Some scientists speculate that supermassive black holes that contain millions to billions of times the mass of our Sun, may exist at the centers of nearly all large galaxies, including our own Milky Way. The study of black holes challenges the very foundations of physics, pushing the limits of our understanding of space, time, and the fundamental nature of the universe. These cosmic giants, though they may seem alien and incomprehensible, are essential components in the cosmic ballet of creation and destruction. As we continue to explore the mysteries of black holes, we gain a deeper understanding of the universe's evolution, the behavior of matter under extreme conditions, and potentially even the discovery of new physics that transcend our current comprehension. Detecting and studying black holes presents a unique challenge. Because black holes do not emit light, they are effectively invisible to traditional telescopes. However, scientists have developed sophisticated techniques to infer the presence of black holes through their gravitational influence on surrounding objects. One of the primary methods for identifying black holes involves observing the motion of nearby stars. When a star orbits an unseen object, its movement can provide key clues about the mass of the object. For example, if a star appears to be moving rapidly in space, but there is no visible companion, it suggests that a black hole might be lurking just out of sight. Another approach to detecting black holes involves studying the radiation emitted by the accretion disks that form around them. As matter falls into a black hole, it spirals around and forms a glowing disk. This material heats up to incredibly high temperatures due to friction and gravitational forces, causing it to emit radiation in the form of X-rays. Specialized space telescopes can detect these high-energy emissions, giving scientists valuable insights into the black hole's mass, spin, and overall behavior. These observations are crucial for advancing our understanding of the fundamental physics at play in these extreme environments. One of the most significant breakthroughs in black hole research came with the Event Horizon Telescope's historic capture of the first ever image of a black hole. This remarkable achievement not only provided visual confirmation of black holes' existence, but also marked a new chapter in the study of these elusive objects. By using advanced imaging techniques, scientists were able to observe the event horizon of a supermassive black hole located at the center of the galaxy M87, a momentous event that has revolutionized our understanding of these cosmic giants. Black holes come in various sizes and types, primarily categorized into stellar black holes and supermassive black holes. Stellar black holes form when a massive star collapses after exhausting its nuclear fuel, producing a black hole with a mass ranging from about 3 to 25 times that of our Sun. These black holes are scattered throughout galaxies, often found in binary systems where they interact with companion stars, drawing in material and emitting energy in the process. Supermassive black holes, however, are in a league of their own. Found at the centers of galaxies, these black holes can contain masses ranging from millions to billions of solar masses. The formation of these colossal objects remains an area of active research. Some scientists hypothesize that supermassive black holes may have formed from the merger of numerous smaller black holes or from the collapse of enormous clouds of gas in the early universe. The immense gravitational pull of these supermassive black holes influences the orbits of nearby stars and plays a key role in shaping the dynamics of galaxies. The fascinating part is how these two types of black holes interact with their environments. Stellar black holes, while formidable, typically only influence their immediate surroundings, mostly affecting the stars in their close vicinity. On the other hand, supermassive black holes have the ability to shape entire galaxies. As matter spirals into a supermassive black hole, it forms an accretion disk that radiates high-energy emissions, often observed as quasars, some of the brightest objects in the universe. These phenomena reveal the profound influence supermassive black holes have on their galaxies, dictating not only their structure but also their evolution. Recent advancements in observational technology have allowed us to gain a better understanding of these different types of black holes. Stellar black holes are often identified through their interactions with visible stars, while supermassive black holes have been detected by observing the motion of stars orbiting around them. However, the mystery of how these black holes form and evolve continues to drive astrophysical research, reminding us of the vast complexity of our universe. At the core of every black hole lies an incredible gravitational force, one so powerful that it can affect everything in its path. This force is capable of drawing in gas, dust, and even entire stars, leading to the creation of an accretion disk, a swirling mass of material that gradually spirals into the black hole. As this matter accelerates and heats up, it emits radiation that can sometimes outshine entire galaxies. The radiation emitted by accretion disks can have far-reaching effects on the surrounding environment. It can influence the formation of new stars, either triggering the collapse of nearby gas clouds into stars, or preventing star formation by dispersing the gas and dust. This delicate balance between creation and destruction highlights the ongoing cycle of life and death in the cosmos, a reminder that the universe is constantly in flux, shaped by the gravitational forces exerted by black holes and the cosmic processes they drive. Black holes, far from being passive, are anything but static entities. In fact, they are incredibly dynamic, constantly interacting with their surroundings in ways that shape the cosmos around them. A fundamental way they engage with their environment is through the processes of stellar winds and galactic jets. When a black hole begins to accrete matter, pulling in gas, dust, or even entire stars, it doesn't just keep that matter to itself. Instead, it launches incredibly powerful jets of particles from its poles, shooting them outward at nearly the speed of light. These jets are not mere bystanders in the universe. They play a critical role in influencing the interstellar medium, the vast, sparse matter that fills the space between stars and galaxies. These jets, often carrying enormous amounts of energy, can alter the dynamics of entire galaxies. They help sculpt the evolution of galaxies, injecting energy into the galaxy's surrounding gas, affecting star formation rates, and contributing to the overall galactic environment. But this is just the tip of the iceberg when it comes to understanding black holes' role in the universe. In densely populated regions of the cosmos, particularly in the centers of galaxies, supermassive black holes have an even greater impact. These titanic black holes can stretch their influence across mind-boggling distances, extending their gravitational reach over vast swaths of space. One of the ways this manifests is through their ability to alter the orbits of stars in their vicinity. Supermassive black holes can warp the structure of their host galaxies, sometimes affecting entire galactic rotations and the distribution of matter across billions of stars. Their gravitational pull is so profound that it is as if the black hole is the central axis around which the entire galaxy orbits. This relationship between black holes and their surrounding environments highlights just how integral black holes are in the cosmic dance that shapes galaxies and, by extension, the larger structure of the universe. These interactions underline the concept that black holes are not just remnants of dying stars, but are active, dynamic participants in the ongoing creation and destruction of the universe. When we delve deeper into the heart of black holes, however, we encounter a region where our conventional understanding of physics falls apart. At the event horizon, the point beyond which nothing, not even light, can escape, the laws of gravity become infinitely strong. In this extreme environment, current models of physics no longer function as they should. This is where the laws of quantum mechanics and general relativity seem to collide, and where the enigma of the black hole lies. Understanding this intersection is one of the most significant challenges in modern science, as physicists continue their search for a unified theory that could reconcile these two pillars of our understanding of the universe. One of the biggest unsolved puzzles revolves around the nature of black hole entropy and the fate of information that falls into them. According to quantum mechanics, information is supposed to be preserved, but when matter is swallowed by a black hole, it seems to be lost, effectively erased from existence. This creates what is known as the information paradox. How can information vanish if the laws of quantum physics demand that it cannot? This paradox has sparked countless debates among researchers who are exploring various theoretical solutions. Some suggest that this information might be encoded on the black hole's event horizon, while others believe it may somehow be preserved in quantum fluctuations. However, despite intense scrutiny, a comprehensive resolution remains elusive. Beyond these theoretical concerns, black holes may hold the keys to understanding some of the universe's most profound mysteries. Dark matter and dark energy, the invisible forces that govern the cosmos, remain largely unexplained. These mysterious entities play a pivotal role in the structure and evolution of the universe, but their true nature is still unknown. Some theorists propose that black holes, in their complex interactions with matter and energy, could provide vital clues to unraveling the secrets of dark matter and dark energy. Theories abound that suggest black holes could help us understand the origins of these forces, or even be intrinsically linked to their existence. Despite their enigmatic nature, black holes are more than just the final resting place of dying stars. They are laboratories for understanding the very fabric of the universe itself. By studying their formation, behavior, and the vast effects they have on their environments, scientists hope to unlock some of the deepest secrets of the cosmos. As our technology advances, and we learn to probe these celestial objects in greater detail, we may find that black holes are not just strange phenomena at the center of galaxies, but essential players in the cosmic evolution that shapes everything we know. The ultimate fate of black holes presents one of the most profound unsolved mysteries in modern astrophysics. It is well established that black holes emit a form of radiation known as Hawking radiation, a theoretical prediction proposed by physicist Stephen Hawking in 1974. According to this theory, black holes can gradually lose mass and energy over time, eventually leading to their slow evaporation. However, the timescales for this process are so staggeringly long that they far exceed the age of the universe itself. As a result, this phenomenon remains well beyond our observational reach. This raises an intriguing question. Will black holes eventually disappear entirely, leaving behind nothing but a vacuum, or will they leave some kind of residual remnant? The answers to these questions could profoundly alter our understanding of the universe's most fundamental laws, and potentially even reshape our conception of space and time. These speculative fates of black holes are intricately tied to the larger narrative of cosmic evolution, offering the potential to reveal secrets of the cosmos that we are only beginning to approach. In parallel to the black hole enigma, there exists another profound mystery within our universe: dark matter. Despite accounting for about 27% of the universe's total mass and energy content, dark matter remains one of the most elusive and enigmatic components of our cosmic landscape. The term dark in its name is quite fitting, as dark matter does not emit, absorb, or reflect light, making it entirely invisible to our current observational instruments. Its presence was first inferred through the strange motions of galaxies, particularly at their outer edges. When astronomers studied the rotation of galaxies, they observed that stars situated on the outskirts of galaxies were spinning at speeds much higher than what should have been possible given the visible matter in those galaxies. If only the visible mass, such as stars, gas, and dust, were at play, these outer stars should have been flung into space due to their rapid motion. To explain this, scientists hypothesized the existence of a hidden form of matter that exerted a gravitational pull but remained invisible. This unseen substance, which we now call dark matter, was thought to be responsible for the unexpected gravitational forces keeping these stars in place. Further compelling evidence of dark matter's existence came from the study of galaxy clusters. Using the technique of gravitational lensing, where light from distant objects is bent by the gravity of a massive object in the foreground, scientists discovered that the total mass of galaxy clusters far exceeded what could be accounted for by visible matter alone. These observations indicated that the bulk of mass in these clusters was unseen, further supporting the theory of dark matter. The nature of dark matter, however, remains unknown. Researchers continue to explore various possibilities, including the existence of weakly interacting massive particles, WIMPs, along with other hypothetical particles that might hold the key to understanding this mysterious substance. Though dark matter remains elusive, its gravitational influence on galaxies and galaxy clusters plays an essential role in the structure and evolution of the cosmos. Yet, dark matter is not the only cosmic mystery that continues to puzzle scientists. Alongside it exists dark energy, another unseen force that permeates the universe and exerts a powerful influence on its large-scale behavior. While dark matter is a force that attracts and holds matter together, dark energy is a mysterious phenomenon that causes the universe to expand at an accelerating rate. Dark energy is thought to account for a staggering 73% of the total mass energy content of the universe. This discovery, which was made in the late 20th century, dramatically reshaped our understanding of cosmic dynamics. Rather than slowing down as gravity would predict, the expansion of the universe is speeding up, driven by the repulsive force of dark energy. This phenomenon defies the gravitational pull of dark matter, visible matter, and other forces that would otherwise slow the universe's expansion. The discovery of dark energy has raised a multitude of questions. Why does this enigmatic force dominate the universe, especially when ordinary matter and dark matter are necessary for forming structures like galaxies and stars? While several theories have been proposed to explain dark energy, none have achieved widespread consensus. Some scientists suggest that dark energy could be a property of space itself, perhaps related to the so-called vacuum energy inherent in the fabric of space-time. Others speculate that it could be the manifestation of a new, unknown field or particle, one that operates at the most fundamental levels of the cosmos. The reality of dark energy challenges our very understanding of physics, and its implications stretch far beyond the expansion of the universe, offering potential insights into the ultimate fate of all things in the cosmos. Despite their invisibility, both dark matter and dark energy are integral to the overall structure and evolution of the universe. Together, these forces shape the large-scale architecture of the cosmos, influencing the formation of galaxies, the clustering of galaxy groups, and the expansion of the universe itself. Without dark matter, galaxies and clusters would not be bound together. Without dark energy, the universe would not be expanding at the accelerated rate we observe today. The investigation into these cosmic components is at the forefront of contemporary astrophysical research, and scientists are employing a range of innovative methods to study their effects. One of the primary ways in which researchers study dark matter is by examining its gravitational influence on visible matter. While dark matter cannot be seen directly, its presence is inferred by observing the motion of galaxies and galaxy clusters. For instance, when astronomers measure the rotational speeds of galaxies, they find that the visible mass does not provide enough gravitational pull to keep the stars in the outer regions from flying off into space. This discrepancy can only be explained by the presence of dark matter, which acts as an invisible source of additional gravity. Gravitational lensing also provides crucial information. By studying the bending of light from distant galaxies as it passes through massive galaxy clusters, astronomers can map out the distribution of dark matter across the universe. Dark energy, on the other hand, is studied primarily through its effect on the expansion of the universe. The observation that the universe's expansion is not only continuing but accelerating has been a key piece of evidence supporting the existence of dark energy. The distance at which galaxies are receding from us and the rate at which they are doing so can be measured through the study of distant supernovae. These cosmic explosions, which have a known intrinsic brightness, serve as standard candles to calculate distances and measure the rate of expansion of the universe. Space missions like the European Space Agency's Euclid and NASA's Wide Field Infrared Survey Telescope, WF-IRST, are specifically designed to gather data on cosmic structures and improve our understanding of dark energy. These missions will enable scientists to probe the universe on an unprecedented scale, providing critical insights into the nature of both dark energy and dark matter. Though dark matter and dark energy are two of the greatest unsolved mysteries in modern cosmology, they are also key to understanding the universe as a whole. As technology and observational techniques continue to advance, scientists are getting closer to unveiling the secrets behind these elusive phenomena. One day, perhaps, the mysteries of dark matter and dark energy will no longer be hidden in the shadows, but will instead illuminate our deepest understanding of the cosmos itself. Dark matter and dark energy are two of the most enigmatic and profound aspects of our universe, occupying a central place in the ongoing quest for cosmic understanding. These two forces, invisible to direct observation, dominate the universe's structure and evolution in ways we are still working to fully comprehend. Their investigation is not just confined to abstract theories, but is grounded in real-world observations, massive simulations, and large-scale cosmic surveys. One such endeavor is the Sloan Digital Sky Survey, SDSS, a project that maps vast regions of the universe, uncovering patterns and structures that offer crucial insights into the cosmic puzzle. Through these expansive surveys, scientists capture vast amounts of data, such as galaxy distributions and the cosmic microwave background radiation, CMBR, which provide essential clues about how dark matter and dark energy shape the universe. By merging this observational data with theoretical models, researchers continue to peel back the layers of these cosmic mysteries. With each new piece of evidence, they inch closer to unlocking the secrets of dark matter and dark energy, one of the greatest enigmas in modern astrophysics. The relationship between these forces is at the heart of the ongoing investigation into the universe's expansion, which stands as a key topic intertwining both observational data and theoretical speculation. At the forefront of this exploration is dark energy, an invisible force believed to make up approximately 70% of the universe's total energy content. Its most striking feature is its role in driving the accelerated expansion of the universe. Rather than acting as a gravitational force that pulls objects together, dark energy acts as a kind of repulsive pressure, pushing galaxies apart at an increasing rate. The most compelling evidence for this acceleration comes from observations of distant supernova and the cosmic microwave background radiation. These observations suggest that the expansion of the universe is not merely continuing at a steady pace, but that it is speeding up over time, a phenomenon that has challenged our understanding of gravitational forces in the cosmos. Dark matter, while also invisible, behaves very differently. Making up roughly 25% of the universe, dark matter cannot be directly observed through traditional means, but its presence is inferred from its gravitational effects on visible matter, radiation, and large-scale cosmic structures. Unlike dark energy, dark matter has a gravitational pull that slows down the expansion of the universe at smaller scales. Within galaxies, dark matter provides the necessary gravitational glue to keep the stars and other visible matter bound together. Without it, galaxies would fly apart due to their high rotation speeds, but dark matter's influence prevents this from happening. At larger cosmic scales, dark energy dominates, causing accelerated expansion. Thus, the interplay between dark matter's stabilizing influence and dark energy's expansive force creates a delicate balance within the cosmos. This cosmic tension between dark matter and dark energy shapes the structure and evolution of the universe. Dark energy accelerates the expansion of the universe, pushing galaxies away from each other, while dark matter holds galaxies together, preventing them from being torn apart. Over time, this dynamic has sculpted the vast networks of galaxy clusters and filaments that we see today, forming the so-called cosmic web. This balance between expansion and gravitational pull has profound implications for the ultimate fate of the universe and its large-scale evolution. As researchers probe deeper into the nature of these two cosmic components, they are confronted with fundamental questions about the very fabric of reality itself. What exactly are dark matter and dark energy made of? How do these forces interact with the visible matter that makes up the stars, planets, and galaxies we observe? And what role will these forces play as the universe continues to evolve, expanding at an ever-increasing rate? These are just some of the profound questions that continue to drive the exploration of the universe's most mysterious components. Each discovery unravels a little more of the cosmos, but the deeper we look, the more we realize how much more there is to understand. The ongoing investigation into dark matter and dark energy not only seeks to explain the mechanics of cosmic expansion, but also challenges our most fundamental assumptions about the nature of the universe. As new technologies and methodologies continue to evolve, scientists are optimistic that they will one day unlock the secrets of dark matter and dark energy, revealing the true nature of the cosmos. As of now, though, these two forces remain deeply mysterious, occupying the frontiers of astrophysical research and our understanding of the universe itself. Interestingly, the visible matter that makes up stars, planets, and galaxies constitutes only a small fraction of the total energy content of the universe. Current hypotheses suggest that dark matter, an invisible substance that does not emit, absorb, or reflect light, accounts for approximately 25% of the universe. Despite being invisible, dark matter's gravitational effects are detectable, and it is crucial in shaping the structure of galaxies. Observations of spiral galaxies, for instance, show that their stars spin at such high velocities that without dark matter's invisible mass, these galaxies would simply fly apart. In essence, dark matter acts as a kind of cosmic glue, holding these massive structures together and providing the necessary gravitational framework for the universe's large-scale structure. The true nature of dark matter, however, remains elusive. Over the years, various candidates have been proposed, with one of the leading hypotheses being that dark matter consists of weakly interacting massive particles, WIMPs. These theoretical particles would interact with normal matter only through gravity, making them exceedingly difficult to detect with current technology. Other possibilities include particles known as axions or sterile neutrinos, but none of these candidates have yet been confirmed. Despite this, the search for dark matter continues, engaging scientists across the globe in a concerted effort to uncover its secrets. As new detectors and observational methods are developed, the hope is that one day we will directly detect dark matter and finally understand what it is made of. Alongside dark matter, dark energy constitutes roughly 70% of the universe, and its role in the accelerated expansion of the cosmos is equally mysterious. While gravity is typically associated with pulling matter together, dark energy behaves in the opposite way. It seems to push galaxies apart, accelerating the expansion of the universe in a manner that defies intuition. The leading hypothesis is that dark energy is a property of space itself, potentially related to the cosmological constant, a concept originally proposed by Albert Einstein as part of his theory of general relativity. Another theory suggests that dark energy may be connected to a field known as quintessence, which permeates the universe and evolves over time, potentially behaving differently in different epochs of cosmic history. Regardless of its exact nature, dark energy remains one of the most profound and puzzling mysteries in modern astrophysics, pushing the boundaries of our understanding of the universe. As research in this field continues to advance, scientists are hopeful that new technologies and discoveries will help to untangle the mysteries of both dark matter and dark energy. Each new breakthrough brings us closer to understanding the true structure of the universe, the forces that shape its evolution, and the very fabric of reality itself. In the midst of these cosmic forces, stars, those dazzling, burning spheres of gas, form and die in cycles that have profound implications for the evolution of the universe. Stars are born from vast clouds of gas and dust, known as nebulae, which serve as the raw material for stellar formation. These nebulae are often seen as colorful, beautiful clouds in images captured by telescopes, but within these clouds lies the potential for new stars to form. When regions within a nebula become dense enough, small gravitational forces begin to pull the matter together. Over time, these clumps of gas and dust increase in density, and the gravitational pull strengthens. As the material continues to collapse, the temperature and pressure at the core rise significantly. Eventually, when the temperatures reach high enough levels, nuclear fusion begins, marking the birth of a new star. This process of star formation can take millions of years, with the nebula slowly evolving into a new celestial body. Interestingly, not every part of a nebula leads to the formation of a star. Some regions may form protostars, early pre-stellar stages, but may not gain enough mass to ignite nuclear fusion. Star formation often occurs in clusters, meaning multiple stars can be born from the same nebula at the same time. This clustering process is crucial in understanding how stars evolve and how their lifespans are determined. As these newly formed stars shine brightly, they also influence their surrounding environment. The energy they emit heats the remaining gas within the nebula, which can trigger further star formation. This ongoing cycle of creation and destruction highlights the dynamic and interconnected nature of the cosmos. Nebulae not only act as stellar nurseries, but they also serve as windows into the life cycle of galaxies and the broader universe. Through the study of nebula, we gain insight into the fundamental processes that drive the evolution of stars and galaxies, offering a glimpse into the eternal dance of creation that defines the cosmos. The lifespan and fate of a star are determined primarily by its mass. Stars begin their lives within nebulae, where vast clouds of gas and dust come together under the force of gravity. Once nuclear fusion ignites in the core, the star enters its main sequence phase, where it shines by converting hydrogen into helium and releasing tremendous amounts of energy. This process is the driving force behind the star's existence, as it powers the star and allows it to shine for millions or even billions of years. Depending on their mass, stars will evolve in different ways, with the most massive stars eventually undergoing supernova explosions, while smaller stars may evolve into white dwarfs or even black holes. Each phase in a star's life contributes to the ongoing cycle of stellar birth and death, shaping the universe in profound and lasting ways. The life cycle of a star is shaped by its mass, a force so significant that it dictates its temperature, luminosity, and the pace at which it burns through its nuclear fuel. From the birth of a star in the vast, gas-filled nurseries of space to its ultimate death, the entire journey is a reflection of the powerful forces at play within the universe. While all stars are born from the same cosmic materials, not all stars follow the same path. The mass of a star is the key determinant in how it will evolve, live, and die. For the most massive stars, those that are several times more massive than our own sun, their journey is brief but intense. These stars live fast and burn hot, consuming their fuel in mere millions of years. Their fate is an extraordinary spectacle, a supernova explosion. A supernova occurs when these stars reach the end of their lives and undergo a catastrophic collapse of their cores. This event releases a shockwave of energy, brighter than the entire galaxy for a short period of time, while scattering elements that were forged in the star's core into the surrounding space. These elements, from carbon to oxygen to iron, will serve as the building blocks for future generations of stars, planets, and potentially life itself. After the explosion, the remnants of the star's core may condense into a neutron star, or if the star was massive enough, collapse further into a black hole. These are some of the most exotic and dense objects in the universe. On the other hand, smaller stars like our Sun experience a far more measured, less explosive existence. These stars can burn steadily for billions of years. As they begin to exhaust their hydrogen fuel, the core contracts and the outer layers expand, causing the star to swell into a red giant. At this stage, the star begins to fuse helium into heavier elements, but the changes do not stop there. As the red giant phase reaches its end, the outer layers of the star are ejected gently into space, creating a beautiful planetary nebula. What remains is the dense, cooling core, which becomes a white dwarf, a dim, stable remnant of its former self. Over the course of billions of years, this white dwarf will slowly cool and fade, leaving behind a quiet legacy in the cosmic narrative. The tale of a star is ultimately a story of mass. Its mass dictates its fate. Massive stars blaze brightly and end with the violent spectacle of a supernova, while smaller stars take a more peaceful route, evolving into red giants before shedding their outer layers and leaving behind a white dwarf. These two contrasting fates exemplify the underlying physics of stellar evolution, as well as the dynamic, sometimes violent nature of the universe itself. At the beginning of a star's life, it emerges from a giant cloud of gas and dust known as a stellar nursery. Gravity causes parts of this cloud to collapse in on themselves, forming clumps that heat up and ignite nuclear fusion at their cores. This marks the birth of a star. But how this star will continue to evolve depends largely on its mass. Smaller stars, such as the Sun, will eventually exhaust their hydrogen fuel. When this happens, their cores contract and heat up, while their outer layers expand dramatically, transforming them into red giants. This red giant phase can last for millions or even billions of years. During this time, the star begins to fuse helium into heavier elements. The outer layers, having expanded far beyond their original size, will eventually be shed into space. The ejected material forms what is known as a planetary nebula, a beautiful cloud of gas and dust that may be illuminated by the remaining core, which has become a white dwarf. White dwarfs are stable, though they are far dimmer than the stars they once were. Over billions of years, these remnants will gradually cool and fade away, leaving nothing but a faint trace of the star's former glory. In contrast, the fate of more massive stars is far more dramatic. After exhausting their nuclear fuel, the core of these stars collapses under the immense force of gravity. The outer layers of the star are flung outwards in a violent supernova explosion. This catastrophic event releases an enormous amount of energy, briefly outshining entire galaxies. The elements created within the star's core, along with those formed in the heat of the explosion itself, are scattered across space, enriching the cosmos with materials that will eventually form new stars, planets, and possibly life. Depending on the mass of the collapsing core, it may become a neutron star, a dense, compact remnant with an incredibly strong magnetic field, or if it's massive enough, it may collapse further into a black hole, an object with such intense gravity that not even light can escape it. This explosive death of a star is not just a spectacular event in itself, it also plays a crucial role in the cycle of matter throughout the universe. The elements during a supernova provide the essential building blocks for new stars and planets. Most of the elements we rely on for life, such as carbon, oxygen, and iron, were created in the cores of ancient stars and distributed across the cosmos during these supernova explosions. Without these events, the universe would be a far simpler, less diverse place. The rich variety of elements we find in our own planet and the very conditions necessary for life to exist owe their existence to the cosmic recycling of star material. The diverse fates of stars, ranging from the quiet fading of white dwarfs to the explosive power of supernova, demonstrate the intricacies of stellar evolution. These events not only illuminate the spectacular processes that govern the birth, life, and death of stars, but also reveal the interconnectedness of all cosmic phenomena. From the ashes of dead stars arise the very elements that give rise to new stars, planets, and even life. This continuous cycle, marked by the death and rebirth of stars, underscores the profound and ongoing evolution of the universe. In the end, stars, regardless of their size or mass, are not simply born, live, and die in isolation. They are part of a grand cosmic narrative that spans billions of years and extends beyond the stars themselves. From the birth of a star in a stellar nursery to its fiery end in a supernova or its peaceful demise as a white dwarf, each stage of a star's life contributes to the ever-evolving story of the cosmos, enriching the universe with elements that will form new worlds, new stars, and perhaps new forms of life. The life cycle of a star is, therefore, a reflection of the universe itself, ever-changing, ever-growing, and infinitely interconnected. The shock waves produced by a supernova are not merely the aftermath of a stellar death, but rather they can act as cosmic catalysts for the formation of new stars. As these shock waves travel across the vast expanse of the interstellar medium, they compress clouds of gas and dust, creating dense regions where gravity takes hold. These areas, under their own weight, can collapse in on themselves, initiating the process of star formation. Essentially, supernovae become the universe's recycling mechanisms, turning the remnants of older stars into the raw materials for the birth of new celestial bodies. Through this process, they facilitate the continuous transformation of elements, passing them from one generation of stars to the next. The life cycle of matter in the universe becomes a seamless cycle of birth, death, and rebirth, each phase interconnected with the other. This cosmic rhythm ensures not only the continuity of material across time, but also the evolution of the cosmic landscape itself. In the vastness of space and time, this cycle serves as a grand narrative, weaving together the fates of stars, planets, and galaxies. One of the most remarkable outcomes of this stellar rebirth is the formation of neutron stars, some of the most fascinating objects in the universe. These extraordinary, ultra-dense remnants are what remain after massive stars exhaust their nuclear fuel and end their lives in cataclysmic supernova explosions. When the core of such a star collapses, it does so with an incredible force, compressing the matter into a space so small that atomic structure itself breaks down. During this collapse, protons and electrons fuse together to form neutrons, creating a star composed almost entirely of these subparticles. The result is an object of mind-boggling density. A single teaspoon of neutron star material would weigh as much as an entire mountain. This extreme density is what gives neutron stars their name and underscores the violent processes that produce them. Neutron stars exist in some of the most extreme environments known to humanity. Their magnetic fields can be millions of times stronger than Earth's, and these intense fields can accelerate charged particles to nearly the speed of light. As these particles move along the star's magnetic lines, they emit beams of radiation that sweep across space. If these beams are directed toward Earth, we observe them as pulses, a phenomenon that has earned neutron stars the name pulsars. These pulsating stars have become invaluable tools for scientists, providing rare insights into the fundamental laws of physics under conditions that cannot be replicated on Earth. A neutron star's existence can take many forms, especially if it resides in a binary system, where it may begin to accumulate material from a companion star. As this material is drawn toward the neutron star, it can trigger even more dramatic phenomena, such as intense bursts of X-rays. In some cases, the accumulation of mass may even lead to the formation of a black hole, an object so dense that not even light can escape its gravitational grip. This dynamic cycle of stellar evolution presents both challenges and opportunities for our understanding of the universe. Neutron stars continue to push the boundaries of physics, offering up new mysteries and questions for scientists to explore. Pulsars, a type of neutron star, are often referred to as cosmic lighthouses because of their regular, rhythmic emissions of electromagnetic radiation. These stellar remnants spin at incredibly fast rates, and as they emit beams of radiation from their magnetic poles. These beams sweep through space, much like the light from a lighthouse sweeping across the dark ocean. This process occurs because the magnetic poles of a pulsar are not aligned with the star's axis of rotation. As the neutron star spins, charged particles become trapped in its intense magnetic fields and are accelerated to nearly the speed of light. The resulting radiation is emitted in pulses, with the regularity of the pulses depending on the pulsar's rotation speed. Some pulsars rotate several times per second, while others emit pulses every few milliseconds. These pulsations allow astronomers to measure the pulsar's rotation period with remarkable precision. In fact, some pulsars are so accurate that they rival atomic clocks in their ability to keep time. This precision makes pulsars powerful tools for testing theories of gravity, studying the behavior of matter in extreme conditions, and even probing the fabric of space-time itself. Every new discovery related to pulsars brings us a step closer to understanding the fundamental forces that govern the universe. Quasars, short for quasi-stellar objects, are among the brightest and most mysterious phenomena in the cosmos. Powered by supermassive black holes that reside at the centers of distant galaxies, quasars emit an incredible amount of energy as matter is drawn toward these black holes. As the matter spirals inward, it forms an accretion disk, an energetic whirlpool where friction and intense gravitational forces generate immense heat and light. This process can produce radiation across the entire electromagnetic spectrum, making quasars visible across vast distances. Some quasars are so bright that they can outshine entire galaxies, emitting as much light as hundreds of billions of stars combined. This extraordinary luminosity allows astronomers to study quasars even from billions of light years away, providing a window into the distant past of the universe. The light from a quasar carries with it information about the early conditions of the universe, revealing clues about the formation of galaxies, the evolution of supermassive black holes, and the nature of the gas and dust that existed just a few billion years after the Big Bang. By analyzing the light from quasars, scientists can learn about the composition and temperature of the material being consumed by the black hole and how it moves and interacts with its surroundings. In essence, quasars serve as beacons from the past, helping us to understand the formation and evolution of the universe itself. Similarly, gamma-ray bursts, GRBs, are some of the most energetic and luminous events ever observed. These explosive phenomena can release more energy in just a few minutes than the sun will emit over its entire lifetime. Typically, gamma-ray bursts appear as intense flashes of gamma-ray radiation, the highest energy form of light. These bursts can be detected from billions of light years away, making them invaluable tools for studying the farthest reaches of the cosmos. There are two main types of gamma-ray bursts. The first type, long-duration bursts, lasts more than 2 seconds and is often associated with the death of massive stars. When such a star runs out of fuel, its core collapses, triggering a supernova explosion. If the collapsing star's mass is great enough, the collapse can result in the formation of a black hole. As matter spirals into this black hole, it releases powerful jets of gamma radiation. The second type of gamma ray bursts, short-duration bursts, lasts less than 2 seconds. These bursts are thought to occur when two neutron stars collide, or when a neutron star merges with a black hole. In either case, the collision generates shock waves that produce intense bursts of gamma radiation. The study of gamma ray bursts has helped to deepen our understanding of phenomena such as black hole formation, neutron star behavior, and the evolution of galaxies. Throughout history, some of the most perplexing and awe-inspiring phenomena in the universe have pushed the boundaries of scientific understanding. Black holes, with their immense gravitational forces, challenge our conception of space and time. Matter compressed into an infinitely small volume creates regions where gravity is so strong that not even light can escape. This fundamentally alters our understanding of time, space, and the very fabric of reality. The behavior of black holes is governed by the theory of general relativity, formulated by Albert Einstein, but even this theory cannot fully explain the mysteries of black holes. Additionally, the universe's largest mysteries, such as dark matter and dark energy, continue to confound scientists. Dark matter, which accounts for about 27% of the universe, remains invisible to our instruments, while dark energy, which makes up about 68% of the universe, causes the cosmos to expand at an accelerating rate. Together, these mysterious forces challenge our most basic understanding of physics, pushing scientists to reconsider existing theories and search for new particles or forces that may explain what we cannot yet see. These enigmatic aspects of the universe remind us of how much we have yet to discover about the cosmos. Quantum mechanics, with its profound complexities, offers a fresh, enigmatic layer to our understanding of the universe. The peculiar behaviors it reveals at the microscopic scale challenge the very foundation of classical physics. At this scale, particles can exist in multiple states simultaneously, a phenomenon that defies the conventional rules of physics. This strange duality, where a particle can be both here and there at the same time, raises unsettling questions about the very nature of reality. Quantum entanglement, another baffling phenomenon, presents us a scenario where two particles can become instantaneously linked, no matter the distance that separates them. This seemingly telepathic connection undermines our most basic intuition about causality and the flow of time. These quantum mysteries don't just pose philosophical dilemmas, but also highlight the deep contradictions between quantum mechanics and general relativity, two pillars of modern physics. General relativity, which governs the behavior of massive objects in the fabric of space-time itself, stands in stark contrast to the quantum world's bizarre rules. This dissonance has driven many scientists to seek a unified theory, one that can harmonize the behavior of the very large and the very small. But while theoretical physicists grapple with this complex issue, another even more perplexing challenge emerges: time itself. As researchers delve into the heart of black holes and explore the fabric of space-time, they are confronted with the possibility that time may not be a simple linear progression. This discovery has profound implications not only for how we understand causality, but for the very structure of the universe. This ongoing exploration of the cosmos is more than a quest for answers. It is an invitation to expand the boundaries of our knowledge, to rewrite the very laws that govern our existence. The deeper we peer into the mysteries of time, space, and the forces that shape them, the more our view of reality is transformed. But what was once inconceivable now seems like a tantalizing possibility. And with each new insight, the framework of physics becomes richer, more intricate, and more beautiful. As scientists continue their quest to understand these elusive phenomena, they are reshaping the way we perceive the cosmos, opening doors to knowledge that were previously closed, and challenging us to think in ways we never thought possible. One of the most fundamental forces in the universe, gravity, plays a crucial role in shaping the structure of the cosmos. This invisible force, which pulls matter together, has been a central player in the development of the universe since the very beginning. Shortly after the Big Bang, tiny fluctuations in density began to set the stage for the formation of galaxies, stars, and other cosmic structures. Areas of slightly higher mass exerted greater gravitational pull, drawing in surrounding matter and allowing the formation of larger structures over billions of years. As these clumps of matter came together, they formed galaxies, clusters of galaxies, and vast cosmic filaments, an intricate web-like structure often referred to as the cosmic web. The cosmic web consists of dense regions where galaxies are clustered together and vast voids where little matter exists. This intricate structure is maintained and strengthened by the presence of dark matter, an invisible substance that doesn't emit light but exerts a gravitational influence. Dark matter acts as a scaffolding, holding the cosmic web together and ensuring its stability. Over time, gravity has continued to influence the motion of galaxies. It pulls them closer together, sometimes causing them to collide and merge, which has significant consequences for the evolution of galaxies across the universe. As galaxies interact and merge, new structures emerge, including superclusters, vast groups of galaxies bound together by gravity. On the other hand, there are vast regions of the universe that remain almost entirely empty, illustrating gravity's role in creating cosmic voids, the sprawling emptiness between dense clusters of galaxies. Even the expansion of the universe itself is influenced by gravity. While the universe is steadily expanding, gravity works to slow down this expansion. This interplay between expansion and gravity holds the key to understanding not only the current state of the universe, but also its past and future evolution. Gravitational waves, ripples in the fabric of space-time caused by violent cosmic events, are among the most exciting discoveries in modern physics. These waves move at the speed of light, stretching and compressing space itself as they pass through. They serve as echoes of cataclysmic events, such as the collision of black holes or neutron stars, traveling vast distances across the universe and carrying with them crucial information about their origins and the fundamental nature of gravity. In September 2015, scientists made a historic breakthrough with the first direct detection of gravitational waves, a milestone that opened up an entirely new way of observing the universe. The Laser Interferometer Gravitational Wave Observatory LIGO, with its long L-shaped detectors, was the key player in this monumental discovery. LIGO detects the tiny changes in distance caused by gravitational waves, which are so subtle that they cause oscillations in the detector's arms by just a fraction of the diameter of a proton. This minute measurement is enough to detect the passing of a gravitational wave. The detection of gravitational waves came from the merger of two black holes, located approximately 1 billion light-years away. This event confirmed one of the key predictions of Einstein's theory of general relativity and provided an entirely new lens through which to view the cosmos. Since that groundbreaking discovery, LIGO and its partner observatories around the world have continued to observe numerous events, unveiling previously unseen aspects of the universe. These observations have given us insight into the lives of black holes, neutron star mergers, and even the origins of the universe itself. As scientists continue to track these cosmic ripples, they promise to unlock even greater secrets about the nature of space-time and gravity, transforming our understanding of the universe in profound and lasting ways. The study of gravity has had a profound impact on our understanding of the universe, from its early conceptualization to the groundbreaking work of Isaac Newton in the 17th century. Gravity has been central to our understanding of how celestial bodies interact. Newton's law of universal gravitation laid the foundation for understanding the gravitational pull between objects and how they affect each other. However, it was Albert Einstein's theory of general relativity that truly revolutionized our perception of gravity. Einstein's theory proposed that gravity is not a force that acts at a distance, as Newton had suggested, but rather a curvature of space and time caused by the mass of objects. This groundbreaking idea reshaped our understanding of the cosmos and laid the groundwork for modern cosmology. Imagine placing a heavy object, like a bowling ball, on a trampoline. The weight of the ball causes the trampoline's surface to dip, and smaller objects, such as tennis balls, roll toward it. In this analogy, the trampoline represents the fabric of space-time, and the bowling ball represents a massive object like a planet or star. The presence of mass causes the fabric of space-time to bend, and this curvature influences the movement of other objects. This conceptual shift not only explains the motion of celestial bodies, but also leads to predictions that Newton's laws could not account for, such as the bending of light around massive objects, a phenomenon known as gravitational lensing. Gravitational lensing has been observed multiple times and has provided scientists with unprecedented views of the cosmos. Light from distant galaxies is distorted as it passes near massive objects, such as clusters of galaxies, and this effect has been used to map the distribution of dark matter in the universe. Though Newton's laws work perfectly well for many everyday situations, and even for the majority of celestial events, general relativity offers a more complete and accurate description of the universe, especially when dealing with extreme conditions, such as near black holes, or in the vast stretches of space where massive objects influence the very fabric of space-time. In the search for deeper understanding, gravity remains a constant force guiding our exploration of the cosmos, shaping everything from the orbits of planets to the formation of galaxies and the expansion of the universe. The pursuit of knowledge about gravity and its influence on the universe continues to be one of the most exciting and transformative endeavors in modern science. As we venture further into the mysteries of the universe, gravity will undoubtedly remain an essential part of the story, shaping our understanding of the heavens above and the forces that govern the universe. When we delve into the realm of extreme gravitational fields, those found near black holes or neutron stars, the predictions of general relativity come into sharper focus. Here it is not the laws of classical physics that dominate, but rather the theory of general relativity, which provides a more accurate description of the forces at play. This theory dramatically reshapes our understanding of the universe, offering a new lens through which we can view the cosmos. As we confront these awe-inspiring phenomena, our comprehension of gravity and space itself is transformed. What once seemed like abstract concepts now becomes an intricate dance of forces, stars, and matter, forever altering how we perceive the vastness of the universe and our place within it. Gravity has always fascinated scientists, primarily because it behaves in ways that set it apart from the other fundamental forces of nature. Unlike electromagnetism, the weak nuclear force, and the strong nuclear force, gravity operates on a much larger scale and has an undeniable, pervasive presence. It governs everything from the movement of galaxies to the behavior of a falling apple. To understand how we might unify gravity with these other forces, we must first explore what unification means in the context of physics. Unification proposes that all these forces, at their most fundamental level, are expressions of a single, overarching force or theory. One leading contender in the search for this unified theory is string theory. This groundbreaking concept suggests that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings. According to string theory, the different ways in which these strings vibrate give rise to various particles, and consequently, the forces we observe, gravity included, emerge naturally from these interactions. This vision of the universe suggests that, at its core, everything is interconnected by these vibrations, and string theory has become a compelling candidate for what is known as the theory of everything. However, string theory is not without its competitors, and another exciting avenue of exploration is loop quantum gravity. Unlike string theory, which operates in a higher dimensional space to unify all the forces, loop quantum gravity focuses on the very fabric of space-time itself. It proposes that space-time is not a smooth, continuous entity, but rather is composed of tiny, discrete loops woven together like threads in a fabric. This theory aims to reconcile the grandeur of general relativity, which explains gravity on large scales, with the principles of quantum mechanics, which govern the subatomic world. While still in its early stages, loop quantum gravity offers a tantalizing glimpse into how gravity might fit into the quantum realm. In addition to these theories, many physicists are investigating grand unified theories, GUTS, which suggest that at extremely high energies, such as those that existed during the moments following the Big Bang, the electromagnetic weak and strong forces merge into one. Gravity, however, remains elusive, and scientists continue to search for ways to unify all four fundamental forces of nature, hoping that at the energy scales found near the Big Bang, such a unification might be achieved. This ongoing quest shapes much of modern physics and cosmology, driving both theoretical innovation and experimental exploration. The advent of telescopes marked a pivotal moment in our ability to understand the cosmos. Before these instruments were developed, early astronomers were limited to observing the heavens with the naked eye, and their understanding of the universe was constrained by this lack of magnification. The invention of the telescope in the early 17th century allowed humanity to peer deeper into space than ever before. One of the most famous pioneers of this new age was Galileo Galilei, who, using a relatively simple telescope, made groundbreaking discoveries such as the moons of Jupiter and the phases of Venus. These observations challenged the prevailing geocentric view of the universe, fundamentally altering our understanding of our place in the solar system. As telescope technology advanced, so too did the scope of astronomical research. By the 19th and 20th centuries, large, sophisticated optical telescopes enabled astronomers to observe fainter and more distant objects. Public observatories like Mount Wilson and Mauna Kea became centers for groundbreaking observations, allowing scientists to map our galaxy, identify nebula, and discover galaxies billions of light years away. Telescopes acted as time machines, allowing us to see light that had traveled for eons, providing glimpses into the distant past of the universe. This ability to look back in time has reshaped our understanding of cosmic evolution. In the mid-20th century, the introduction of radio telescopes brought a new dimension to our exploration of space. These instruments were capable of detecting radio waves from space, phenomena that optical telescopes could not capture. Radio telescopes revealed new cosmic structures, such as the cosmic microwave background radiation and pulsars, which are rapidly rotating neutron stars that emit beams of radio waves. This technological leap broadened our perspective on the universe, revealing not only its structure, but also the conditions that prevailed in the universe's infancy, shortly after the Big Bang. Today, space-based telescopes like the Hubble Space Telescope have taken astronomical observations to unprecedented heights. By orbiting above the Earth's atmosphere, Hubble is able to capture crystal-clear images of celestial objects, unaffected by atmospheric distortion. Hubble's contributions to science have been nothing short of revolutionary. One of its most significant achievements is its role in measuring the rate of the universe's expansion. This led to the discovery that the expansion is accelerating, a finding that has prompted scientists to investigate dark energy, a mysterious force that is now central to modern cosmology. By observing distant supernova, Hubble also helped refine the age of the universe, placing it at approximately 13.8 billion years. Moreover, Hubble provided stunning images of objects like the Pillars of Creation in the Eagle Nebula, revealing vast clouds of gas and dust where new stars are born. These breathtaking photographs not only captivate the public, but also provide essential data on the processes of star formation and the evolution of cosmic structures. Space missions have also played a pivotal role in advancing our knowledge of the universe. Human space exploration has spanned decades, and the robotic missions of today continue to expand our understanding. Some of the most significant contributions come from spacecraft that venture beyond Earth's atmosphere. Launched in 1990, the Hubble Space Telescope provided a wealth of information, capturing images of distant galaxies and shedding light on everything from star formation to the nature of black holes. The data collected by Hubble has been instrumental in measuring the universe's expansion and in exploring the enigmatic properties of dark energy. Robotic missions to other planets have also significantly enriched our understanding. The Mars rovers, for instance, have analyzed the Martian surface, searching for signs of water and investigating the planet's climate and geology. These missions have been essential in determining whether Mars could have supported life in the past, prompting scientists to rethink the potential for life in environments once thought inhospitable. The Voyager spacecraft, launched in the late 1970s, represent another remarkable achievement in space exploration. Carrying golden records with sounds and images of life on Earth, Voyager 1 and Voyager 2 have traveled beyond the reaches of our solar system, providing invaluable data on the outer planets and the vast, empty spaces between the stars. These space missions continue to deepen our understanding of interstellar space, revealing new information about the conditions and materials found beyond our solar system. As technology advances, new missions are being planned that will continue to push the boundaries of what we know about the universe. The journey to explore the cosmos remains an ongoing and essential pursuit, one that will continue to define humanity's quest for knowledge for generations to come. Hubble's exploration of exoplanets has ignited an unprecedented wave of enthusiasm in the ongoing search for extraterrestrial life. Utilizing powerful techniques like transit photometry, Hubble has uncovered the faintest signatures of exoplanet atmospheres, providing vital clues about their chemical compositions. Elements such as water vapor and carbon dioxide have been detected, further fueling the fire of scientific curiosity and the hope of finding life beyond Earth. These discoveries are not merely academic. They revitalize the field of astrobiology, encouraging deeper inquiries into the conditions that might make distant worlds habitable. With each new finding, the quest to understand humanity's place in the vast cosmos takes a step closer to clarity. The launch of the James Webb Space Telescope, JWST, in December 2021 marks a monumental leap in our ability to explore the universe. This groundbreaking instrument was designed with one primary goal: to achieve what previous telescopes like the Hubble Space Telescope could only dream of. Equipped with an extraordinarily large mirror and a suite of advanced scientific instruments, Webb's capabilities extend far beyond those of its predecessors. Most notably, its focus on infrared light allows it to peer through cosmic dust clouds and gas nebulae that typically obscure our view of distant celestial bodies. This revolutionary ability opens up exciting new pathways for understanding the universe's birth, both in terms of stars and galaxies. One of the most fascinating aspects of the JWST is its potential to capture light from the universe's earliest stars and galaxies. These ancient celestial bodies, known as Population 3 stars, are believed to have played an essential role in shaping the cosmos. By studying their light, scientists hope to answer one of the most profound questions in cosmology: how and when did the first galaxies form? These stars existed in the early universe, shortly after the Big Bang, and their study could unlock secrets that have remained hidden for billions of years. It's like peeling back the layers of a cosmic onion, slowly revealing the intricate history of our universe. Moreover, Webb's ability to study exoplanets is a game changer. The telescope's advanced instruments allow for an unprecedented analysis of exoplanet atmospheres, offering clues about their composition and potentially their habitability. With Webb, scientists can identify key molecules such as water vapor and carbon dioxide, essential building blocks for life as we understand it. This deep dive into exoplanet atmospheres has the potential to answer one of the most pressing questions of our time. Are we alone in the universe? By uncovering these chemical signatures, Webb is poised to radically transform our understanding of distant worlds and their capacity to support life. But the JWST is not just another piece of technology. It is a gateway to the mysteries of the cosmos. The sheer scale of its capabilities promises to reshape our view of reality. The telescope's ability to observe the universe through infrared light means it can see beyond the obstacles that once limited our exploration. As we continue to unlock the universe's secrets with the help of Webb, the future of space exploration has never looked more promising. We are on the cusp of discoveries that could redefine humanity's understanding of the cosmos itself. Looking forward, scientists are abuzz with excitement about emerging technologies that could open up new frontiers in space exploration. Perhaps one of the most revolutionary is the development of next-generation propulsion systems. Traditional chemical rockets, while effective, are limited in terms of speed and efficiency. To break free from these constraints, researchers are exploring alternative propulsion methods such as nuclear thermal propulsion. This new technology could drastically shorten travel times to distant destinations such as Mars, or even the moons of Jupiter and Saturn. Missions that once took months or years could be completed in a matter of weeks, unlocking incredible new possibilities for human exploration beyond Earth. In parallel with propulsion advancements, there is growing interest in-space resource utilization, a technology that could drastically improve the sustainability of space missions. As humanity ventures further into the cosmos, the ability to harness resources from other celestial bodies becomes critical. The Moon, for example, is thought to contain deposits of ice in permanently shadowed craters. This ice could be converted into water for drinking, oxygen for breathing, or even rocket fuel, thus reducing the need to send supplies from Earth. Such innovations would allow astronauts to explore deeper into the solar system with far less dependency on resources from home. Artificial intelligence, AI, is another key player in the future of space exploration. AI's potential to assist astronauts in navigating complex remote environments cannot be overstated. With communication delays inherent in deep space missions, AI could serve as an invaluable tool for making real-time decisions when immediate contact with Earth is not possible. Imagine robots equipped with advanced AI exploring the surface of Mars or even asteroids independently, sending back crude data, crucial thing experiments, while humans remain safely in orbit or on another celestial body. This technological synergy between human and machine could enable missions that were once considered too risky or complex. At the same time, advances in material science are reshaping our concept of space habitats. The harsh conditions beyond Earth's atmosphere, such as radiation and extreme temperatures, pose significant challenges to long-term human habitation. To address these threats, scientists are investigating new materials that could protect astronauts and provide safe living environments in space. Concepts like inflatable habitats or structures built from resources found on other planets are being explored as viable options for sustaining life during long-duration missions. As these technologies evolve, they will transform our ability to explore the universe and make the dream of becoming an interplanetary species ever more achievable. The search for extraterrestrial life is one of humanity's most enduring and exciting endeavors. Over the past few days, scientists have uncovered a wealth of evidence suggesting that life may exist elsewhere in the universe. One of the most compelling pieces of evidence comes from the discovery of extremophiles, organisms that thrive in extreme conditions on Earth. These resilient life forms can withstand extreme temperatures, pressures, and radiation, demonstrating that the fundamental building blocks of life can survive in environments previously thought too hostile. Furthermore, the discovery of exoplanets, planets orbiting stars outside our solar system, has significantly strengthened the case for extraterrestrial life. Thousands of these distant worlds have been identified, with many located in the so-called Goldilocks zone, the region around a star where conditions may be just right for liquid water to exist. The presence of water is considered a critical factor in the search for life, as it is one of the essential ingredients for life as we know it. Telescopes like Kepler and the Transiting Exoplanet Survey satellite, TESS, have identified numerous exoplanets that could harbor life. Mars, too, continues to provide compelling evidence in favor of extraterrestrial life. NASA missions have detected seasonal dark streaks on the Martian surface known as recurring slope lineae, which suggest the flow of briny water. This discovery, along with other findings, further enhances the likelihood that life, past or present, may have existed or could still exist on the red planet. These discoveries, both near and far, continue to fuel the imagination of scientists and the general public alike. The search for life beyond our planet has only just begun, and with each new breakthrough, we edge closer to answering one of the most profound questions humanity has ever asked. Are we alone in the universe? The exploration of Mars has been an exciting and pivotal chapter in the search for extraterrestrial life. Scientists have uncovered compelling evidence suggesting that this red planet once had a far more hospitable climate, one where liquid water flowed abundantly across its surface. Among the most intriguing pieces of this puzzle are the ancient riverbeds along with minerals that form in the presence of water, hinting at a much wetter Mars in the distant past. This ancient climate could have been ideal for microbial life, offering the potential for life to have thrived there, at least in its most basic forms. As we continue to explore Mars, the question of whether it could still host life today becomes increasingly tantalizing. While current conditions on the planet are harsh, cold, dry, and barren, the evidence of past water raises intriguing possibilities. Could there still be remnants of life lurking beneath the surface, perhaps in the form of microbial organisms that have adapted to the planet's extreme environment? The growing curiosity surrounding this question continues to drive exploration, with missions like NASA's Curiosity rover offering valuable insights into the planet's history and the search for signs of life. Beyond Mars, the search for extraterrestrial intelligence, SETI, seeks to detect signals from other civilizations that may exist elsewhere in the universe. Despite decades of scanning the cosmos for evidence of intelligent life, no definitive signals have yet been detected. Still, the sheer size and complexity of the universe keep hope alive. With billions of galaxies, each containing billions of stars, the odds seem to favor the possibility that life exists beyond Earth. Whether through the discovery of strange new environments on distant planets, the discovery of water on Mars, or the search for signals from intelligent beings, humanity's drive to answer the question, "Are we alone?" remains steadfast and determined. One of the most thrilling areas of exploration today is the search for exoplanets, planets that orbit stars outside our solar system. The discovery of these distant worlds has become one of the most exciting frontiers in astrophysics. The techniques scientists use to identify and study exoplanets are as diverse as the planets themselves. One of the most influential methods is the transit method, which involves monitoring a star's brightness over time. When an exoplanet passes front of its host star, it temporarily blocks a portion of the star's light. By measuring the dip in brightness, scientists can infer the planet's size and its distance from the star, key factors in determining whether it resides in the so-called Goldilocks zone, a region where conditions are just right for liquid water to exist, an essential ingredient for life as we know it. Another technique that has proved invaluable in the hunt for exoplanets is radial velocity, also known as the Doppler effect method. As a planet orbits its star, its gravitational pull causes the star to wobble slightly. This wobble affects the star's light spectrum, shifting it towards the red or blue end of the spectrum, depending on whether the star is moving away from or towards Earth. By tracking these shifts, scientists can detect the presence of an exoplanet, determine its mass, and calculate its orbit. This method has already led to the discovery of many exoplanets, some of which lie in potentially habitable zones, sparking speculation about their potential to host life. Direct imaging of exoplanets, though challenging, provides another fascinating glimpse into these distant worlds. Stars are incredibly bright, and their glare often overwhelms the faint light of the planets around them. However, advancements in telescope technology, particularly adaptive optics, have made it possible to block out the star's light, revealing the planets orbiting it. By studying the light from these planets, scientists can learn about their atmospheric composition, vital information that can provide clues about their habitability. Together, these various techniques, transit, radial velocity, and direct imaging, offer a broad and diverse view of the exoplanets scattered across our galaxy, especially those that might share characteristics with Earth. As technology continues to improve, the search for exoplanets in the habitable zone is gaining momentum. This excitement is fueled by the possibility that we might one day discover a planet that mirrors Earth in terms of its environment and the potential to support life. Each new discovery in this field contributes to our growing understanding of the universe and humanity's place within it. One such discovery that has captured the imagination of scientists and the public alike is Proxima Centauri b, an exoplanet orbiting Proxima Centauri, the closest star system to Earth. Proxima Centauri b lies within the habitable zone of its star, where liquid water could exist, one of the key ingredients for life. This discovery has sparked renewed interest in the possibility of finding life beyond our solar system, as it presents a nearby, potentially habitable world just over 4 light years away. Another exciting candidate in the search for life is Kepler 1a6f, an exoplanet discovered by NASA's Kepler mission. Located about 158 light-years from Earth, Kepler 1a6f is roughly 1.1 times the size of Earth and is positioned in the habitable zone of its star, a red dwarf. This planet's rocky surface and potential atmosphere make it a strong candidate for further study, as it could possess conditions similar to those on Earth, making it a promising target in the hunt for alien life. The TRAPPIST-1 system, located about 40 light-years from Earth, is home to 7 Earth-sized planets. 3 of these planets are firmly located in the habitable zone, where liquid water could exist. The diversity of atmospheres on these planets has intrigued scientists as it raises fascinating questions about the potential for life to arise in varying conditions. Could these planets, with their different environments, harbor life forms adapted to the unique conditions of their respective worlds? LHS 1140b, located just 41 light-years from our solar system, is another notable exoplanet. Dubbed a super-Earth, it has a robust gravity and thick atmosphere, which could offer a stable environment for life. Scientists are particularly interested in studying the composition of this planet's atmosphere, as it could provide critical insights into the planet's potential for habitability and the conditions that might support life. As our technology continues to advance and our ability to explore deeper into the cosmos improves, we inch ever closer to understanding which of these distant exoplanets could one day be our cosmic neighbors. The discoveries of these potentially habitable worlds are monumental in our quest to answer the age-old question of whether we are alone in the universe. The discovery of extremophiles on Earth, organisms that thrive in extreme environments once thought inhospitable to life, has significantly shaped how we think about the possibility of life beyond our planet. Extremophiles have been found in some of the harshest environments on Earth, from volcanic hot springs to the deep, dark depths of the ocean, and even in the frozen expanse of Antarctica. Their ability to survive and thrive in environments with extreme heat, high pressure, and acidity has broadened our understanding of what constitutes a habitable environment. For decades, scientists focused on searching for life on planets and moons that resembled Earth. However, the discovery of extremophiles has shifted this focus. Life, it turns out, can exist in a wide variety of environments. This realization opens up new possibilities for finding life in places that were once considered unlikely candidates, such as the thick clouds of Venus or the icy oceans beneath the surface of moons like Europa and Enceladus. Extremophiles have demonstrated that life is incredibly adaptable, and this insight has fueled a new wave of exploration in astrobiology. Upcoming missions to Mars are poised to investigate ancient water sources and subsurface habitats where extremophiles might still survive. Similarly, missions to Europa are driven by the hope that beneath its frozen exterior lies a subsurface ocean that could harbor microbial life. The discovery of extremophiles on Earth has revolutionized how scientists approach the search for life in the cosmos, guiding our exploration of the most extreme and unexpected environments in our quest to understand the broader potential for life in the universe. The study of extremophiles is one of the most intriguing and enlightening branches of scientific inquiry, offering remarkable insights into the very nature of life itself. These resilient organisms which thrive in the most hostile and extreme environments on Earth, ranging from the crushing depths of the oceans to the searing heat of boiling springs, serve as living laboratories for scientists seeking to understand the fundamental biochemical processes that might sustain life in other parts of the universe. By examining how extremophiles metabolize, reproduce, and survive in such inhospitable conditions, researchers are able to develop hypotheses about the potential for life to exist elsewhere in the cosmos. These hypotheses often involve biochemistry that differs from the biological systems we are familiar with, suggesting that life in other worlds might not resemble anything we can easily imagine. Extremophiles, therefore, offer a powerful lens through which we can reevaluate our understanding of life. Their existence challenges our conventional thinking about the conditions necessary for survival, showing us that life may not require Earth-like conditions at all. This insight has profound implications, especially when considering the possibility of extraterrestrial life. The influence of extremophiles extends far beyond the boundaries of our planet, prompting us to reconsider where and how we might find our extraterrestrial neighbors. Their adaptability opens the door to the idea that life could exist in environments we would consider utterly inhospitable, be it on planets with acidic atmospheres, moons bathed in freezing cold, or even in the vast reaches of space itself. This exploration of life's potential beyond Earth dovetails with one of humanity's most enduring quests, the search for extraterrestrial intelligence. For centuries, this search has captivated the human imagination, leading to the creation of ambitious projects aimed at reaching out to potential civilizations scattered across the vastness of space. One of the most iconic and thought-provoking efforts in this pursuit has been the attempt to send messages into the depths of the cosmos, hoping to establish contact with intelligent beings millions, if not billions, of light years away. Interstellar messages are not mere signals. They are carefully designed communications crafted with the intention of revealing our existence to others in the universe. These messages represent a form of universal dialogue, a potential bridge between civilizations separated by unimaginable distances. In their design, scientists and researchers seek to encode critical aspects of human civilization, from our understanding of mathematics to our scientific achievements, our cultural values, and the very essence of who we are as a species. The goal is not simply to transmit information, but to create a universal language that transcends the barriers of speech, culture, and context. The first such attempt to communicate with extraterrestrial civilizations was the Arecibo message, sent in 1974 from the Arecibo Observatory in Puerto Rico. This binary-coded radio message contained fundamental information about humanity, the structure of our DNA, the numbers 1 through 10, the solar system's layout, and more. Its target was the globular star cluster M13, which is located about 25,000 light-years away. The message was a symbolic gesture, an expression of humanity's hope to connect with intelligent life beyond Earth, regardless of how far away or how different they might be. While the Arecibo message was one of the most well-known efforts, it was not the only one. Over the years, numerous attempts have been made to send messages into the cosmos, driven by a desire not only to proclaim our presence, but also to engage in a dialogue with any potential listeners. However, this endeavor is not without its risks. The very act of sending out a message signals our location and existence to the cosmos, raising the possibility of unwanted attention from entities whose intentions remain unknown. Despite these concerns, the pursuit of communication continues, fueled by humanity's unyielding curiosity and deep-seated need to understand our place in the universe. The belief remains that one day, somewhere in the vast expanse of space, our signals will find a listening ear, and that dialogue with other civilizations will become a reality. This search for extraterrestrial life is intimately tied to our evolving understanding of the universe, and theories such as space-time and the multiverse offer profound insights that challenge and deepen our perceptions. Space-time, first formalized by Albert Einstein, is a concept that merges the fabric of space with time, creating a unified continuum. This radical shift in perspective suggests that events are not simply located in space, but are also intertwined with the flow of time. In this framework, time is an active participant in shaping the cosmos, influencing the movement of celestial bodies and the very course of the universe. It is a dynamic and fluid force, rather than a static backdrop for events to unfold. Equally transformative is the multiverse theory, which proposes that our universe may be just one of many in an infinite ensemble of parallel realities. Emerging from various interpretations of quantum mechanics, the multiverse suggests that every decision or quantum event might give rise to alternate realities, universes where different versions of events unfold, or where the laws of physics themselves may differ. In this vast collection of universes, there could be countless worlds, some similar to ours, and others vastly different, each governed by its own unique set of physical laws. This theory forces us to reconsider the uniqueness of our own universe and to ask questions about the true nature of reality itself. These ideas, while still largely theoretical, have opened new avenues for scientific exploration, offering potential answers to some of the most fundamental questions about existence. For instance, the study of black holes has shown how time and space behave under extreme conditions, offering a glimpse into how the laws of space-time might break down under immense gravitational pressure. Similarly, if the multiverse is real, it could help explain why our universe seems to be finely tuned for life, with physical constants that just happen to be perfect for the existence of biological organisms. Perhaps other universes do not share this fine-tuning, and thus life cannot exist within them. Both space-time and the multiverse are far more than abstract concepts. They provide a framework for understanding phenomena that remain beyond our grasp. They push the boundaries of human knowledge and spark our imagination, urging us to think beyond what is known and to consider the vast, untapped potential of the cosmos. These theories suggest that the universe is far richer and more complex than we can fully comprehend, and they encourage us to remain curious, to continue exploring, and to question the very nature of existence. In this pursuit of understanding, concepts like wormholes and time dilation further challenge the limits of what we know. Wormholes, which are theoretical passages through space-time, could create shortcuts between distant regions of the universe, allowing for faster-than-light travel or even time travel. These wormholes, if they exist, could offer a new means of exploring the universe, opening doors to distant stars and galaxies in a way that would have once seemed impossible. Time dilation, another concept derived from Einstein's theory of relativity, describes how time slows down for an object moving at a high velocity or near a massive body, like a black hole. This strange phenomenon, where time moves at different rates depending on one's location or speed, forces us to reconsider our understanding of the passage of time itself. In essence, the exploration of these ideas, whether it be through the study of extremophiles, the search for extraterrestrial life, or the investigation of the very fabric of space-time, reminds us that our understanding of the universe is far from complete. The journey of discovery continues, driven by our innate curiosity and our desire to make sense of the cosmos. It is a quest that pushes the boundaries of what we know, compelling us to explore new realms of possibility and ultimately to expand the horizons of human knowledge. The concept of wormholes, although still confined to the realm of theory, holds a fascinating place within the equations of general relativity. These hypothetical passages through space-time offer a tantalizing glimpse into potential breakthroughs in our understanding of the universe. Despite being supported by mathematical models, wormholes have never been observed in practice. This presents a significant gap between abstract theory and empirical evidence, leaving them firmly within the domain of possibility rather than certainty. Integrating such concepts into our current frameworks of physics opens up an expansive range of potential, where theories and ideas once thought impossible are now subject to serious exploration. For instance, researchers are delving into the idea that wormholes could be stabilized using a theoretical substance known as exotic matter. Exotic matter, which remains an enigma in itself, is essential in discussions surrounding the feasibility of creating stable wormholes. If such stabilization could be achieved, it would not only revolutionize the idea of interstellar travel, but would also raise profound questions about the nature of time, causality, and the very structure of the universe. The possibility that wormholes might allow for shortcuts through space-time challenges everything we know about travel and communication, inviting us to rethink fundamental concepts that have guided scientific inquiry for centuries. While these concepts might seem like science fiction, they represent critical questions in theoretical physics, pushing the boundaries of what we know and can imagine. Scientists around the world are engaged in ongoing investigations and debates, attempting to unravel the complexities of these ideas, each step forward bringing us closer to potential new revelations about the universe and our place within it. The interaction between wormholes, time dilation, and the fundamental fabric of space-time remains one of the most exciting frontiers in modern science, where the lines between speculation and discovery blur in exhilarating ways. One of the most captivating examples of these scientific challenges comes in the form of the twin paradox, a thought experiment that beautifully illustrates the counterintuitive nature of time within the framework of relativity. The paradox begins with two twins, traditionally named Twin A and Twin B. Twin A stays on Earth while Twin B embarks on a journey to a distant star, traveling at speeds approaching the speed of light. According to Einstein's theory of relativity, as Twin B speeds through space, time itself slows down for them relative to Twin A, who remains on Earth. This phenomenon, known as time dilation, means that when twin B finally returns, they will have aged less than twin A, despite both being born at the same time. This apparent discrepancy in aging is not the result of any intrinsic difference between the two twins, but rather a consequence of the extraordinary speeds involved and the relative motion between them. Twin B's experience of time is fundamentally altered by their journey through space, demonstrating that time is not a universally shared experience, but one that can be influenced by velocity and gravitational forces. This paradox offers a striking illustration of one of the central principles of relativity. Time is not absolute, and its passage is shaped by an object's motion through space. Einstein's equations show that as objects approach the speed of light, the fabric of time itself becomes more malleable, stretching and warping to accommodate the dynamics of motion. In extreme cases, this bending of time could lead to a radically different experience of reality for observers in different states of motion. The twin paradox forces us to confront the limits of our intuition, suggesting that our everyday understanding of time might be wholly inadequate in extreme conditions. The paradox also raises profound questions about the nature of simultaneity, the idea that two events that appear to occur simultaneously for one observer may not be simultaneous for another, depending on their relative motion. This isn't just an academic exercise, however. The twin paradox has been tested experimentally, most notably with atomic clocks placed aboard high-speed jets. The results have consistently supported the predictions of relativity, confirming that time dilation is not merely theoretical, but an observable reality. These experiments have solidified our understanding that time, far from being a constant and immutable measure, is an incredibly flexible entity, intricately woven into the very fabric of space itself. Such revelations about the malleability of time have deep implications for how we perceive the universe. Historically, humanity has viewed time as a simple, linear progression, an unbroken line stretching from the past to the future. This intuitive sense of time, though deeply ingrained in our daily lives, has been upended by modern physics. The understanding that time is intertwined with space to form a dynamic fabric known as space-time opens new vistas for exploring the cosmos. Rather than a mere backdrop for events, time itself is an active participant in the behavior of the universe. In this new paradigm, time is not the same everywhere. The strength of gravity and the speed at which an object moves both influence how time flows. Near a black hole, for example, where gravity is immensely strong, time slows down dramatically as one approaches the event horizon, the point beyond which nothing, not even light, can escape. For someone far away from the black hole, however, time continues at a normal pace. This discovery forces us to confront some of the most profound questions about the nature of reality. Is time an experience that is shared universally by all observers, or is it deeply personal, shaped by the forces acting on each individual? In addition to reshaping our understanding of time, these insights have also deepened our appreciation for the expanding universe. Over the past century, astronomers have observed that the distance between galaxies is growing. This realization that the universe is not static but constantly evolving has revolutionized our view of the cosmos. Space is no longer an empty void, but a dynamic, ever-changing entity. This expansion has profound implications for the fate of the universe, sparking debates about scenarios such as the Big Freeze or the Big Crunch, both of which unfold over unimaginable periods of time. As we continue to explore the mysteries of time and space, we are forced to reconsider our place in this vast universe. Each new discovery invites us to reflect on our existence in a way that is both humbling and awe-inspiring. The more we learn, the more we realize how small we are in the grand scheme of things. We are but a speck in an ever-expanding cosmos shaped by forces far beyond our comprehension. Yet, this realization also deepens our connection to the universe, as we come to understand that each new discovery is a step toward uncovering our role in this extraordinary cosmic drama. The idea of an infinite universe raises profound philosophical questions that have intrigued thinkers for centuries. If the universe is infinite, both in terms of space and time, what does this mean for our understanding of existence itself? Could there be other universes, each with its own set of physical laws and histories? The notion of a multiverse, an infinite collection of universes, forces us to reconsider the uniqueness of our own existence. It suggests that everything that can happen, every possibility, may already be realized in some form across the vast expanse of this cosmic tapestry. As we continue to probe these questions, we find ourselves not just exploring the outer limits of space, but also the very nature of reality itself. Moreover, the concept of an infinite universe significantly impacts our understanding of fate and free will. If every possibility is realized somewhere within the cosmos, it brings us to ponder one of the most profound questions of human existence. Are our choices genuinely free, or are they, in fact, simply reflections of a multitude of preordained trajectories already set within the boundless expanse of reality? This line of thought leads to a fascinating philosophical debate surrounding determinism. In such a universe, every possible version of ourselves could be playing out in parallel realms, each unfolding in a different way. So, where does that leave our sense of agency and responsibility? In this context, the philosophical inquiry shifts to reconciling our experience of choice and consequence with a universe that permits every possible outcome to manifest. The very fabric of existence seems to allow all potential versions of events to occur, stretching our understanding of free will. Each choice we make may appear to be uniquely our own, but when viewed through the lens of infinite possibilities, it begs the question, are we genuinely the architects of our own fate, or are we merely passengers on a predetermined journey, guided by forces far beyond our control? The idea of infinite versions of ourselves existing simultaneously can be both unsettling and awe-inspiring. It forces us to confront the fragility and complexity of our own existence. Then there's the profound issue of meaning in a universe that stretches infinitely in all directions, both spatially and temporally. In the face of such an infinite scale, our individual lives can seem insignificant, fleeting moments in an otherwise endless expanse. However, this same infinitude can also spark a sense of awe, inspiring a deep connection to the cosmos and a realization that even the smallest actions, thoughts, and events might reverberate through the vast universe in ways we cannot even begin to comprehend. This duality, the sense of being both insignificant and paradoxically significant in the grand cosmic scheme, compels us to reconsider what it truly means to matter in a universe so seemingly boundless. It challenges us to search for meaning in the midst of this immense vastness, urging us to find a sense of purpose, even in the face of uncertainty. In grappling with these profound implications, we stand at the crossroads where science meets philosophy. The potential infinitude of the universe not only invites us to explore the intricate mechanics of cosmic phenomena, but also prompts us to reflect on our own existence. While science provides the empirical data and models that describe how the universe operates, it is philosophy that enriches our understanding by probing the deeper questions. What do these scientific truths mean for us as conscious beings? What implications do they hold for our understanding of existence itself? It's a partnership between the two fields that reminds us that the journey of discovery is as infinite as the universe we endeavor to understand. Amid this vastness, astronomers have uncovered several anomalies that challenge our current understanding of the universe and continue to ignite curiosity. One of these enigmas is the mysterious phenomenon known as fast radio bursts, FRBs. These brief, intense bursts of radio waves originate from distant galaxies and last only a few milliseconds. The precise cause of these bursts remains a puzzle. Some scientists speculate that they might result from neutron star collisions or black hole mergers, while others entertain the possibility that they could be signals from extraterrestrial civilizations. The uncertainty surrounding their origin only adds to their allure, and every new discovery related to FRBs seems to only deepen the mystery. Another cosmic anomaly that has captured the attention of astronomers is the Great Attractor, located nearly 200 million light-years away. This region of space appears to exert a gravitational pull on our galaxy and several others. The Great Attractor itself is not directly observable, as it is concealed behind the dense star fields and gas of the Milky Way's galactic plane. Despite its elusive nature, the gravitational influence it exerts on surrounding galaxies is undeniable. The presence of such a massive force leads astronomers to question the distribution of mass throughout the universe, suggesting that there are large-scale structures lurking in the cosmos that we have yet to fully comprehend. Then there's the perplexing mystery of dark matter, an invisible substance that makes up about 27% of the universe. Despite its ubiquity, dark matter cannot be directly observed, and its existence is inferred primarily through its gravitational effects on visible matter. One of the most striking manifestations of dark matter is its influence on the rotation of galaxies. Observations show that galaxies rotate in ways that cannot be explained solely by the mass of visible matter that we can detect. Dark matter, it seems, is the hidden force shaping the structure of the universe. The search for dark matter particles is a scientific endeavor akin to detective work, as researchers sift through cosmic clues in an attempt to piece together the identity of this mysterious substance. Lastly, consider the peculiar galaxies like Antlia 2, an example of a dark matter-dominated galaxy. Antlia 2 is enormous yet faint, making it an incredibly difficult galaxy to study. Its structure hints at the overwhelming influence of dark matter on its formation and behavior, suggesting that it may not fit neatly into the conventional models of galaxy formation. This galaxy, like many others, forces us to rethink our understanding of cosmic structures and the role that invisible forces like dark matter play in shaping the universe. These anomalies not only capture our imagination, but also serve as stark reminders that the universe is full of surprises, often compelling us to rethink what we know about the very nature of reality. Each discovery, whether it's a new understanding of dark matter, the detection of fast radio bursts, or the mysteries of the Great Attractor, enriches our knowledge and fuels our thirst for further exploration. These cosmic puzzles remind us that, even in our attempts to grasp the vastness of the universe, we are still standing on the edge of something much greater, far beyond what we can currently comprehend. At the heart of these discoveries lies the Great Attractor, a massive gravitational anomaly located toward the center of our Milky Way galaxy. Hidden behind the dense star fields and gas of the galactic plane, this enigmatic region exerts a powerful influence on our galaxy and others nearby. The force of attraction from the Great Attractor has challenged existing models of the universe, particularly those that assumed a more uniform distribution of mass across vast cosmic distances. Instead, the presence of such a concentrated region of mass suggests that there may be structures on a cosmic scale that we are only beginning to understand. It is a puzzle that continues to captivate scientists and philosophers alike, prompting us to reconsider the fundamental nature of the universe and our place within it. As we continue to explore these anomalies, it becomes increasingly clear that our understanding of the cosmos is far from complete. Every new discovery presents us with more questions than answers, pushing us further into the unknown. Yet it is in this very uncertainty that we find the greatest potential for discovery, challenging our perceptions and inviting us to rethink everything we thought we knew about the universe. The Great Attractor, a mysterious and powerful gravitational anomaly located in the heart of our universe, has become a pivotal focal point in our exploration of the cosmos. Studies of this enigmatic region have unveiled astonishing revelations about the nature of dark matter, an elusive and invisible substance that plays a vital role in cosmic dynamics. Dark matter does not emit or absorb light or energy, which has long rendered it invisible to conventional detection methods. However, the gravitational forces in this region compel scientists to revise their understanding of the universe's fundamental workings. The interaction between visible and dark matter in this region challenges traditional theories that rely predominantly on observable matter to explain the motion and behavior of galaxies. As researchers delve deeper into the Great Attractor's gravitational influence, they are forced to reconsider the unseen elements of the universe, those that silently shape the universe's large-scale structure, guiding the movement and interaction of galaxies. This forces scientists to refine their models of cosmic evolution, adding new layers of complexity to our understanding of the cosmos. The Great Attractor serves as a reminder that the universe is full of unknowns, and that each discovery invites us to expand our imagination and rethink our assumptions. Its existence pushes the boundaries of astrophysical research, opening new doors to understanding the forces that govern the cosmos. The gravitational pull of this anomaly highlights just how much we have yet to learn, proving that even as we make monumental strides in our exploration of the universe, we are still only scratching the surface of its vast, mysterious nature. Moving beyond the realm of dark matter, another area that continues to intrigue scientists is the Oort cloud, a vast spherical shell of icy bodies located on the outermost fringes of our solar system. First proposed by the Dutch astronomer Jan Oort in the 1950s, this cloud is thought to be the repository for billions of comets that formed in the early solar system. These objects, largely composed of ice and dust, lie roughly 1 to 2 light years from the Sun, far beyond the orbit of Pluto and all other known planets. The Oort cloud is not just a distant, passive collection of objects. It is a dynamic region that influences the inner solar system. Occasionally, objects within the cloud are disturbed, often by the gravitational pull of nearby stars or other celestial forces, sending them on a collision course with the inner solar system. As these icy bodies approach the Sun, the intense heat causes the solid ice to sublimate, turning it directly into gas. This process creates the glowing coma and tail that we associate with comets. Interestingly, the Oort cloud is believed to be the origin of long-period comets, those whose orbits can take hundreds or even thousands of years to complete. These comets, often appearing unexpectedly in the night sky, can provide spectacular displays of light as they travel through the inner solar system. In contrast, short-period comets are typically believed to originate from the Kuiper Belt, a region closer to the Sun. The study of the Oort cloud and its comets is crucial for understanding the early formation of the solar system. Comets are often referred to as time capsules, preserving the original materials from which the planets were formed. As scientists continue to study these celestial wanderers, they gain invaluable insights not only into the history of our solar system, but also into the broader dynamics of celestial mechanics and the evolution of the universe itself. The Oort cloud remains one of the most tantalizing mysteries of our cosmic neighborhood, a frontier that continues to captivate astronomers and enthusiasts alike. In addition to the phenomena of dark matter and the Oort cloud, the universe is also home to cosmic rays, high-energy particles that constantly bombard Earth's atmosphere. These particles, which are primarily protons along with heavier nuclei and electrons, travel at nearly the speed of light. While Earth's atmosphere and magnetic field provide substantial protection, cosmic rays still present significant challenges, particularly in the fields of space exploration and technology. For astronauts venturing beyond the protective layers of Earth's atmosphere, cosmic rays pose a severe risk. When humans travel into space, they are exposed to these high-energy particles, which can increase radiation doses and raise the risk of long-term health issues, including cancer. In addition, cosmic rays can have detrimental effects on the central nervous system. With planned missions to Mars and beyond, agencies like NASA have made radiation exposure a key area of concern, intensifying research to develop effective shielding technologies to protect astronauts on long-duration missions. On Earth, cosmic rays can also interfere with technology, especially systems that rely on sensitive electronics. Satellites and high-tech systems can suffer from so-called single-event upsets, where a cosmic ray particle strikes microelectronic circuits, potentially causing data errors or even complete system failures. To mitigate these risks, some satellites are equipped with radiation-hardened components designed to withstand these high-energy particles. Despite these precautions, cosmic rays continue to pose a persistent threat to our technological infrastructure, underscoring the need for ongoing vigilance and innovation. However, cosmic rays also serve as a tool for scientific advancement. Their high energy makes them valuable in the study of the universe's origins and the fundamental forces that shape it. By observing the behavior of matter under extreme conditions, cosmic rays offer clues about the interplay between cosmic forces and the fundamental processes of particle physics. While they may be a source of risk, cosmic rays also foster breakthroughs in our understanding of the universe, helping us to better comprehend the fundamental building blocks of reality. One of the most fascinating phenomena in the universe is the pulsar, an intensely magnetic, rapidly spinning neutron star that emits beams of radiation. Imagine a lighthouse in space, a compact, rapidly rotating star sending out regular pulses of energy like a cosmic clock. Pulsars serve as invaluable tools for astronomers, offering precise measurements of the fabric of space and time. Their regularity and unique characteristics allow scientists to study the physics of extreme environments and test theories of general relativity in ways that are not possible on Earth. Meanwhile, the realm of black holes continues to fascinate and perplex researchers. While most people are familiar with the concept of black holes as regions of space where gravity is so intense that nothing, not even light, can escape, few realize the sheer scale of supermassive black holes. These cosmic giants, found at the centers of most galaxies, can be millions or even billions of times the mass of our Sun. Their gravitational influence is so powerful that it warps the fabric of space-time itself, bending light and distorting the paths of stars and gas clouds in their vicinity. At the core of these supermassive black holes are accretion disks, rotating disks of gas and dust that heat up as they spiral inward, emitting intense radiation. These black holes not only shape the structure of their host galaxies, but also fuel the growth and evolution of galaxies over time. Supermassive black holes remain some of the most awe-inspiring and mysterious objects in the universe. Beyond black holes and pulsars, the universe is also home to the vast cosmic web, a structure formed by the influence of dark matter. This invisible substance, which does not emit light, has a profound effect on the way galaxies are organized throughout the universe. The cosmic web consists of vast strands that connect clusters of galaxies, creating a network of filaments and voids that stretch across billions of light years. Though invisible, dark matter's gravitational effects create a stunning cosmic landscape, one that illustrates the interconnectedness of the universe and the forces that shape it. The cosmic web is a testament to the invisible forces at work behind the scenes, weaving together the very fabric of the universe in ways that are still not fully understood. It's a phenomenon that challenges our perceptions, offering a glimpse into the immense complexity and beauty that lie hidden beneath the surface of the cosmos. Comets, those fascinating celestial travelers, have long captivated our imaginations. Though we often perceive them as fleeting visitors from the farthest reaches of our solar system, their existence is far more profound. These icy, rocky orbs are not just spectacular sights in our night sky, they are ancient time capsules holding secrets about the early solar system's formation. As they journey towards the sun, the intense heat triggers the sublimation of their icy cores, resulting in the awe-inspiring tails we see trailing behind them. These tails stretch for millions of kilometers, a visual testament to the physical processes occurring within. But beyond their beauty, comets offer us tantalizing clues about the origins of water and organic molecules on Earth. Could they have played a role in delivering the building blocks of life? The connection between these icy wanderers and our own planet hints at a deeper cosmic bond, one that ties Earth's past to the far reaches of the universe. In their icy exodus, comets reveal the profound interconnectedness of all things, urging us to look beyond our world and ponder our place in the cosmos. As we turn our gaze even further outward, the vastness of space provokes another, even more profound question. What lies ahead for the universe itself? Our understanding of the universe's ultimate fate remains uncertain, but current scientific theories provide us with a range of possibilities, each more mind-boggling than the last. The most widely accepted scenario is known as the Big Freeze, a theory that posits the universe will continue to expand at an accelerating rate, driven by an enigmatic force called dark energy. This unseen energy is causing galaxies to drift apart, and as it does, the universe will cool, eventually leading to a dark, cold expanse. In this future, stars will burn out and no new ones will be born, leaving behind only the remnants of once glorious cosmic bodies. The universe, in this vision, will become a lifeless void, void of heat, light, and activity. Alternatively, some scientists propose a far more dramatic fate, known as the Big Crunch. This theory hinges on the density of the universe. If it were high enough to counteract the forces driving its expansion, gravity could eventually pull everything back together. Over the course of billions of years, galaxies, stars, and all matter would converge into a singularity, an infinitely dense point where time and space cease to function as we understand them. This process would mirror the reverse of the Big Bang, as the universe collapses back on itself in a cataclysmic implosion. Yet another intriguing hypothesis is the Big Rip, a theory that suggests dark energy may not only continue to drive expansion, but it could intensify over time, eventually becoming so powerful that it tears apart galaxies, stars, planets, and even atoms. This violent dissolution would end the universe as we know it, leaving nothing behind but the dispersed remnants of what once was. While the Big Freeze and the Big Crunch seem like distant possibilities, the Big Rip offers a scenario where cosmic structures are ripped asunder in a dramatic and potentially more immediate conclusion. The Big Freeze, the Big Crunch, and the Big Rip each represent distinct trajectories for the universe's end, each shaped by the interplay of cosmic forces and fundamental physical laws. Each theory is as captivating as it is sobering, offering us an opportunity to reflect on the inevitable dissolution of everything we know. But these theories are not just academic exercises. They reveal how our understanding of the universe is shaped by the laws of physics, and how our place in the cosmos is framed by the ultimate fate of all things. Central to these theories is the concept of entropy. In simple terms, entropy refers to the disorder or randomness within a system. The second law of thermodynamics tells us that in an isolated system, entropy will always increase. Over time, energy becomes more evenly distributed and less available for doing work. As the universe expands, entropy rises, leading to a gradual decline in organized structures. Stars burn through their fuel, generating both light and waste heat, which contributes to this process. Eventually, stars exhaust their fuel and galaxies drift apart. The universe will experience what is known as heat death, where energy is so evenly spread that no thermodynamic activity occurs. This will result in a dark, cold cosmos filled with the remnants of stars, black holes, and neutron stars. But entropy doesn't only shape the physical evolution of the universe, it also forces us to contemplate the transient nature of existence itself. As stars burn out and galaxies dissipate, we are reminded that everything we know and love is temporary. The cycle of creation and destruction, whether on the scale of a single star or the entire universe, underscores the fleeting nature of life and the delicate balance that sustains it. Black holes, those mysterious regions in space where gravity is so intense that not even light can escape, play a crucial role in shaping our understanding of the universe's fate. Far from being merely the endpoint of massive stars, black holes are critical players in the universe's long-term evolution. As scientists continue to study these enigmatic objects, they uncover insights that inform our predictions about the future. For instance, black holes could contribute to the Big Freeze scenario by remaining as stable, long-lived remnants in an ever-expanding universe. Over immense timescales, black holes might collide and merge, creating even more massive black holes. These mergers could alter the distribution of matter across the cosmos, ultimately influencing the fate of the universe. In the Big Crunch scenario, black holes play an even more pivotal role. If the universe's expansion were to slow and reverse, black holes could help pull galaxies back together through their immense gravitational influence. In this vision, black holes could be the anchor that keeps the universe from dispersing into oblivion, pulling everything back into a cataclysmic collapse that mirrors the conditions of the Big Bang. Yet the expanding universe we currently observe suggests that the Big Crunch is less likely than it once seemed. Instead, dark energy, the mysterious force driving the accelerated expansion of the cosmos, continues to push galaxies farther apart. As we ponder the future of the universe, we are left with a series of questions. Will dark energy continue to accelerate the universe's expansion? Can black holes influence the outcome, or are they doomed to become the silent survivors in a universe that fades into nothingness? Whatever the answer, the study of these cosmic phenomena brings us closer to understanding the intricate forces that govern the universe, and the role we play in this grand, ever-expanding tapestry. When considering the future of the universe, one cannot ignore the profound role black holes will play, particularly in the context of information theory and the fate of information itself. These enigmatic cosmic objects have captivated scientists for decades, raising questions that reach into the very fabric of our understanding of space, time, and reality. At the heart of these questions lies the mystery of what happens to the information contained within matter as it falls into a black hole. As we know, black holes are regions where gravity is so intense that not even light can escape. For a long time, it was believed that any information, whether it be the particles of matter, the energy, or the very essence of what falls into these dark abysses, was lost to the cosmos forever. This dilemma, often referred to as the black hole information paradox, has sparked debates among the brightest minds in theoretical physics. Some scientists have proposed that black holes may eventually evaporate, a phenomenon known as Hawking radiation. In this model, the black hole slowly emits radiation, gradually losing mass and potentially releasing the information it has absorbed back into the universe. This theory, though still unproven, could fundamentally alter our understanding of time, space, and the continuity of information in an ever-evolving universe. If black holes do indeed shed their accumulated information, it might provide new insights into the very nature of reality and how information, whether physical, quantum, or otherwise, survives within the cosmos. As it stands, black holes represent a crossroads in cosmological theory, where fundamental questions about the universe's destiny intersect with the mechanics of quantum physics. Their role in the grand narrative of the universe is undeniable. These cosmic giants have the potential to shape not just the fate of nearby stars or galaxies, but the very structure of the cosmos itself. As our understanding deepens, the questions about the ultimate fate of information within black holes continue to spark curiosity and awe, keeping scientists and curious minds alike engaged in the ongoing exploration of these fascinating phenomena. Inextricably tied to the future of black holes is the fate of the universe itself. Despite all the advances in scientific understanding, the ultimate destiny of the cosmos remains one of the greatest mysteries. While many theories have been proposed, the vastness of space and the unknowns that lie within it ensure that these questions remain open. One of the most significant unknowns is the role of dark energy, an enigmatic force responsible for the accelerated expansion of the universe. We know that dark energy exists, but its true nature and how it will influence the universe's future remain elusive. Based on current understanding, several possible outcomes for the universe's fate have been proposed. One of the most widely discussed is the Big Freeze theory, which predicts that the universe will continue to expand indefinitely. As galaxies drift further apart, stars will burn out, and the cosmos will eventually be left in a cold, dark, and lifeless state. On the opposite end of the spectrum is the Big Crunch theory, which suggests that the expansion of the universe will eventually slow down and reverse itself. The gravitational pull of all the matter within the universe could collapse it back into a singularity, essentially bringing the universe to an end in a dramatic implosion. However, the likelihood of these outcomes depends heavily on the nature of dark energy, whose properties we have yet to fully understand. As researchers delve deeper into the complexities of dark energy, they are also exploring alternative theories, such as the Big Rip. In this unsettling scenario, dark energy's influence grows stronger over time, causing the universe's expansion to accelerate to the point where galaxies, stars, planets, and even atoms are torn apart. The possibility of such an outcome presents deep questions about the very forces that govern the universe and pushes scientists to explore the nature of dark energy and its impact on space-time. But the mysteries of the cosmos don't stop there. As scientists continue to probe deeper into the fabric of reality, some theories suggest that our universe might not be the only one. In the concept of the multiverse, our universe could be one among many, each with its own distinct laws of physics. If true, this would imply that the fate of our universe could be vastly different from that of others within this multiverse, and the universe's end could take on countless possible forms. The very idea of a multiverse introduces yet another layer of complexity to our understanding of existence, raising as many questions as it answers. As we stand on the edge of scientific discovery, the unknowns surrounding the universe's ultimate fate continue to tantalize researchers, urging them to dig deeper. Each new breakthrough, each new observation, only reveals more layers to the cosmic enigma. The answers may lie in parts of physics that have yet to be explored, or in realms of space and time that are still beyond our grasp. It is this endless mystery, this ever-expanding frontier that propels us to keep looking to the stars in search of understanding. The evolution of our understanding of the universe has been a remarkable journey, reflecting not only the progress of science, but also the growth of human thought and curiosity. In ancient times, civilizations such as the Babylonians and Greeks gazed up at the stars, weaving rich mythologies to explain their observations. Early astronomers like Ptolemy proposed the geocentric model of the universe, suggesting that Earth was the center of it all, surrounded by celestial bodies. For nearly 1,000 years, this model dominated our understanding of the cosmos and our place within it. The 16th century marked a revolutionary shift in our understanding, thanks to the work of Nicolaus Copernicus. In his heliocentric model, Copernicus boldly proposed that the sun, not the Earth, was at the center of our solar system. This radical idea challenged the prevailing geocentric view, laying the foundation for future discoveries. Galileo Galilei, with his groundbreaking use of the telescope, provided empirical evidence for Copernicus's theory by observing the moons of Jupiter and the phases of Venus. These observations offered undeniable support for the heliocentric model, forever changing the course of astronomical thought. As the scientific revolution unfolded, our understanding of the cosmos continued to expand. In the 17th century, Sir Isaac Newton synthesized earlier discoveries and introduced his laws of motion and universal gravitation. These laws offered a framework for understanding the movement of celestial bodies and laid the groundwork for the more complex theories that would follow. Newton's work revealed a universe that was not static and unchanging, but dynamic and governed by precise laws that could be understood, predicted, and modeled. The 20th century saw the advent of modern physics and cosmology, which further transformed our view of the universe. One of the most profound breakthroughs came with the observation of the redshift of light from distant galaxies, which led to the realization that the universe is expanding. This discovery, coupled with the formulation of the Big Bang theory, transformed our understanding of the origins and evolution of the universe. From a hot, dense beginning, the universe has been expanding for billions of years, evolving into the vast, complex expanse we observe today. As we continue to explore and understand the cosmos, our journey is far from over. Each new discovery offers glimpses into the mysteries that lie ahead, reminding us that the universe is a story still being written, one that will continue to unfold as we push the boundaries of knowledge and curiosity. As technology continues to advance, with groundbreaking tools like the Hubble Space Telescope and innovations in studying cosmic microwave background radiation, humanity finds itself unlocking ever deeper layers of the universe's mysteries. Each new discovery, whether it's about dark matter, dark energy, or the fundamental laws that govern the cosmos, further expands our understanding and highlights just how dynamic and evolving our comprehension of space truly is. This is not merely about sending spacecraft into the vastness. Space exploration carries profound cultural and philosophical implications that stretch far beyond the immediate act of exploration. Looking up at the stars, we are confronted with some of the most fundamental questions of existence. What is our place in this vast universe? What responsibilities do we have as caretakers of Earth? Different civilizations across history have gazed upon the heavens, each seeing the sky not just as a backdrop, but as a canvas filled with mystery, inspiration, and meaning. Ancient peoples, whether Egyptians, Mayans, or others, created rich mythologies that intertwined with the movements of celestial bodies. These myths didn't merely help them track time. They deeply influenced rituals, spirituality, and ways of understanding the natural world. In the modern era, the exploration of space invites a reevaluation of what it means to be human. As we send astronauts and robots far beyond our home planet, we find ourselves wrestling with ethical dilemmas that challenge our assumptions. What if we encounter extraterrestrial life on distant planets like Mars or moons like Europa? What rights would these life forms have, and how should we approach them? Should we meet them? The possibility of discovering alien intelligence forces us to rethink our own relationships, not only with these potential beings, but also with Earth itself, urging us to reflect on the importance of sustainability, compassion, and stewardship of our home planet. One of the most profound shifts brought about by space exploration is the growing sense of shared perspective, especially when astronauts describe the emotional impact of seeing Earth from space, known as the overview effect. This phenomenon leads to a deepened sense of unity with humanity and a newfound appreciation for the fragility of our planet. From the vacuum of space, Earth appears as a small, fragile orb, and this view sparks movements for global cooperation, environmental preservation, and the responsible use of resources. As we see our world suspended in the emptiness of the cosmos, the necessity of protecting it for future generations becomes clearer than ever before. Beyond the practical implications of space exploration, its philosophical dimensions are equally profound. Each mission into the cosmos invites us to ask timeless questions. What is the meaning of life beyond Earth? Are we alone in the universe, or is the cosmos teeming with other forms of life? Every step into space, every new discovery brings us closer to answering these questions, compelling us to reconsider the very nature of existence and our place in the grand tapestry of the universe. The pursuit of knowledge, meaning, and connection is no longer just a scientific endeavor. It has become a deep, almost spiritual quest that resonates across cultures and throughout time. For centuries, the cosmos has inspired human creativity in every form of expression. Artists, musicians, and writers have all turned to the stars for inspiration, while finding in the vastness of space a boundless source of wonder. The beauty and mystery of the universe have been captured in countless works of art, from the swirling stars in Vincent van Gogh's Starry Night to the intricate celestial designs of ancient cultures. These depictions are not merely representations, they are expressions of the awe and reverence that the cosmos inspires in the human heart. In music, too, the universe plays a starring role. Composers like Gustav Holst have sought to convey the essence of different planets through sound. In his The Planets, Holst takes the characteristics of Mars, Venus, Jupiter, and others, and translates them into powerful orchestral pieces that resonate with listeners' emotions. The music is not just a reflection of celestial bodies. It is an emotional journey that mirrors the grandeur and mystery of the universe itself. Literature has likewise been deeply influenced by space exploration. Writers, particularly in the realm of science fiction, have used the cosmos as a stage for exploring profound existential questions. Works like Arthur C. Clarke's 2001, A Space Odyssey, and Ray Bradbury's The Illustrated Man don't just imagine the future of humanity in space. They delve into questions about our purpose, our nature, and the mysteries of life itself. The universe, in these stories, becomes not just a physical place, but a rich narrative backdrop for exploring the deepest aspects of human existence. Throughout history, cultures across the globe have gazed upon the night sky and woven their own interpretations of cosmic events. For many ancient civilizations, the stars were not merely distant points of light. They were imbued with deep meaning and often personified as gods. The Egyptians, for example, revered Ra, the sun god, believing he governed life, death, and rebirth. Their understanding of the cosmos was not just scientific but spiritual, shaping agricultural cycles, rituals, and religious practices. In North America, indigenous cultures viewed the stars as a framework for storytelling. For the Loda people, constellations were more than mere patterns. They were guides and educators, shaping myths that reflected the rhythms of nature. The positions of the stars and planets were believed to influence earthly events, such as the changing of the seasons and the migration of animals. This connection to the cosmos fostered a deep respect for the natural world and its cycles. In China, a rich tradition of celestial observation merged astronomy with philosophy and medicine. The Chinese zodiac, with its 12 signs based on lunar cycles, reflects a belief that time and fate are intimately connected. Solar eclipses and meteor showers were seen as omens of the divine's presence in the heavens. These celestial events were both feared and revered, woven into the fabric of cultural life and interpreted with great care and significance. In the modern era, interpretations of cosmic phenomena continue to blend ancient wisdom with contemporary scientific understanding. Events like solar eclipses and meteor showers are celebrated worldwide, embraced both as scientific marvels and as moments of universal wonder. These celestial occurrences continue to stir a collective awe, uniting people across cultural divides and sparking a shared appreciation for the mysteries of the cosmos. This ever-deepening understanding of the universe has fundamentally changed how we perceive ourselves. For centuries, humans believed that Earth was the center of existence, an idea known as geocentrism. This worldview was dramatically upended by the heliocentric model proposed by Copernicus, which placed the sun at the center of the solar system. As technological advances in astronomy brought new insights into the nature of the cosmos, this shift in perspective expanded our understanding of our place in the universe. Later, with the contributions of astronomers like Galileo and Kepler, humanity began to realize that Earth was just one small planet in a vast universe, orbiting an average star in a galaxy filled with billions of other stars. The advent of space exploration, especially through tools like the Hubble Space Telescope, has only deepened this realization. Images of far-off galaxies, nebulae, and even the eerie beauty of our own Milky Way have shown us just how small and interconnected we are. This reality can be humbling, but also incredibly inspiring, urging us to explore further, to ask bigger questions, and to marvel at the infinite wonders that lie beyond our home planet. In the end, space exploration is not just a scientific pursuit. It is a journey that reshapes how we see the world, how we see each other, and how we see ourselves in the grand expanse of the universe. Every new discovery pushes the boundaries of our understanding, reminding us of the vastness and mystery of the cosmos, and of our collective responsibility to protect and cherish our fragile planet. Furthermore, the discovery of extraordinary cosmic phenomena, such as black holes, pulsars, and the cosmic microwave background radiation, has ignited an unprecedented era of scientific exploration. These phenomena, once the stuff of theoretical speculation, have now become cornerstones in our understanding of the universe. The Big Bang Theory, for instance, has revolutionized our perception of the cosmos, moving the narrative from ancient creation myths to a scientific understanding of the universe's origins and evolution. This shift has profound implications not just for science, but for philosophy, spirituality, and human self-awareness. As we uncover the mechanisms of the universe, we are confronted with deeper questions about life, consciousness, and existence itself. How did we come to be? What is the nature of consciousness? These fundamental questions spark a reevaluation of our beliefs, our cultures, and our connections to each other. In the grand scheme of things, we are not merely inhabitants of Earth. We are part of a much broader cosmic story. This perspective, humbling yet awe-inspiring, compels us to reflect on our role in the universe and why we are here. As humanity continues to explore the cosmos, our understanding of ourselves and our place in the universe is destined to evolve. Each discovery, each new piece of knowledge adds depth to our collective understanding, guiding future generations in their quest for knowledge and meaning. The universe, ever expanding and ever mysterious, holds infinite possibilities. Our capacity to comprehend it, however, is continually evolving. Yet the limitations of current space travel present a significant barrier in this quest. At present, space exploration relies heavily on chemical propulsion systems, specifically rockets, which have remained largely unchanged for decades. These systems have proven effective for reaching low Earth orbit and for relatively short trips, such as those to the Moon and Mars. However, when we look at the vast distances involved in exploring the deeper regions of space, the limitations of this technology become glaringly evident. For instance, a journey to Alpha Centauri, the closest star system to our own, would take over 4 years, even if we could travel at the speed of light, which, of course, is far beyond our current technological reach. The challenges of space travel are not just technical, they are biological as well. Human endurance in space poses another monumental hurdle. Prolonged exposure to microgravity leads to serious health risks, including muscle atrophy and bone density loss. Protecting astronauts from the harmful effects of radiation is equally problematic. Outside the protective shield of Earth's atmosphere, cosmic rays and solar radiation pose a serious threat to long-duration space missions. Current spacecraft are ill-equipped to offer the necessary shielding to safeguard astronauts from these dangers, making long-term space travel not only more complicated, but also significantly slower. Compounding these challenges is the issue of financial resources. Space exploration is an expensive endeavor. The cost of sending missions into space is astronomical, and national space agencies and private companies alike are continuously working to innovate and refine technologies that might reduce these costs. However, budget limitations still dictate the scope of our explorations. There is, however, hope in international collaboration. By pooling resources and sharing knowledge, spacefaring nations can enhance their collective ability to explore the cosmos while minimizing individual costs. Despite these constraints, these very limitations inspire innovation. Concepts like ion propulsion and solar sails are examples of promising technologies that could revolutionize space travel, allowing us to explore deeper into space. Ion propulsion, for example, uses electrically charged particles to generate thrust, offering an energy-efficient alternative to traditional chemical rockets. Meanwhile, solar sails harness the pressure of sunlight to propel spacecraft, opening the door to new forms of travel. As we continue to develop these technologies and learn from each mission, the boundaries of what we can achieve in space exploration will continue to expand. Looking to the future, humanity's ambitions are soaring higher than ever before. One of the most audacious goals is the establishment of a sustainable human presence on the moon. The Artemis program, spearheaded by NASA, aims to return astronauts to the lunar surface in the coming years, with the ultimate goal of building a permanent base. This lunar outpost would serve as a springboard for deeper exploration into our solar system, paving the way for missions to Mars and beyond. Mars, in particular, has captured the imagination of scientists, engineers, and the general public. Numerous missions are already planned to explore the Red Planet, with the ultimate goal of sending humans there by the 2030s. SpaceX, for example, envisions the colonization of Mars, while NASA's Perseverance rover is currently gathering invaluable data that could one day assist human explorers. Perhaps the most exciting aspect of these plans is the potential discovery of life, past or present, on Mars. The search for signs of life on Mars adds an extraordinary layer of excitement to these missions. If life once existed, or still exists, on the Red Planet, it would transform our understanding of life's prevalence in the universe. Terraforming Mars, or making it habitable for humans, is another ambitious concept that scientists are exploring on a broader scale. Although this idea remains speculative at present, technological advancements in areas like bioengineering, atmospheric manipulation, and resource extraction from Martian soil could one day make such a venture feasible. At the same time, scientists are increasingly focused on exploring the outer planets of our solar system, especially Jupiter and its enigmatic moon, Europa. Europa, with its thick icy shell, is believed to harbor an ocean beneath its surface, one that may hold the conditions necessary for life to thrive. Missions like NASA's Europa Clipper, slated for launch in the coming years, are poised to investigate this moon in detail, searching for signs of life and studying its environment. Meanwhile, the search for extraterrestrial life beyond our solar system is intensifying. With the launch of new telescopes like the James Webb Space Telescope, our ability to detect exoplanets, planets that orbit stars outside our solar system, has reached new heights. Some of these exoplanets are located in their stars' habitable zones, where conditions might be suitable for liquid water to exist. The discovery of a potentially habitable planet akin to Earth would be a momentous breakthrough, reshaping our understanding of life's potential in the universe. As we look toward the future, the possibilities are endless. Advances in space technology promise to transform our ability to venture far beyond the reaches of our solar system. New and more powerful telescopes, for instance, will allow us to explore distant exoplanets with greater precision. These instruments will help scientists identify planets with the best conditions for life, laying the groundwork for future missions to study these worlds up close. On the propulsion front, developments in technologies like ion propulsion and nuclear thermal propulsion are poised to revolutionize space travel. These advanced propulsion systems harness energy more efficiently, enabling spacecraft to travel at higher speeds and significantly reducing travel times. In the not-so-distant future, we could reach Alpha Centauri in just a few decades instead of tens of thousands of years. What was once science fiction could soon become a tangible goal. The exploration of space, with its immense challenges and even greater rewards, serves as a testament to humanity's unyielding curiosity and determination. Our pursuit of knowledge and our desire to understand our place in the cosmos continues to drive us forward. As technology evolves, so too will our capacity to explore the unknown, ultimately reshaping our understanding of the universe and our role within it. Artificial intelligence stands at the frontier of a new age of discovery, offering humanity unprecedented tools to explore the far reaches of the cosmos. As we strive to understand our universe, AI's ability to process vast amounts of data at speeds and accuracies far beyond human capability is opening doors to insights that were once thought impossible. Whether it's scanning the skies for signals from distant stars or analyzing the intricate composition of an exoplanet's atmosphere, AI can sift through immense data sets with precision, identifying patterns and anomalies that would take humans years, if not decades, to uncover. This ability can transform mission planning and execution. AI's speed in processing data allows space agencies to not only make real-time decisions during missions, but also to prioritize which destinations in the cosmos are most worthy of exploration. It can optimize spacecraft trajectories, predict the behavior of distant celestial bodies, and provide insights that help researchers focus their efforts more effectively. As we stand on the edge of revolutionary technological breakthroughs, the dream of exploring beyond our solar system feels more within reach than ever before. With the power of artificial intelligence, we can enhance the capabilities of telescopes, refine propulsion systems, and make the most of every resource available to us in our quest for the stars. But it's not just about the technology. It's about what this technology enables us to achieve. Humanity's journey into space is no longer a distant fantasy. It is a future we are actively shaping. The universe, vast and shrouded in mystery, beckons us to venture further, to explore its countless secrets, and to unlock its endless possibilities. We are preparing to answer that call. And with every new advancement, the cosmos feels a little less distant. Yet, as we set our sights on the stars, the concept of space colonization looms large on the horizon. It offers incredible promise, the potential to expand our species beyond the confines of Earth and secure a future for humanity that is no longer tethered to a single planet. But with that promise comes a host of challenges, especially ethical dilemmas that we cannot afford to ignore. One of the most urgent of these concerns is ownership. If humanity succeeds in reaching the Moon or Mars, who owns these celestial bodies? According to international treaties like the Outer Space Treaty of 1967, space is meant to be a domain accessible to all of humankind, free from territorial claims. But as technology continues to advance, the question of private ownership becomes ever more pressing. The possibility of corporations claiming resources on other planets or moons raises difficult moral questions. Is it justifiable to colonize another world when we still face so many unresolved issues here on Earth? The balance between exploration and exploitation is delicate, and how we navigate this issue will shape the future of interplanetary exploration. Another critical issue is the potential discovery of extraterrestrial life. Should we encounter microbial organisms on another planet, the ethical imperative to protect them will become a matter of utmost importance. Colonization efforts could unknowingly disrupt or even destroy alien ecosystems before we even understand them. As we seek to push the boundaries of our reach, we must carefully consider our responsibilities as stewards of life, not just life on Earth, but life wherever it may exist. The motivations behind our exploratory spirit, whether driven by curiosity and wonder or by the impulse to conquer and exploit, are central to this debate. In addition to these ecological concerns, the social and cultural implications of space colonization are profound. The societies we create in space will inevitably reflect the values and structures of those who build them. This raises the possibility of replicating the same inequalities and conflicts that we face on Earth. As we look ahead to creating new communities in the cosmos, we must ask ourselves how to build inclusive societies that respect diversity, promote cooperation, and avoid the pitfalls of division. The legacy of space colonization cannot simply be one of technological triumph. It must also reflect the best of what humanity has to offer. Furthermore, the psychological effects of leaving Earth behind cannot be underestimated. For those who venture into space, life on another planet will present challenges that are both physical and mental. The experience of living on Mars or the Moon or any other celestial body will not only affect the explorers themselves, but will likely have profound repercussions back on Earth. What lessons will we learn about sustainability, society, and human nature in the process? As we stretch beyond the confines of our home planet, we are not just learning about other worlds. We are discovering more about who we are and what it means to be human. These ethical considerations about ownership, life, society, and our own psyche challenge us to reflect deeply on who we are as a species and what we want our future to look like. As we venture into the cosmos, we must ask ourselves, are we seeking to explore for the betterment of all, or are we driven by a desire to dominate and possess? The answers to these questions will not only determine the future of space colonization, but will shape the very essence of what it means to be part of this remarkable species. Looking ahead, the next few decades will likely be a period of unprecedented scientific and technological exploration. As we prepare to leave Earth and expand our presence into the solar system and beyond, we must prioritize our efforts. The Moon, Mars, and the broader expanse of deep space each hold unique challenges and opportunities. Each of these destinations holds the potential to reveal not only more about our place in the universe, but also crucial insights into the survival of life on Earth itself. The Moon, in particular, is set to be a focal point for human exploration in the near future. Plans are already in motion for returning humans to the lunar surface, with the Moon serving as a critical testing ground for the technologies and strategies that will support future missions to Mars and beyond. The Moon's resources, such as water ice found in permanently shadowed craters, could be invaluable in sustaining a human presence in space. This water could be converted into oxygen for breathing and hydrogen for fuel, making long-term space exploration more feasible. The Moon's proximity and its potential as a stepping stone for deeper missions into the solar system make it an essential part of humanity's cosmic journey. The Moon offers a vantage point for astronomical observations like no other, allowing us to peer into the cosmos without the interference of Earth's atmosphere. Its barren surface, untouched by weather patterns or pollution, enables a clarity that is essential for understanding the vastness of space. This unparalleled perspective offers astronomers and scientists the ability to study distant stars, planets, and cosmic phenomena with an accuracy that simply isn't possible from Earth's surface. Meanwhile, Mars has long captivated the imagination of both scientists and space enthusiasts. The red planet, with its rugged terrain and vast deserts, holds within its dusty surface a history that continues to intrigue. The rovers currently exploring Mars are revealing a landscape that once harbored water, sparking curiosity about its potential to have supported life in the past. As we study the Martian soil and atmosphere, we seek to answer two critical questions. Did life ever exist on Mars, and could we as humans one day inhabit the planet? These questions are not just hypothetical. They challenge us to push the boundaries of our technology and scientific understanding. Our quest to answer these questions will undoubtedly lead to innovations that could, in turn, benefit life here on Earth. From advancements in robotics and artificial intelligence to new techniques for resource extraction and sustainability, the technologies developed for Mars exploration will reverberate back to us in ways that are not yet fully understood. Beyond our planetary neighbors, humanity's gaze is increasingly turning toward the deeper, more enigmatic reaches of space. With missions to asteroids and the outer planets already underway, we are striving to understand the very building blocks of our solar system. These celestial bodies hold secrets about the early days of the solar system and, more profoundly, about the formation of Earth itself. There is a growing effort to capture small asteroids and return samples from them, with the hope of uncovering organic materials that could shed light on the origins of life. By studying these cosmic fragments, scientists hope to reveal the materials that formed our planet, perhaps even answering the ultimate question of how life began. However, as we explore these distant regions, we must not lose sight of the fragile existence of life here on Earth. These exploratory efforts are not just about seeking knowledge, but also about ensuring that we are protecting the planet that sustains us. As we peer into the cosmos, we must continue to understand the delicate and interconnected nature of life on Earth, ensuring that our scientific endeavors also serve to preserve our home. Throughout the history of cosmology, each new discovery has raised more questions than answers. The journey of scientific inquiry is one of endless layers. As we peel back one mystery, we often uncover new ones beneath. The process of discovery is fundamental to the advancement of science, where each moment of clarity reveals yet another shadow. For example, when scientists first grasped the concept of black holes, it was a monumental achievement that helped solve a puzzle that had baffled researchers for decades. But this breakthrough only deepened the mystery. New questions arose. What happens inside a black hole? Is information lost forever within its event horizon? How do black holes influence the evolution of the universe? Each new answer led to even deeper inquiries, demonstrating the ever-expanding nature of our understanding. Similarly, the discovery of dark energy marked a pivotal moment in cosmology. Researchers were initially trying to measure the rate at which the universe was expanding. What they found, however, was far more astonishing. The expansion was accelerating. This observation, attributed to a mysterious force dubbed dark energy, revolutionized our understanding of the universe. Yet, the discovery did not bring closure. It opened a new set of questions. What exactly is dark energy? How does it fit into the larger cosmic puzzle? And what are its implications for the ultimate fate of the universe? This realization has sparked an era of intense study, where scientists are now racing to uncover the nature of this enigmatic force that seems to govern the cosmos. As we continue to push the boundaries of our knowledge, new technologies and methods emerge. These innovations, fueled by our quest to understand the universe, give us the tools to ask even more profound questions. With each new discovery, we move closer to understanding the intricate, sometimes unfathomable workings of the cosmos. Each solution, it seems, is simply another stepping stone, leading us into ever deeper realms of thought and exploration. The role of theoretical physics in this journey is indispensable. At its heart, this branch of science allows researchers to create models and frameworks that explain the fundamental forces and particles that govern the universe. Unlike experimental physics, which depends on observation and experimentation, theoretical physics is rooted in mathematics and imagination. It is through these abstract concepts that we come to understand phenomena that we cannot yet observe directly. A perfect example of this is the mysterious concepts of dark matter and dark energy, which together make up approximately 95% of the universe's total mass energy content. Although we cannot detect them directly, theoretical physicists use advanced mathematical models to infer their existence and to understand their impact on cosmic structures. This approach, which goes beyond traditional knowledge, helps to complete our picture of the universe, even as it challenges our understanding of reality itself. Theoretical physics also allows us to venture back to the very origins of the universe. By combining the principles of quantum mechanics and general relativity, physicists are able to create models that simulate the conditions just after the Big Bang. These simulations provide valuable insights into the earliest moments of the cosmos, although the results are often not yet testable with current technology. Nonetheless, these theoretical models offer the hope that future discoveries and experiments may one day confirm or refute these predictions, allowing us to better understand the birth of everything. At its core, theoretical physics serves as a guiding light, illuminating the darkest corners of our understanding. It encourages us to ask questions about existence itself, offering new realms of thought and possibility. With each new theory, we add another layer to the ever-expanding tapestry of knowledge, inviting curiosity and wonder into our collective journey through the universe. In this process, scientists must navigate the delicate balance between empirical evidence and theoretical conjecture. Empirical evidence, the foundation of scientific inquiry, is derived from careful observations, experiments, and data collection. On the other hand, theories are frameworks that help explain and predict natural phenomena. Striking a balance between these two components is vital for advancing our understanding of the universe. The process begins with formulating hypotheses. educated guesses grounded in existing theories. These hypotheses guide experiments designed to test predictions. For example, when Isaac Newton proposed the theory of gravity, he observed the motion of falling objects and crafted experiments to measure these motions. The results of these experiments provided empirical evidence that either supported or refined the original theoretical framework. However, empirical data alone is not enough. Interpretation is key. Scientists must critically evaluate their findings, often comparing them with existing theories. If the observations align with predictions, this provides strong support for the theory. But if the results contradict the predictions, they often lead to new hypotheses, pushing the boundaries of understanding even further. This ongoing cycle of observation, theory, and reinterpretation is what drives scientific progress, ensuring that our knowledge of the universe continues to evolve. In the world of scientific discovery, the relationship between empirical evidence and theoretical conjecture is not merely one of cause and effect. Rather, it forms a dynamic and symbiotic bond. As evidence accumulates through experiments and observations, it constantly shapes and refines existing theories. However, when discrepancies arise, when something does not align with the expectations of a prevailing theory, it becomes an opportunity for growth. These inconsistencies are not viewed as setbacks, but as windows into deeper understanding. New inquiries spring from these anomalies, sparking revisions of existing theories or at times leading to entirely novel concepts that were once beyond imagination. This constant back and forth between theory and observation creates a culture of perpetual discovery, with the scientific community driven by an unyielding thirst for answers. It fosters a sense of inquiry, where each question answered only leads to a cascade of new questions, expanding the boundaries of knowledge. Theories, which might have once seemed unassailable, are challenged, refined, or replaced as they are tested against the real-world data we gather. It is this very dynamism that powers scientific progress, shaping our understanding of everything from the tiniest particles to the grandest cosmic phenomena. Indeed, this relationship is not a one-way street. It is a partnership in the truest sense. Theories are the lenses through which we design our experiments, and in turn, the empirical data we gather informs and reshapes those very theories. Together, they form the engine of scientific advancement, propelling us forward and enabling us to unlock new realms of understanding about the universe. From the infinitesimally small world of particle physics to the boundless expanse of cosmology, it is this balance between theoretical speculation and empirical evidence that underpins the very core of science. Among the most fascinating and enigmatic fields of scientific inquiry is cosmology. This discipline, which seeks to understand the origins, structure, and ultimate fate of the universe, presents some of the most profound questions of existence. Perhaps the most captivating of these are those related to dark matter and dark energy. These mysterious substances, which together constitute about 95% of the universe's total mass energy content, remain elusive despite their observable effects. Dark matter, making up roughly 25% of the cosmos, does not emit or reflect light, making it invisible to traditional observational methods. Yet, through its gravitational influence, scientists can infer its presence and, to a degree, trace its distribution. Dark energy, which accounts for about 70% of the universe, is even more mysterious. Its primary influence is thought to be the accelerating expansion of the universe, a discovery that has fundamentally altered our understanding of cosmic evolution. But what are these entities made of? How do they interact with the visible matter we can observe? These questions continue to confound scientists, driving research in ways that challenge our most basic assumptions about the universe. Another question that lies at the heart of cosmological research is the origin of the universe itself. The Big Bang Theory, which posits that the universe began as an infinitely small and dense point about 13.8 billion years ago, provides a widely accepted framework for understanding cosmic origins. However, the events that transpired in the earliest moments of the universe's existence remain a subject of great speculation. Was there anything before the Big Bang, or was this singularity the true beginning of time itself? Could the universe be part of a cyclical process where it expands and contracts in a never-ending cycle? These questions push the boundaries of not only science but philosophy, as they invite us to consider the very nature of time, existence, and causality. The fate of the universe is another central mystery that cosmologists continue to explore. Recent observations have shown that the expansion of the universe is accelerating, likely due to the effects of dark energy. But what does this mean for the distant future of the cosmos? Will the universe continue to expand indefinitely, gradually growing colder and darker until all stars burn out in a scenario often referred to as the heat death? Or will there be a reversal, a contraction back into a singularity in what is known as the Big Crunch? These possibilities continue to fuel research, as their resolution would have profound implications for our understanding of cosmic evolution and the ultimate fate of all things. Among the most profound and tantalizing questions in the realm of cosmology is the search for life beyond Earth. As technology advances, scientists have discovered thousands of exoplanets in the habitable zones of distant stars, regions where conditions might be conducive to the existence of life. Yet, despite these exciting discoveries, we have yet to find definitive evidence of life elsewhere in the universe. This search not only holds the potential to expand our understanding of biology and the conditions that support life, but also forces us to reconsider our place in the vast cosmos. Are we truly alone, or is life elsewhere a natural consequence of the universe's complexity? This question challenges our assumptions about what it means to be human and how we define life itself. The pursuit of knowledge through science does not merely answer questions, it also raises new ones. With each breakthrough, the doors of possibility swing open wider, inviting further exploration. A quintessential example of this is the detection of gravitational waves, an elusive phenomenon predicted by Albert Einstein over a century ago. The confirmation of these waves, the ripples in space-time caused by massive cosmic events like the collision of black holes, not only validated Einstein's theory of general relativity, but also opened entirely new avenues for investigation in astrophysics. Discoveries such as these reveal the unexpected and often lead to new realms of inquiry. They inspire future generations to look beyond the horizon of the known and venture into the unknown. The stories behind these discoveries, stories of brilliant minds, daring ideas, tireless experimentation, and sometimes spectacular failure, resonate with people on a deeply human level. It is this human element, the dreamers, explorers, and persevering scientists, that draws us into the world of science and connects us to the universe in ways that transcend intellectual curiosity. At its core, scientific discovery is a narrative that speaks to our humanity. It compels us to question our origins, the nature of existence, and our place in the cosmos. It ignites the spark of curiosity, prompting us to explore new frontiers, and inspires innovation and creativity. Science invites us to ask the big questions, questions about life, the universe, and everything in between. And in doing so, it fosters a sense of wonder that is essential to the human spirit. It reminds us that the universe is not just an abstract concept to be studied, but a vast, awe-inspiring expanse waiting to be understood. As we continue our journey of exploration, we are confronted with the humbling reality that some aspects of the universe may always remain beyond our grasp. Despite centuries of progress in understanding the cosmos, there are still mysteries that evade our comprehension. One such mystery is the nature of dark matter and dark energy, whose enigmatic properties continue to puzzle scientists. These substances may make up the majority of the universe's mass energy content, yet their true nature remains a mystery, leading to questions about the very limits of human knowledge and the potential for discovery. Another mystery that challenges our understanding is the concept of infinity. If the universe is indeed infinite, it raises questions about the nature of space, time, and the very fabric of reality. How can we comprehend something boundless without limits? The infinite stretches the bounds of human cognition, confronting us with a concept that is impossible to fully grasp with our finite minds. These mysteries, while elusive, are the very things that drive scientific inquiry. They remind us of the vastness of the unknown and the limits of human reason. Yet, they also underscore the boundless potential of human curiosity and the ever-present desire to understand our place in the universe. The pursuit of knowledge, driven by these mysteries, is an endeavor that will continue to shape our future and inspire generations to come. Furthermore, there are aspects of time that may completely defy our comprehension. While we experience time in a linear fashion, the true nature of time could be far more intricate and complex than we can imagine. Some of the most advanced theories in physics, such as the notion of time as a dimension akin to space, challenge our conventional understanding, suggesting that our perception of time, restricted to a one-way flow, might not capture its full essence. These theories imply that time could be much more fluid, multidimensional, or even cyclical, something that stretches beyond the confines of linearity. As scientific knowledge evolves, it consistently pushes the boundaries of what is conceivable, unveiling new insights while simultaneously leaving some mysteries unresolved. These unanswered questions serve as a reminder that despite the significant progress science has made in explaining the cosmos, the universe still retains vast areas of unknowns that may remain forever out of reach. The ever-expanding nature of science continually redefines what we know, but the complexity and grandeur of the cosmos are such that some truths may always be just beyond our grasp. Scientists, driven by an unyielding curiosity, work tirelessly to deepen our understanding of the universe, often facing challenges posed by the limitations of contemporary technology. As these barriers arise, researchers employ innovative strategies, blending creativity and collaboration across disciplines to push the envelope of discovery. One of the primary methods scientists use is the development of new and improved observational tools. By enhancing existing instruments or designing entirely novel ones, researchers can collect more detailed data about distant celestial bodies and complex cosmic phenomena. For instance, advancements in telescope technology have allowed astronomers to peer into the farthest reaches of the universe with unprecedented clarity, enabling the observation of distant galaxies and nebulae in remarkable detail. Another critical strategy involves making the most out of existing technology. Scientists maximize the potential of the tools they already have, often integrating data from multiple sources, including space telescopes, ground-based observatories, and satellite missions. By pooling this information, they are able to create a more comprehensive understanding of cosmic events. This integrative approach allows researchers to overcome the limitations imposed by single instruments, combining diverse perspectives to build a fuller picture of the universe's intricacies. Furthermore, with the aid of sophisticated algorithms and computer simulations, scientists are able to model phenomena that are impossible to observe directly, such as the formation of stars or the mysterious nature of black holes. Collaboration is also an essential component of modern scientific progress. As technology evolves at a rapid pace, so too does the need for global cooperation. Scientists from all corners of the world frequently share their findings and collaborate on large-scale projects that pool resources and expertise. This collaborative spirit has led to remarkable discoveries that would have been inconceivable through isolated efforts. A prime example is the Event Horizon Telescope, an international collaboration that captured the first ever image of a black hole. Despite the individual limitations of the technologies employed, the collective effort of scientists across the globe was able to transcend these challenges, resulting in a groundbreaking achievement that expanded our understanding of the universe. In addition to technological advances and cross-border partnerships, education and public engagement play a vital role in the ongoing pursuit of knowledge. By fostering curiosity and interest in science, society ensures that future generations will continue to develop the tools and techniques necessary to further unravel the mysteries of the cosmos. Through outreach programs and collaborative research initiatives, scientists not only address the challenges of today, but also lay the groundwork for a future rich with discovery and innovation. The cycle of scientific progress is perpetuated by the enthusiasm and creativity of young minds, like ensuring that our grasp of the universe will continue to evolve in ways we cannot yet foresee. Yet, amid all the advancements and breakthroughs, humility remains a cornerstone of scientific inquiry. At its heart, science is a quest for knowledge, an ongoing process of questioning, exploring, and understanding the universe. But it is also a recognition that our current understanding may only be provisional. The willingness to embrace uncertainty, to acknowledge that our answers may only be stepping stones toward deeper truths, is essential in a field where knowledge is constantly evolving. Scientists must be open to new ideas and be willing to revise long-held beliefs in the face of new evidence. This openness allows for the flexibility needed to adapt to new findings and theories, a crucial trait in an ever-changing landscape of discovery. This sense of humility also fosters collaboration, as it encourages the sharing of ideas and insights among researchers. When scientists acknowledge the limits of their own understanding, they create an environment where collective knowledge can flourish. Collaboration not only facilitates the tackling of complex problems, but also accelerates the pace at which new breakthroughs are achieved. By working together, combining expertise from diverse fields, scientists are able to tackle questions that would otherwise remain elusive. And in the process, they uncover insights that are greater than the sum of individual contributions. In this way, the process of scientific discovery is an iterative, collaborative, and humbling journey. As technology advances and minds collaborate, the mysteries of the universe continue to unfold, slowly but surely, bringing us closer to an understanding of the vast and awe-inspiring cosmos in which we live. Yet, despite all that has been revealed, the true scope of the universe may still be far beyond our grasp, its deepest secrets hidden in the folds of time and space, waiting to be discovered by future generations. Humility in science is a cornerstone that often goes overlooked, yet it is essential in protecting against cognitive biases that can significantly hinder the pursuit of discovery. It is the subtle yet profound realization that no scientist holds an infallible truth, and that the path to understanding is constantly evolving. When scientists adopt humility, they position themselves to challenge their own assumptions and preconceptions, assumptions that, if left unchallenged, can cloud judgment and ultimately block innovation. Acknowledging the possibility of being wrong or that their interpretations could be incomplete or inaccurate is not a sign of weakness, but rather a vital practice that fosters the spirit of intellectual growth. In embracing this humility, scientists cultivate a culture of skepticism, a natural antidote to complacency. This environment of critical thinking is essential for scientific progress because it is the rigorous testing of ideas and hypotheses. Humility, then, is not simply about personal modesty. It is a force that propels science forward by ensuring that ideas are subjected to scrutiny, leading to deeper insights and more robust conclusions. It is through this process of self-correction that the integrity of scientific investigation is maintained. Transparency in reporting findings, whether they align with or challenge existing theories, is critical for upholding the reliability of science. This commitment to accountability strengthens trust, not only within the scientific community, but also with the broader public, who rely on science to inform decisions that impact their daily lives. As science becomes increasingly intertwined with policy, it is this trust that ensures its credibility and continued relevance. In the face of these challenges, keeping the public engaged with space and science remains a multi-layered task. The complexities of these fields often leave many feeling distant from their realities, yet the beauty of the cosmos and humanity's unending quest for understanding have the power to captivate minds across the globe. To bridge the gap, two fundamental elements are crucial: education and storytelling. By weaving captivating narratives around scientific discoveries, such as the ongoing exploration of black holes or the intricate patterns of far-off galaxies, science can be made accessible and engaging. These stories have the power to illustrate the profound significance of space research, transforming abstract concepts into ideas that resonate with everyday people. An effective means of maintaining public interest is through educational initiatives that reach diverse audiences. Schools, museums, and public lectures all serve as vital spaces where curiosity can be sparked and nurtured. However, it is citizen science programs that offer a unique and transformative opportunity. By involving ordinary people in real scientific research, whether it's identifying galaxies or tracking the movements of local stars, such programs allow individuals to forge a personal connection with the scientific community. This engagement provides not only the knowledge necessary to understand complex topics, but also a sense of ownership in the collective endeavor of exploring the universe. Media, in its many forms, plays an indispensable role in shaping the public's perception of science. Documentaries, podcasts, and social media platforms act as conduits for new discoveries and ongoing research, presenting these findings in ways that captivate and inspire. The power of visual storytelling cannot be overstated. Images from distant telescopes or footage of space missions carry a weight that words alone cannot convey. These stunning visuals, paired with informative yet accessible content, make the vastness of space feel not only understandable but inviting. They have the potential to transform the daunting into the familiar, to spark curiosity where there was once indifference, and to ignite a sense of wonder that fuels continued interest. Furthermore, collaboration between scientists and communicators is vital to ensuring that the knowledge and excitement of scientific discovery reach the broader public. When researchers take the time to explain their work in clear, relatable terms, they bridge the often wide gap between complex theories and public understanding. Events like World Space Day, stargazing nights, and interactive exhibits can help maintain this momentum, keeping the conversation about space exploration alive and vibrant. These platforms not only educate but also cultivate a sense of excitement and wonder, ensuring that the public remains not just informed but passionate about the universe and humanity's place within it. Imagination and creativity are integral to scientific exploration. While rigorous observation and experimentation form the backbone of inquiry, it is often the visionary thinking of scientists that propels the field forward. Every time a scientist gazes at the night sky, they do not merely see stars, they see the untapped potential of the cosmos. It is through the lens of imagination that some of the most profound questions are asked and the most groundbreaking theories are proposed. Take, for example, the concept of black holes. The very idea of a region of space where gravity is so intense that not even light can escape was born from creative thinking, a concept that transcended the limits of current understanding. Without the imagination to picture such a phenomenon, it is doubtful that theories about black holes would have ever taken shape. These imaginative concepts are not merely fanciful ideas. They play a crucial role in the development of mathematical models that allow scientists to explore the universe in new ways. By providing a framework within which these ideas can be tested, they lead to groundbreaking insights into the very fabric of space and time itself. In this way, creativity and imagination are not separate from scientific inquiry. They are essential components, guiding researchers as they chart the unknown and unravel the mysteries of the cosmos. Creativity stands as the cornerstone in the advancement of technology, especially in fields like cosmic exploration. It is through the visionary power of the human mind that we are able to conceptualize what seems unimaginable and transform it into reality. Take, for instance, the evolution of telescopes. These once simple optical devices, constructed with nothing more than a pair of lenses, have grown into massive, complex structures capable of peering into the farthest reaches of the universe. What began as a rudimentary tool for stargazing has now blossomed into an instrument that allows us to observe light emitted from distant stars and galaxies billions of years ago. This transformation wasn't merely the result of improving existing designs. It was driven by bold, imaginative leaps that envisioned what could be possible, rather than simply enhancing what was already in place. Scientists and engineers have continually harnessed their creative instincts to stretch the limits of our technology, pushing boundaries and providing us with a more profound view of the cosmos than we ever thought possible. Moreover, imagination isn't only crucial in the development of new tools, it also fuels the stories we tell about our place in the universe. From ancient mythologies that first inspired early astronomers to modern narratives surrounding space exploration, these stories not only captivate our hearts and minds, but also inspire the next generation of explorers. They invite us to look up at the stars filled with wonder and curiosity. In the vast and complex realm of cosmology, imagination serves as the bridge between what we know and the endless unknown. It sparks an eternal curiosity that propels humanity forward, driving us to seek out the mysteries that lie hidden within the cosmos. A striking example of this unrelenting curiosity is the multiverse theory, which suggests that our universe may not be unique, but rather just one of an infinite number of universes, all existing simultaneously. These universes could operate under entirely different physical laws, creating an astonishing array of realities, each with its own set of rules. The theory emerges from various scientific disciplines, such as quantum mechanics, string theory, and cosmological inflation. These theories propose mechanisms by which other universes could exist alongside our own. Perhaps one of the most captivating aspects of the multiverse theory is the idea that our universe, with its finely tuned constants like the strength of gravity or the charge of an electron, appears to have been calibrated perfectly for the emergence of life. If even one of these constants were to differ, life as we know it might not exist. The multiverse theory offers a possible explanation for this cosmic fine-tuning. If there are countless universes, each with different physical constants, it becomes more likely that one of them, ours, perhaps would be suitable for life. However, the evidence supporting the existence of multiple universes is largely indirect. One of the most intriguing pieces of evidence comes from the cosmic microwave background radiation, a remnant of the Big Bang. This radiation shows subtle fluctuations that some scientists propose could be the result of interactions with other universes. Additionally, string theory, with its complex mathematical framework, points to multiple dimensions and inevitably multiple universes. Despite these compelling ideas, the task of directly proving the existence of alternate realities remains a monumental challenge. With our current technological capabilities, observing other universes is fundamentally out of reach. Still, the multiverse theory continues to be a topic of deep discussion in cosmology and beyond. It raises profound questions about the nature of reality, urging us to ponder our place within it and consider the vast possibilities that lie beyond the stars. The concept of parallel universes, often explored in popular culture, adds another layer to our imagination. It suggests the existence of alternate realities where different versions of ourselves experience the consequences of different choices. While this idea is often treated abstractly in movies and books, in the realm of physics, particularly through quantum mechanics, it takes on a more structured and scientific form. This is known as the many worlds interpretation. According to this interpretation, every quantum event causes the universe to branch, creating multiple outcomes and, therefore, multiple coexisting universes. For instance, when a particle has two possible spin directions, the universe splits, allowing each possible outcome to occur in its own distinct reality. This process would mean that every choice we make, every event that unfolds, spawns a new universe in which a different version of ourselves plays out a different reality. It's a fascinating idea, suggesting that the possibilities of existence are far broader than we can imagine. The broader concept of parallel universes, however, encompasses far more than just quantum outcomes. It opens the door to other possibilities, such as universes with different physical laws, extra dimensions that transcend our perception, or entirely new forms of matter and energy. Some of these universes might never interact with our own, unlike the interconnected branching realities suggested by the many worlds interpretation. This distinction emphasizes that while parallel universes cover a wide array of potential models, the many worlds interpretation offers a specific perspective rooted in quantum mechanics. Both concepts, parallel universes and the many worlds interpretation, invite us to reconsider the nature of reality. They challenge our understanding of existence, pushing us to explore the boundaries between what is known and what is unknown. The many worlds interpretation provides a captivating perspective on the branching possibilities inherent in quantum mechanics, while the broader idea of parallel universes stretches the imagination to consider a multitude of alternate worlds, each waiting to be discovered. Together, these ideas open new avenues for understanding the cosmos and the place of humanity within it, urging us to rethink the very fabric of reality. The idea of parallel universes has long been a source of fascination for both scientists and philosophers. It has sparked debates that stretch far beyond the confines of traditional science, touching on questions of existence, identity, and the very nature of consciousness. The scientific exploration of parallel universes often begins with quantum mechanics, which posits that every decision we make could lead to branching realities, giving rise to countless outcomes across different universes. This suggests the existence of infinite variations of ourselves, all living out their own versions of reality in separate realms. From a scientific standpoint, the multiverse theory expands on quantum mechanics by incorporating ideas from cosmic inflation. This theory proposes that after the Big Bang, our universe underwent an incredibly rapid expansion, which may have created bubble universes. These bubbles, each with its own distinct set of physical laws, could constitute an infinite number of universes. The sheer scale of this possibility forces us to reconsider our place in the cosmos, suggesting that what we experience might only be one version of countless potential realities. Philosophically, the existence of parallel universes raises profound questions about the nature of self and identity. If every choice we make gives rise to a new universe, what does that mean for our concept of individuality? Are we defined solely by the experiences we have in this particular universe, or do alternate versions of ourselves exist in other realms, experiencing lives that diverge from ours? These questions delve deeply into the nature of consciousness and spark debates about the concepts of fate and free will. In exploring the idea of parallel universes, we are confronted not only with the limitations of our current understanding of reality, but also with the vast, uncharted territories that lay beyond. What if everything we've ever known is only a small piece of a much larger cosmic puzzle? The implications of parallel universes open up a realm of thought-provoking metaphysical questions that challenge our very understanding of morality and consequence. If every possible outcome of our decisions exists somewhere in the vastness of existence, how does this shape our sense of responsibility? Are we still held accountable for our actions when alternative versions of ourselves are living out different lives in parallel realities? As we dive into the scientific theories and philosophical questions surrounding parallel universes, we find ourselves at the crossroads of knowledge and awe, confronting the complexities of existence and the nature of reality itself. At the heart of this exploration lies string theory and quantum mechanics, two revolutionary ideas that significantly shape our understanding of the multiverse. String theory proposes that the very building blocks of matter are not the point-like particles we once believed them to be, but rather minuscule vibrating strings. These strings, according to the theory, can exist in countless configurations, and it is through their different vibrational states that various particles emerge. This challenges the traditional views of physics, opening the door to the possibility of multiple alternative realities. Imagine, instead of a single universe, a cosmic landscape filled with countless others, all emerging from the delicate dance of these vibrating strings. On the other side, quantum mechanics introduces a notion of inherent randomness into the universe, particularly at the smallest scales. It asserts that particles do not have fixed states until they are observed. The famous thought experiment known as Schrödinger's cat illustrates this point dramatically. A cat can be simultaneously alive and dead inside a box until someone opens it to check. This idea suggests that all possible outcomes of quantum events occur in parallel, each branching off into different dimensions or universes. Here, we are faced with the possibility of a multiverse, where every potential reality coexists, each one representing a different outcome of quantum uncertainty. When string theory and quantum mechanics converge, they form a powerful framework that enhances our understanding of the multiverse. String theory, with its multiple dimensions beyond the familiar four, suggests that our universe could be just one among many possible configurations in a far larger space. Within this framework, each universe in the multiverse could have its own distinct set of physical laws and constants, shaped by the vibrational states of strings in that particular corner of the cosmos. This interplay between the two theories invites us to rethink the very nature of existence, envisioning a vast, endless tapestry of universes, each a reflection of different possibilities, shaped by the intricate interactions between strings and quantum states. As scientists continue to delve deeper into the intricacies of string theory and quantum mechanics, the concept of the multiverse expands, sparking curiosity and deep profound questions about our place in the cosmos and the very fabric of reality itself. The idea of parallel universes, multiple coexisting realities, fundamentally challenges and enriches our understanding of existence. Traditionally, we've thought of our universe as the singular one, governed by specific, unchanging laws and constants. However, the notion of parallel universes suggests that there could be countless other realities, each with its own unique laws of physics, histories, and possibly even forms of life. This brings us to questions of identity and choice. If every decision we make leads to the creation of a new universe where the alternative decision is realized, what does that mean for the concept of free will? It implies that our lives unfold not as a linear progression, but as part of an intricate web of outcomes, where every conceivable choice is played out somewhere in the vastness of existence. This notion fosters a sense of awe and complexity, but it also raises questions about our role in the grand scheme of things. How do we understand our significance in a reality where every possible version of ourselves exists? And what does this mean for the idea of personal responsibility? The existence of parallel universes could also force a fundamental reevaluation of some of the most basic scientific principles. If other universes operate with different physical constants, could this explain why our universe is governed by the specific set of laws we observe? Could these parallel realities hold the key to unlocking new scientific discoveries, advancing fields like quantum mechanics by suggesting that particles exist in multiple states simultaneously, influenced by interactions with alternate realities? In this way, the very nature of reality becomes far more intricate and multifaceted than we could have ever imagined. As we explore these theories, we are not only pushing the boundaries of our scientific knowledge, but also grappling with the philosophical implications of our existence in a potentially infinite multiverse. This exploration raises profound questions about what it means to be human in a universe, or perhaps a multiverse, of infinite possibilities. The idea of parallel universes invites us to reflect on our place in the cosmos, sparking deep introspection about identity, choice, and existence. In pondering our potential counterparts across countless alternate realities, we are reminded of the vastness and mystery that surrounds us. The very nature of reality, it seems, may be far more complex and expansive than we could have ever imagined. Time travel, an idea that has fascinated humanity for centuries, remains an area of both scientific inquiry and philosophical speculation. The theoretical models that discuss the possibility of time travel propose intriguing ideas grounded in the realm of physics that turn our conventional understanding of time upside down. At the core of these discussions lies the theory of relativity, developed by Albert Einstein. According to relativity, time is not a fixed and absolute entity. Instead, it is intertwined with space to form what we call space-time. This means that the passage of time can vary depending on an object's speed and the strength of the gravitational fields it encounters. The faster an object moves, or the more intense the gravitational force acting on it, the more its perception of time is affected. One of the most captivating ideas related to time travel is that of wormholes. These theoretical constructs, often depicted as tunnels through the fabric of space-time, could provide shortcuts between distant points in the universe. If wormholes exist and could somehow be stabilized, they could offer a potential means of traveling through time. A traveler might, theoretically, enter one end of a wormhole and emerge at a completely different point in time, potentially even in the past or future. While wormholes remain speculative and largely unproven, they offer a tantalizing glimpse into the possibility of traversing time in ways that defy our current understanding. Another fascinating concept involves what are known as closed time-like curves. These hypothetical paths through space-time loop back on themselves, potentially allowing someone to return to an earlier point in time. Theoretical solutions to Einstein's field equations suggest that such curves could exist, providing the possibility of time travel. However, these scenarios often lead to paradoxes, which bring us back to the most well-known of these, the grandfather paradox. This paradox suggests that a time traveler could, by traveling to the past, prevent their own existence, creating a logical contradiction. Such paradoxes highlight the challenges inherent in the notion of time travel, revealing the complexities of navigating time in a non-linear fashion. Time travel remains a subject of both scientific fascination and philosophical intrigue. While it sparks endless possibilities, it also raises fundamental questions about the nature of time, causality, and reality. In contemplating time travel, we are invited to explore the very fabric of the universe itself, its laws, its limits, and its potential. Moreover, physicists have long pondered the potential implications of quantum mechanics in the context of time travel. Some quantum theories suggest that parallel universes or alternate timelines could emerge from decisions made in the past. This idea raises profound questions about the very nature of reality and the existence of the multiverse, expanding our understanding of potential time travel mechanisms. While practical time travel remains securely anchored in the domain of science fiction, these theoretical frameworks ignite curiosity, encouraging us to think deeply about the fundamental structure of our universe and the mysterious nature of time itself. Time travel, as a concept, has captured the imaginations of scientists, philosophers, and the general public alike. Yet it is riddled with paradoxes and challenges that make it an exceptionally complex topic. One of the most famous paradoxes in time travel discussions is the grandfather paradox. Imagine a time traveler who goes back in time and unintentionally prevents their grandfather from meeting their grandmother. If this happens, the time traveler would never have been born, creating a logical inconsistency that directly challenges our understanding of causality. This paradox forces us to confront the intricate nature of time and its connection to cause and effect. Another fascinating challenge arises from the concept of closed time-like curves, CTCs, which emerge from solutions to Einstein's equations of general relativity. These curves suggest that under certain conditions, it might be theoretically possible to return to a previous point in time. However, the very existence of such curves brings about numerous complications. For example, if a person were to travel back in time and alter a historical event, would they actually succeed in changing anything? Or would their actions always have been a part of the timeline, thereby preventing any alteration from occurring? This conundrum raises further questions about the rigidity or fluidity of time itself. Moreover, many theories of time travel propose conditions or materials that are not currently observable or known in our universe. Concepts such as negative energy, wormholes, or exotic matter remain speculative and present significant challenges in terms of feasibility. To fully understand the laws of physics as we currently comprehend them raises even more questions than answers about the practical implementation of time travel. Could the universe ever permit such phenomena, or are these merely the flights of fancy born from the human imagination? Beyond the scientific implications, a deeply philosophical dimension to consider. If time travel were possible, it could radically alter our understanding of history and personal identity. Philosophers frequently debate whether a time traveler would be the same person after experiencing different timelines. Would the act of stepping into another timeline create multiple versions of the individual, and how would this affect our perception of reality? The challenges inherent in these questions create a fascinating tapestry of inquiry that continues to engage thinkers across both scientific and philosophical realms. Time travel has also become an iconic theme in modern science fiction, appearing in films, television shows, and literature. From the legendary DeLorean in Back to the Future to the intricate time loops in Looper and the endlessly complex narrative of Doctor Who, these stories explore time travel in myriad ways. Each depiction presents a unique interpretation of the concept, often examining the consequences of altering past or future events. These narratives invite us to reflect on fate, agency, and the very nature of time itself. More than just entertaining tales, these stories reflect societal hopes and fears, offering moral quandaries about the risks and rewards of meddling with time. For instance, the ability to change one's past can evoke powerful feelings of nostalgia or regret, as characters grapple with the weight of decisions that could forever shape their futures. In many cases, these narratives emphasize the potential for unintended consequences, warning that even small alterations in time might spiral into catastrophic events. This serves as an invitation to consider the concept of personal responsibility. What would you change if given the chance? And what is the true cost of such alterations? Modern science fiction also introduces concepts like multiverses and alternate realities, challenging our conventional understanding of time as a linear progression. Series like The Umbrella Academy take time travel beyond simple temporal manipulation, weaving in themes of family, growth, and destiny. In these stories, the journeys through time profoundly influence relationships and shape individuals' futures in ways that go beyond mere changes in history. Such explorations invite viewers to reflect on the fabric of reality itself, suggesting that time may not be as straightforward as it seems. Ultimately, these imaginative portrayals of time travel do more than entertain us. They provoke deep philosophical questions about our existence. Could time travel be a tool for exploration, or is it fraught with peril? Through the lens of science fiction, we confront the boundaries of human understanding, gaining insight into our own lives, choices, and regrets. The genre encourages us to consider not just how time travel might function, but also how the concept of time shapes our very understanding of who we are and what we can become. Shifting focus to the realm of scientific possibility, the concept of time travel has long been a captivating subject for theorists. While it is still far from being a practical reality, advancements in physics have provided intriguing glimpses into how time travel might one day become feasible. One of the most compelling theories comes from Albert Einstein's theory of relativity, which posits that as an object approaches the speed of light, time slows down relative to an outside observer. This phenomenon, known as time dilation, has been demonstrated in particle experiments, suggesting that if astronauts could travel at near light speeds, they would age more slowly than people on Earth. Although this effect has been observed at microscopic scales, the immense engineering challenges of building a spacecraft capable of such speeds make this a distant possibility. Another concept that fuels the imagination is the idea of wormholes, hypothetical passages through the fabric of space-time that could connect distant points in the universe, or even different times. Theoretically, wormholes could provide a shortcut through space and time, potentially allowing time travel to the past or future. However, the creation and stabilization of a wormhole would require exotic matter with negative energy density, a substance that remains elusive in our current understanding of the universe. Without such material, the concept remains speculative at best. Finally, the notion of closed time-like curves, CTCs, offers another intriguing possibility for time travel. These curves are theoretical paths through space-time that loop back on themselves, potentially allowing for time travel to the past. While mathematically plausible, the implications of such travel pose significant challenges both philosophically and scientifically. The famous grandfather paradox is just one example of the complications that arise when considering the consequences of tampering with the past. As physicists continue to explore these ideas, they expand our understanding of the universe and the enigmatic nature of time itself, revealing the complexities and tantalizing possibilities that time travel might one day present. In conclusion, time travel remains a fascinating area of exploration where science and imagination collide. While we may still be far from achieving practical time travel, the theories and ideas proposed by physicists challenge our fundamental understanding of time and reality. Whether through the lens of quantum mechanics, relativity, or theoretical concepts like wormholes, time travel continues to captivate our curiosity, urging us to reconsider the very fabric of existence. If time travel were ever achieved, it would require a radical shift in our perspective, transforming time from a mere measurement of past, present, and future into a vast, interconnected web of possibilities waiting to be explored.